All right. Welcome you all to the second day of the CHAM++ workshop, to the 18th annual CHAM++ workshop. But before we start with the program today, I just have a couple of announcements. Let me see if there is any other that have accumulated in my stream. No. First announcement is that today's schedule is slightly different than yesterday's to accommodate our speakers' schedules. So our lunch break is later than yesterday. It will start at 12:50, if I'm not mistaken, and we'll resume after lunch session at 2 o'clock. So whatever it means in these days of virtual conferences and real lunches, adjust your schedules accordingly. The second thing that I would like to do is yesterday I announced that we will do a traditional conference photograph, but of course virtually. And so what that means is that we will be, ideal time would be after the first keynote, but maybe some of you are not ready, maybe too short a warning. So after the second keynote or just before the second keynote will be a good time, and we will announce it here what that time is. What it means is that it will be nice if everyone turns on their cameras. And since it's not a still photo, you can even wave. We can make a little pass over both screens of the audience and get everyone in a frame, so we have a little snippet of all the attendees to show for the workshop. So let's do that in the afternoon. Jamin, Matthias are the program chairs. Do you have anything to add, either one of you?
No, I think we're good to go.
Okay. So it's a great pleasure for me to then welcome Professor Hartmut Kaiser, who is the keynote speaker this morning. I've been wanting to get him to do this keynote for our workshop for a few years now, and some schedule thing or mistake or the other on our part and business on his part has always postponed that till today. And of course, even today, it won't be in person as I would have wished, but it's great to have you at the CHAM++ workshop, Hartmut. So Professor Kaiser is a professor in the computer science department at LSU, Louisiana State University, for a while. That's where I met him first a few years ago. He's also a senior scientist at the Center for Computation and Technology at LSU, and leads a group that's called the Stellar Group within that CCT. They work on a variety of things, but a design and implementation of HPX is what he's known for, and elaboration of the Phylanx model. He's probably even more broadly known for his prowess and his expertise and his contributions in the C++ world, the advanced C++, and then the recent upcoming C++ standard activities. He's significantly involved in that. He's a member of the standards committee. And oftentimes for this group, it is probably useful to know that whenever people talk about task-based runtimes or some alternatives to MPI and so on, HPX and CHAM++ are often mentioned in the same breath. So it will be great to hear from him today. Without further ado, Hartmut.
Thank you so much, Sanjay, and thanks everybody to having me here. Let me see if I can get my screen to be shared. 1 second. Okay. Can everybody see the screen?
Yes, that's good.
Okay, great. Okay. Thanks again for having me at your workshop. As Sanjay said, we are trying to get that organized for years, but it never really happened. So I'm very glad that this time we were able to organize things. What I'm going to talk about today is how we can do asynchronous programming in modern C++. And what I'm especially excited about is to show you some things, how the now accepted C++ 20 standard and the language features that have been introduced in that standard can help us to simplify writing asynchronous code. Because so far it was always a problem to write asynchronous code because you somehow had to take your brain out, turn it around inside out, and plug it back in order to really understand and write asynchronous code. And that will be much, much simpler with the upcoming language features that will be available hopefully soon in the compiler you work with. The picture here on that screen is a still image from a simulation of one of our HBX applications. It's a double white dwarf system. And you might be interested why I'm showing that. Well, our astrophysicists are very excited about being able to simulate these white dwarf systems because they are assumed to be the progenitors for the supernovae of type 1a, which is very important for the astrophysicists because it allows them to measure distances in the universe, which wouldn't be, oh, it's just one method of measuring the distances. And that's a very important thing to do. OK, let's get started. If you look at parallel applications and at the tools available to us when writing parallel applications, then especially in the C++ world, we are faced with a multitude of tools that usually don't fit very well together, that are badly integrated with the C++ language, and in general have a couple of flaws I will elaborate about in the next slides. Also, if we look at even at applications that we believe are nicely parallelized, we usually see this kind of behavior in the utilization of your machine. What that image shows is the utilization of a couple of cores in a typical application, where the green bars show that the core is busy and the white gaps in between the green bars just indicate that the cores have nothing to do. And this is a fairly common thing we have experienced and have seen in many applications where the programmer said, oh, I really parallelized everything. I'm using all the 48 cores I have on my node. But if you look closer, you will see that there's a lot of gaps in the resource utilization. And I will talk about that a bit more, how that can happen. So in real world applications, we usually have the problem that we have insufficient parallelism. And the big problem here is that this insufficient parallelism is, in part at least, imposed by the programming model we are using. And I specifically talk about OpenMP here and MPI. OpenMP as the go-to parallelization framework for on-node parallelism, MPI as the go-to library for distributed parallelism, both of which are very badly integrated with C++. And I'm very happy that the C++ community over the last years has caught up and has tried and succeeded in part in creating tools that very nicely integrate with the C++ language. And we will talk about them later. What's the problem with OpenMP? And just let me say a word before I actually continue. On this slide, I usually have at least one person in the room that gets really, really upset. Because how can I dare to criticize OpenMP or MPI? My point here is that OpenMP and MPI are very, very flexible and very widely used. That, on the other hand, a naive use of those tools usually leads to problems that limit the parallelization and the resource utilization. And it takes a lot of effort and a lot of expertise from the programmer to overcome these limitations, so that both OpenMP and MPI don't give you full resource utilization out of the box without additional significant effort on the programmer side. One example here is the enforced barrier at the end of the parallel for loop in OpenMP. And yes, I know about the no wait clause, but it's kind of useless because, again, you have to do your own programming in order to find out when the loop actually is done. Or in MPI, in many MPI applications, you have that global communication barrier after each time step that puts all nodes into lockstep and makes the application wait for the slowest node before it can continue to the next time step. We also see that we are over-synchronizing by waiting for more things than are actually required by the algorithm. Well, as I said, the lockstepping between nodes is a clear over-synchronization because most of the time, some of the nodes could actually go ahead to the next time step without any problems, but the global barrier prevents us from doing so. Also, there's insufficient coordination between the on-node and off-node parallelism. Have you ever tried to call an MPI API function from an OpenMP thread? If yes, then you know what I'm talking about. So there's insufficient co-design of the tools going on, and that not even talking about adding things like CUDA or HIP or other toolkits, which all give us different distinct programming models for different types of parallelism, which is a major pain for the programmer. Okay, what challenges do we face? We need to design a programming model and programming environment that exposes an API to us that intrinsically enables overlap on computation and communication without additional effort on the programmer side, which enables fine-grained parallelism so that we can utilize our resources much better, which requires minimal synchronization between dependent things so that only the things that are needed to be computed are taken into account in the decision what to do next. We need tools that make data dependencies explicit because only that allows for the system to decide properly what are the next tasks to run. And we need manageable paradigms for handling parallelism, because if you start talking about fine-grained parallelism, you start talking about millions of threads, and no sane person can handle millions of threads and can reason about millions of threads at the same time. And also the additional challenge I am seeing is that all of that has to integrate well with the existing C++ language and the standardization efforts. Asynchrony is definitely one of the factors that can help improving the resource utilization of our machines, but it's not sufficient alone. We need also facilities for efficient parallelization, for efficient creation of threads, for efficient composition of asynchronous tasks, sequential and parallel composition, we will see that in a bit, and efficient synchronization between threads, and certainly facilities that give us the means of asynchronous data transfer between threads and between nodes. All of that really integrated into the programming model so that, as I said, the programmer doesn't have to invest additional effort in order to get these nice features. That should be kind of be automatic if you follow the programming model that the system gives you. We have taken all that, or have tried to take into account all these problems and all these ideas while developing HPX. So it has been developed kind of from first principles. And today is one of the available asynchronous many-task runtime systems. As Sanjay said, next to Charm, well, I'm not going to list all of them here. There are many available. And the sad story is that essentially each national lab develops their own runtime system, and some of the labs develop more than one runtime system at the same time, which is really, really funny and interesting to watch. Okay, so what is special about HPX? We call it the C++ standards library for concurrency and parallelism. And that is for a reason, because what we've done, we have tried to expose a coherent and uniform API in a very standards-oriented way, meaning that if you take a standards-conforming C++ program that uses the C++ standard library, and you change some of the namespaces in your program from std : to hpx : you get a fully functioning program again, with a nice side effect that it usually runs faster. One of those, well, just one example for that, we work with Oak Ridge National Labs on a quantum Monte Carlo simulation, which is called DCA++. And there, just the change of the namespaces has given us a speed up of about 20%, which is quite amazing. And that API we expose can be used for local parallelism, for distributed parallelism, and also in heterogeneous applications. That DCA++ application, for instance, is very heavily using GPUs. It's running on Summit, and it's utilizing the Summit GPUs to a large extent. So HPX enables you to write fully asynchronous code using hundreds of millions of threads. And the important piece is that it gives you a unified syntax and semantics in terms of local and remote operations. If you follow that programming model we have developed, you essentially get an emergent autoparallelization property out of that. And I will highlight that in this talk a bit. A quick structure of HPX, not too many words about that. 4 major blocks: is threading, subsystem, synchronization. We have a global address space, which allows us to move things around, and a networking layer. All of that exposed to the application on top through a concurrency and parallelism APIs that are conforming to the C++ standard, and tied together with a performance counter framework that can be used to drive engines, policies, to control and to introduce runtime adaptivity into the system. Just as a example, how does an API look like? If you know the C++11 or newer standards, then you know about standard thread, mutex, future, async, and so on and so on. And we have all these facilities available in HPX as well. And you might ask, why did we implement things like std function or std any again? Well, we want to extend the APIs the standard gives us for the distributed use case. So in case of std function, you can bind an HPX function on one node, send it over the wire, and execute it on the other node, which is very interesting, very powerful, very C++-like, helps writing modern C++ code. One important part, and that's where the C++ community recently has caught up with the parallelization necessities of applications, is the introduction of parallel algorithms into C++ 17. We know all the algorithms in C++ since late 90s. But now, finally, those have been extended to give you parallelism. And the way they have done that is that all the algorithms now have an additional argument, the first argument, which is called the execution policy. There are several execution policies introduced by the standard. I will highlight only 2 of them here. One is par, the parallel policy that instructs the system, the runtime system, or the library to parallelize a particular loop, or sec, just if you want to force one of those loops to run sequentially anyway. A quick example, standard fill takes begin and end of the range to fill with zeros. And in order to parallelize that loop, all you have to do is you pass an additional argument to the algorithm. The same pattern has been applied to all the other 150 algorithms the standard has. Now, you might say, this is still fork-join parallelism in the same way as OpenMP introduces, and in the same way as OpenMP introduces a barrier after the execution. This mode of operation still introduces that barrier. And that's one point where we have tried to extend the things in the standard in HPX, and I will give you an example for that in a second. So let's look at two more examples. This is the one I just showed you. Just fill the vector with zeros. That doesn't give you much control over where things run and how things are being scheduled. It just tells the system, hey, you parallelize that in any way you like. I don't care as long as it runs faster than before. In HPX, and aligned with ongoing standardization efforts, we have added additional customization possibilities to that parallelization scheme. The user can write what we call executors, which are essentially very simple objects that decides how, where, when, and in what way things are being scheduled. And you can attach your executor to the par execution policy and customize the algorithmic execution that way. Often you want to additionally influence affinities, chunking, scheduling, and so on. And you can do that by writing some special customization object, some parameters object, which can be attached to the execution policy as well. In what we have done in HPX, we have extended the execution policies to be asynchronous, and that really mitigates the fork-join parallelism disadvantages. Because what these asynchronous execution policies, partask and sectask as an example, do, they turn the formally synchronous functions and algorithm invocations into a function that returns a future. So you just kick off the operation and get a future back, which represents the end of the execution of that algorithm. So the parallel construct is executed asynchronously, and that helps with improving the utilization of your machine, because while the parallel loop is tapering off or synchronizing or waiting for all the iterations to catch up, some of the cores are being freed up naturally, which before has led to diminished resource utilization. But since this is executed asynchronously, other work can be started in parallel or concurrently and can take over the cores that are freed up by the loop execution. And that certainly allows us to integrate that into a larger asynchronous control flow, as I will show in a second. So let's talk about futures. And I have shown that many times, so I will be brief. Let's assume we want to calculate the universal answer. So the answer to life, universe, and everything else, which we know from the literature, is 42. But the drawback is that the calculation of that 42 actually takes 7.5 million years. And nobody wants to wait for 7.5 million years without doing anything else. So we construct a computer we call Deep Thought. And the thing that Deep Thought computer does, it uses async to create a new thread to launch the universal answer function that will start running on a separate thread. Then we can go on with our lives for said 7.5 million years. And once we are sick and tired of waiting, we call .get on the future object that was returned from async. And .get can do two things. Either the answer has been computed, then get will return immediately, or the answer has not been delivered to the future yet because it's still running, it's still computing. And in that case, get will suspend and will return only after the value has been delivered. This is very, very nice because it allows us to stop thinking about threads. All we do, we kick off a new operation, and when we need the value, we call get on the future. and it will give us a value whenever it's there. And the current thread is being suspended so that the core can do other things while the current thread is being suspended. So schematically on the left side, this is kind of depicted. You have a future object that is suspended at some point. The second locality is doing the execution of the tasks the future represents. And whenever the value comes back, we resume the original consumer thread and we can continue, which gives us a very nice, transparent way to synchronize with the producer and hides the notion of dealing with threads. That is actually very important. Equally important is that in this context, the future represents a data dependency, because the code that depends on the result will run only after the future has been made ready. If you look at Intel's parallelization efforts, or the efforts to create parallelizing compilers, you will see that Intel is promising us that for 50 years now, and they don't really get everything under control that easily. The reason is that the compiler doesn't know anything about the control flow in the application, and the compiler tries to reconstruct the pieces in the original code that can be run independently. And that is an almost impossible task because, well, the compiler sees only the written code and doesn't understand what the programmer had in mind. So if we have a way to convey the data dependencies to the system, then the system can automatically parallelize things because, well, in order to do something, there are two things have to be finished before. And once these two things are available, then the system can schedule the dependent tasks. So futures are perfect for that. Let's look at an example. So I chose Quicksort because it's computer science 101. Everybody can understand it, everybody knows it, and it fits on a slide. So let's parallelize Quicksort. We assume that we want to sort a sequence of values that are contiguous in memory between first and last. So we are dealing with random iterators here, random access iterators. We certainly want to sort things only if we have more than one element in our sequence. So the easiest way to implement Quicksort is to select a pivot point, which in this case, we select the middle element in our sequence, assign it to P, and then the lambda we pass to partition gives us is a predicate which tells us whether the current value is actually smaller than a pivot point or larger or equal to the pivot point. We use the STL algorithm partition here. Partition is a very nice and powerful algorithm because it reorders the elements in a sequence in a way that everything that's smaller than a given, or everything for every element for which the predicate returns true will become first, and all elements for which the predicate returns false will come after. So the predicate here, in that case, that lambda is being called for all the elements between first and last, and partition reorders the elements. So what we get after partition returns is that all elements that are between first and pivot are smaller than all elements that are between pivot and last. So partition returns the iterator pointing to the actual partition point in the sequence. And all we have to do afterwards is we call Quicksort recursively for the left and the right subpart. Done. So we have a very nice sequential implementation of Quicksort with a couple of lines. Please note that you certainly can use more sophisticated algorithms to decide what pivot point to use. In this case, I just chose the simplest one, so it fits on a slide. Now let's parallelize that. We do the same thing. We have we additionally introduce a threshold to maintain grain size because it doesn't make sense to parallelize things if you want to sort only a couple of elements. So we do the parallelization only if we have more elements than a certain threshold. In the case of if we have too few elements, we just call sort with the sec execution policy, so it will sort sequentially. And otherwise, we call partition with the par execution policy, which will parallelize the partitioning process as explained above. Well, and then we do the quicksort to the left and to the right. You might say, oh, great, done. I have parallelized my quicksort. But the point is that this quicksort is exactly exposing the behavior I showed in my image in the first place and on the first slide, that you have kind of bursty activities whenever partition is executed, but you have these utilization gaps in between. And now let's have a look how we can overcome that. What if we create a quicksort algorithm that actually returns a future? So a quicksort that kicks off the computation and returns essentially immediately. The scheme is the same. If we have more elements or less elements than the threshold, we sort it sequentially. We just do it sequentially. In the end, now remember, we have to return a future. So in this case, we just return a future that is ready to begin with. There's a facility function which is called makeReadyFuture. So that's not very interesting. Now let's have a look at the parallelization part. And here things get a bit more interesting, because I'm using the par task execution policy now, which means that the partition algorithm is launched asynchronously, and it now returns a future that represents the result. Now, the code I will show now is a bit difficult, but please bear with me. I will simplify that significantly on the next slide. Since partition now returns a future, we can't immediately call quicksort on the left and the right subsequences, because the partition has to finish running before we can do the recursion. So what we do, we use the pivot.then function, which is a facility that we have added to the future object that allows us to attach a continuation to the future. That means whenever the future becomes ready, this lambda in this case is called automatically without us having to do anything. And when the lambda is called, we know that the partition operation is finished. So what we do, we call quicksort on the left and on the right subsequences. But remember, quicksort now returns a future. So we have to somehow combine these futures into one future, which is can be done with the when_all facility. And when_all gives you a single future that will become ready when all of the futures it was invoked with have become ready. So it is a means of parallel composition of futures and tie them together into an execution flow. Now let's have a look at what we have actually done. We have turned our initial quicksort function from a function that returns only once it's done into a function that returns essentially immediately and gives you a future representing a data dependency tree, because the return future depends on many futures that one from each recursion essentially. So we have turned the sequential execution into a futurized execution that first creates a tree and then unravels the execution tree in without additional or without unneeded synchronization, which is the important piece here. Now let's simplify that code a bit. And I said in the beginning, I'm very excited about the C++20 features. While the code on the previous slide was very complex and very difficult to write, what we can do now with C++20 that introduces a co-await keyword. And the nice thing about co-await is that you can make it do exactly what I was explaining before. So all we have to do now, we have to co-await for the partition to finish, which gives us the pivot point. And then we do the recursive quicksort to the left and to the right and co-await on the overall future return from when_all. Done. And if you compare that code to the initial sequential code, you will see that there are almost no changes, but we have a fully parallelized code that runs as fast as you can and exposes very nice utilization characteristics. Okay, so I mentioned asynchronous communication in the beginning. Just one slide on how we manage asynchronous communication. We created facilities which we call channels. We have stolen them from Go, from the language. And what they do, You can create a channel on one thread or on one locality. You send it over the wire, and on the other end, you refer to it from another thread. And the channel essentially has two API functions, get and set. And both of them return futures. So the set side returns a future which becomes ready when the channel has accepted your value, and the get end of the channel returns a future which will become ready whenever data has been delivered through the channel. And that allows you to integrate these asynchronous communications between localities or even between threads very nicely with your asynchronous execution flow. Another example. I have to explain a bit more for this example because we are talking about a project that is we've been working on for the last years, which we called Phylanx, a system that allows you to asynchronously execute distributed array processing. So essentially a distributed machine learning framework, allowing to scale out your machine learning problems across clusters. And that's kind of first. There are some attempts in the community to actually create distributed machine learning toolkits, but none are really successful at that so far, from what we can tell. Very quickly, Phylanx tries to solve the problem in machine learning that the main scientists know their topics, but they have trouble getting their things run on high-performance computing resources because we need to make the algorithms distributed, which requires data tiling. The domain scientists usually work in Python, but we want to execute things as fast as we can on a C++ execution engine on a cluster. So our goal was to abstract away the complexities of programming on high-performance computing resources from the domain scientists. And we have done that by integrating Python with a C++ execution engine based on HPX. It's built on top of many parts: HPX, Blaze, linear algebra library, Agave to submit things to the resources, Jupyter notebooks for the front ends. So what we have done there, we have combined the performance of HPC systems with the ease of programming in a higher level language, in Python in this case. So the Python front end abstracts away the complexities of lower level implementations. We integrated with Jupyter notebooks. So we are able to run NumPy code directly in Phylanx. We create distributed task graphs from the Python code and use HPX as the execution engine to execute the task graphs that are created. Let me show some schematic, or let me give you some schematic explanation what we do there. Phylanx builds a system that consists out of three parts: the front end, where you have a normal matrix expression, A and B in this case, a middleware part that uses an internal representation like an abstract syntax tree or MLIR to walk the tree, to optimize it, to do additional things to transform these internal representations. And from that, we create a distributed execution tree that is evaluated using HPX. In practice, that looks like this, for instance. So in Python, we would decorate our function we want to distribute using the @Phylanx decorator. That is transformed into some intermediate representation, which is very similar, has drawn from Scheme. So it's a very functional representation. And that is turned into a HPX execution that uses data flow and other facilities to run the execution tree at full speed. And I will give you a code example later. As I said, that can be run from a Jupyter notebook. You can run it from your interpreter, or you can, if you're really adventurous, you can directly use the C++ API to program it. The middleware is meant to apply various transformations to the internal representation. We want to do optimizations there. We want to automatically decide on how to tile the data and how to distribute the data. And we would like to create a bridge to MLIR here to feed, to use the execution engine with other tools that produce MLIR, that machine learning intermediate representation that is being standardized currently. The goal of those optimizations is to minimize computation and communication between the nodes. And the trick is that this is specific to the expression to be evaluated. So we look at the expression and try to optimize the execution for this particular expression. And we can also store the results of the optimizations, so we don't have to redo that over and over again. The backend, and that's what I want to focus on here, uses adaptive asynchronous execution using HPX, obviously in C++. So if on a single system, on a single node, we have the A minus B expression and it's being evaluated as an execution tree with 3 nodes, the minus node, the nodes that represent A and B. And when evaluated, when you want to evaluate the minus operation, you first evaluate A, then you evaluate B, and deliver the result to the node above. In a distributed system, you deal with tiled data. There we cut the matrices A and B into pieces and put A prime and B prime on one locality and A double prime and B double prime on another locality, and create an execution tree that acts on the parts of the matrices separately. And you can join it afterwards in some way if you want, some reduction operation or whatever. These trees are distributed across the system. So the left tree runs on one node, the right tree runs on the other node, concurrently, obviously. And you obviously, and that's what we have done as well. We have integrated that with Docker or Singularity so that you can submit that not only to clusters, but also to cloud resources from your Jupyter front end. And here's just an example. This is some support we built into the Jupyter notebook. We call that Traveler, where you take some Python code. You can submit that Python code through Agave and Tapiz to a remote resource. You wait for it to be executed, and you get back a link. When you click on that link, you get visualizations of the performance information that was collected while your code was running on the remote node. And here are just a couple of images that depict the various presentation views provided by that system. Very important to look at, or a very important tool, especially in the task-based runtime system arena, because there are no real debugging and performance analysis tools available that allow you to tie the task nature of your execution into the higher level representation of your Python code, or even higher level C++ code. The last figure here shows you the visualization of one of those execution trees, and the colors depict the amount of work that was executed for that particular node. Okay, so let's look at a distributed execution model we have in Phylanx. As I said before, there we had an operation that didn't require communication between the localities because it was an element-wise operation, namely just subtracting one matrix from another. What if we want to do a dot product between two matrices? Well, in that case, things are a bit more complex because besides duplicating the execution tree, we also have to communicate between the nodes in an asynchronous fashion while running these two trees on the two localities concurrently. So the nodes communicate as needed in order to orchestrate the dot product as needed. And we have created quite a list of those primitives. We call those primitives, these things which are in a circle here, to perform a wide variety of operations. And we can essentially translate NumPy code directly to to that execution engine and run it on a cluster. Now let's have a quick look at how that looks from the code standpoint. What I have here is a struct which represents one of those primitives, one of those nodes. And I want to look at the add, quickly show you how the add node is implemented in a very high, on a very high level without too much detail. As you can see, add is derived from a HPX facility, which we call component. And an HPX component is a C++ object you can talk to remotely, and you can create remotely, and you can schedule things to work on remotely. Excuse me. Now, what these primitives expose is essentially a single function, which we have called eval. Eval is being invoked asynchronously and is supposed to return the result of a computation for a particular node, for the add node in this case. The parameters, we can ignore them. At this point, that's additional function arguments that might be needed for other evaluations and not for the add node. But the add itself has a vector as a member that represents the child nodes of that add operation. And in this case, I just assume that I have two children attached to the add node. So once eval is called, once the add operation is to be evaluated, we launch the left and right evaluation, or the evaluation of the left and the right child asynchronously by creating new threads. Those give us a future. And then we use co-await on the left-hand side and on the right-hand side and return the overall result to the node that has invoked the add operation. Again, the code looks very much like the synchronous code you would write if you had to do that in a synchronous fashion. Very straightforward. It enables us to convert synchronous execution into a fully parallelized asynchronous execution without too much effort, thanks to C++20. Okay, another example for that, let's assume we have a CUDA graph we have created from somewhere which represents a subtree in our execution graph. And we can do the same thing. We just evaluate all children. I'm using a special facility function map here. Map concurrently evaluates all elements in the children vector and returns a vector of futures where each future represents the evaluation of one of those children. When all is then used to combine that vector of futures, and we co-await on that single future to get the results of the evaluation. And then we pass these results of the evaluation to some facility function that takes a graph and the arguments and evaluates the CUDA graph on the device. This is just to depict a possible example how things can be, how special accelerators can be integrated in the evaluation of the overall execution graph. So as we have seen, there are many ways to add asynchronous execution to our applications. And to recap, I have introduced a technique we call futurization that allows us to automatically almost automatically transform code by delaying the direct execution in order to avoid synchronization. It turns the straight code we had before into futurized code, which no longer calculates the results, but just generates an execution tree that represents the original algorithm. And if the tree is executed, it produces the same result as the original code was producing. So the execution of the tree is performed with maximum speed because we avoid any unnecessary synchronization, and we can overlap all the computation very nicely because there's a lot of parallelism available in the system. And here we get to the point where that execution kind of exposes an emergent property of almost being auto-parallelized because of the scheduling we use in HPX, which is a commonly known work-stealing scheduler. We can redistribute all the parallelism very nicely on the localities. Some recent results. I showed you that execution graph before. One problem, and as you have seen in the code example I gave you, each of those nodes launches a new thread in order to evaluate its children. And obviously, this can very quickly lead to unnecessary overheads, especially if the children have to perform only very little work. What we have looked at is to introduce some runtime adaptivity here by measuring the execution time for each of the nodes and deciding on that execution time whether to actually launch a new thread when the node is to be evaluated again, or whether we can inline the execution of a certain subtree of the overall tree into the parent thread. And that was very successful because what we have seen is that depending on the problem sizes, we get quite significant speed up if we start inlining tasks based on a adaptive threshold that is used to decide whether to synchronously or asynchronously evaluate a certain subgraph of the tree. This is just an exemplar graph. We have seen these significant improvements across the board, actually regardless of what concrete expression or what concrete algorithm we have tried to evaluate using Phylanx. Another two graphs give you the scaling behavior of Phylanx on a single node. The blue one is the Phylanx execution. The green one is a non-distributed alternating least squares algorithm written in Python using NumPy. As you can see, the Python implementation using NumPy doesn't really scale well, whereas the Phylanx implementation scales very well up to 48 cores. The very same code can be run on a distributed system, in this case up to 64 nodes, each of them using 48 cores. And as you can see, the scaling behavior is very nice as well. And the larger the problem size we are working with, the better the scaling behavior across the board. Again, this is just one example here using a alternating least square algorithm, but we see very similar behavior for other things we have implemented with Phylanx as well. Another example, and that gets me back to the astrophysics application I mentioned in the very beginning, where we wrote an application using HPX, an astrophysics application that combines three different types of physics: hydro, gravity, and radiation transport. And these three models that are kind of combined in the same application and are being evaluated on a adaptive mesh refined using an adaptive mesh refining methods, all have very different time scaling behavior. So combining these three models into one is normally a big challenge because it's very difficult to keep the system really busy running if you do that with conventional means. Just to demonstrate you the adaptive mesh refinement behavior of that application, no surprises there. This video just gives you an example that kind of depicts a couple of time steps of the evaluation. And you see very nicely how the different refinement regions, I hope you can see it over Zoom, how the different refinement regions are coarsening the further away you get from the system, and how the mesh is adapted where the actual physics happens in the center of those two suns. Some scaling results from that application. These results are collected on Daint, PitStaint, which is the largest computer in Europe. It's a GPU machine located at Lugano at the Swiss Supercomputing Center. This graph is a bit difficult to read, so let's focus on the blue lines only. What you see here is 4 strong scaling graphs for this application for 4 different problem sizes. Whenever the scaling of a problem was too small, we switched to a larger problem size and started to do a strong scaling study with a larger problem size. And this graph shows you the scaling behavior of the application from essentially 1 node to almost 5,500 nodes, and the speed up is quite significant. What we have seen that we get a weak scaling efficiency of about 80%, well, 78% from 1 node to 1,000 nodes, and a strong scaling efficiency in this example from 500 nodes to 2,000 nodes of about 68%. Thanks to the futurization techniques I explained before. So what did we get? I started off with this image, and if we look at the same application after some futurization, we see that the utilization of the cores has improved quite nicely. The utilization gaps between the core for the cores are gone because we are able much better to overlap all the ongoing parallel operations in the system. From the standpoint of the integration of different tools, what we would like to go for is to have a uniform API that allows us to handle all kind of parallelism in the system. And I think that the recent events in C++ and the standardization of C++ are very promising that they will deliver exactly that. I'm very eager to wait for the executor, the results of the executor standardization, which are expected to happen in 2023, because those executors will help us to get to exactly that goal. It's an underlying abstraction that will allow us to expose all the parallelism in the system, and I mean all of it, through a uniform API and integrate that well with asynchronous execution, as demonstrated in this talk. So the bottom line of my talk is, please futurize all the things that will help you definitely to speed up the execution of your codes. Thank you so much. So I'm more than happy to take questions and to try to answer those questions if you have any. Thank you.
Great. Thank you very much. Very interesting talk. I have many questions, but I don't know if I should go into my questions first or let the audience speak. I haven't seen a question in the Google Doc, but if someone wants to, well, let me ask a question. In the meanwhile, you can type something in either the Google Doc or the chat channel. A very simple clarification question first. On your slide 23 and 24, where you had the 2 co-awaits, the second co-await for recursive call to the quicksort, can it be skipped? Can we not do that co-await and just pass the future down so that the recursive call waits for it?
Give me a second to get there.
Yep.
That one, yeah?
Yeah. Or if you go to the previous slide, it's the same. Yeah, right.
That one, right? You're asking whether this co-await can go away.
Yeah, that's correct.
Well, you can't, because when all gives you a future, and well, to explain what co-await actually does, that might be in order. Co-await takes the future and attaches the rest of the function as a continuation to that future. So it is a compiler-based transformation of your function, where whatever comes after the co-await expression is attached as a continuation to the operation you're co-awaiting on. It's essentially a .then to the future that is returned from partition. The same is true for the future that is returned from when all. So in this case, it attaches an empty continuation because there isn't anything afterwards. And that's why you're asking, hey, do I need that? Well, you need it in order to compile things, because while the function formally returns a future, the expression returned should be a non-future, which is kind of weird. But the function itself has to return something that is not a future. Do you have an example here? No, I don't.
But I think I understand.
Yeah, and as you see it in the end, right? There's no return statement in the end. So it essentially returns void, which is a non-future, but the compiler pretends that and wraps that into the future that is returned from the function. So it's more of a syntactic requirement that I have to co-await for it because I can't return a future from the function. And the other thing is I have to co-await for the recursive quicksort operations, because when I go up, again, one level up, I have to be done with my recursion before returning. Otherwise, the node higher up will do nonsense, because if the operation in the recursion is not done, you can't continue.
I see. This is maybe some kind of a lazy evaluation type thing that I was thinking about, that you can keep passing the future until you really, really need its value. And at that point, you block for it.
Well, the trick is that co-await is not blocking. As I said, it attaches a continuation and returns immediately. And whenever that future becomes ready, that continuation is triggered later on. So it's really a lazy evaluation, as you say. It's essentially syntactic sugar for what I showed on the previous slide. So this is equivalent code, which is completely semantically equivalent to what the co-await is doing. It's just simplifying the way we write that asynchronous code and significantly, because nobody wants to deal with the .thens and all these continuations explicitly. And co-await is doing that for us by applying compiler transformations to the function the co-await is used in.
Okay. Benson, your question next. Would you want to ask? Otherwise, I'll read it.
Okay, I don't know if you can hear me.
Yes.
I guess I was asking, what's the likelihood of consensus on a distributed memory C++ model that is standardized? So you mentioned that there are a lot of different models that people have tried, but no agreement on maybe some minimal subset that could be standardized.
That's an excellent question. If you have ever attended a standardization meeting, you know that it's more political than anything else. And that's probably not specific to the C++ standardization process that is happening everywhere. So I have no idea what the likelihood of that is. It would require that somebody spearheads it and comes up with an idea. Because standardization is not sitting and discussing ideas. Standardization is assessing proposals. So if somebody has a proposal and proposes it to the committee starts discussing it. But without a proposal, nothing is being discussed. And I haven't seen a proposal for distributed memory, model at this point. On the other end, and that's our experience with HPX, shows that you can get away with the C++ memory model as long as you have certain things in mind when writing your application. Namely, as long as everything is local, you're inside the rules of the C++ memory model. And once you get over the wire, all bets are off anyway, right? So the burden at this point is still on the programmer to make that happen.
So I have a question. It's going to be a little bit longish question, but I really want to know your thoughts on that. So first, let me preface with a couple of things. One is that in Cham++, we stayed with a very, very tame old C++. And part of the reason for that is because early on we had success with NAMD, which was being used on dozens of supercomputers and so on, and some of them would not upgrade their C++ compiler, so we couldn't just do it. So until just a couple years ago, we couldn't even go up to C++ 11.
Yeah.
But now we are unshackled. We feel a little bit freer than that. But leaving that aside, if I had full freedom too, there is a question that arises, and I think this question has to do with, I have seen over my 35 years a variety of C++ based attempts or other attempts at abstraction in parallel programming. And one tension there always is between simplicity and elementariness. I don't know how better to explain it. The best thing I can say is another anecdote, which hopefully some of you will find interesting. In 1985, when I was interviewing for a faculty position, I visited Indiana, where there's a Friedman and Weiss. Friedman was my host there of the Friedman-Weiss scheme and Lisp fame. So we were discussing various things, and he said something interesting. He said, I want to design a programming language for Einstein. If Einstein were to write a program, he should not be shackled by the programming language. His creativity should be matched by what the programming language provides. And the masses, well, that's not what I'm designing it for. So sometimes, now the tension here is that you get a complicated abstraction. Admittedly, some of the complexities in the implementation, you want to make things nicer for the programmer. But sometimes it's not nicer, it is briefer, right? Brief doesn't always mean easy to understand.
Yes.
How do you see that tension between brief and easy to understand abstractions?
That's a question we can talk about for hours, I guess. Well, it really depends on the target audience, right? If your target audience is C++ programmers, like plain HPX, then I think I tend to provide an API that is more explicit than easy to use or simple. As long as the API is consistent and composable, that would be most important for me, to have an API that is rooted on, for instance, on a C++ standard, right? So if somebody has done work in C++, it's not a big deal for them to start using HPX, for instance. So a very consistent, very concise, symmetric, uniform API. That's one of the reasons why we decided to use the HPX Future as a central piece of synchronization everywhere. So whatever task you do, whatever operation you kick off, you always get an HPX Future back, which you then can combine into these execution trees. If your target audience is more of a non-C++, non-HPC related programmer, like the domain scientists in machine learning, right? They know how to use Python and how to use NumPy, and that's it. Then we have to invest much more effort. And then you don't want to expose all that asynchrony directly to the user, because the user really thinks in terms of, hey, I have this array, I want to add those things done. And that's what we have tried to capture with that Phylanx project, where plain Python code is transformed into a synchronous execution without the user even knowing that it's asynchronously being executed. So hiding those complexities behind application-specific frameworks that expose the semantics the domain scientists understand. So it really depends on the target audience in the end and what you want to achieve. If I write a C++ program, I assume that somebody looking at it knows C++, and I don't care. And I'm not afraid to use more complex things. But if I'm writing a Python program, I'm trying to be Pythonic, right? I'm trying to provide APIs that the Python programmer can use.
I see.
Not sure if that answers your question.
No, yeah,
I wouldn't want to implement a programming language for Einstein. Definitely not.
I see. Okay. All right. Well, good. Any other questions?
Here's a question: how do HPX efforts relate to other standardization efforts like SYCL and DPC++?
Yeah.
Michael Wong, the vice president in CodePlay, he is responsible for SYCL. He is very active in the standardization committee. You might have heard of him. SYCL is definitely driving the standardization process based on the use cases SYCL provides. And in that regard, it's very similar to what we try to do with HPX. Those results and those experiences we have collected with HPX are used to drive the standardization or give feedback to existing standardization proposals, right? If somebody comes up and say, hey, I would like to do this, like reflection. Reflection has to be part of C++ standard. And the first thing I told them, hey, can you reflect on the captures of a lambda expression? And they said, no. I said, oh, but I need that in order to do proper serialization in C++. Otherwise, I am not able to send a lambda over the wire, which is one of the limitations today. We can't really do that if the lambda has captures. There's no way to stay in the language and still send a lambda over the wire and deserialize it on the other end. So all we can do, and please understand, LSU is only a small player in the standardization process because the big guys like Google, Apple, Microsoft, and others, IBM, Intel, are much more politically powerful in the standardization than we can be. So all we can do is to provide feedback and say, that's nice, but that breaks this use case. Or that's nice if we added a particular feature to it. And that's what we're trying to do. Does it answer your question, David?
I think there are probably more questions, but in the interest of time, I have myself a couple more questions, but we'll stop here. And if you stick around for lunch, then maybe we'll have a lunch table for you. I meant a virtual room in which you would be there and people can discuss more questions with you. But depending on your time.
Okay, I can.
For now, yep, sorry.
So is 12:15 Eastern time, or is it
Central?
It's Central. 12:15 Central.
12:50 actually.
12:50 Central.
Yeah, it's actually 1 to 2 basically. The next keynote starts at 2, and 1 hour before that, and an additional 10 minutes is the lunch.
Okay, I will try to be there.
All right, excellent.
It's the same link, yeah?
Yep, thank you. I will send Jamin send a reminder again too.
Okay.
All right, thank you.
So much.
Thank you very much. I hand it over to the chair for the next session. Who's that?
Okay, so in the interest of time, let's keep things rolling. So the next speaker is a former PPLer, Jonathan Lifflander, who's now at Sandia National Lab, and he's going to be talking about his new AMT runtime, VT.
Yeah, so this is Jonathan. I've actually asked Phil to take over this presentation because I'm really sick right now and I have a bad cough. So Phil is actually going to do this presentation.
Just want to double check that I have the most recent slides from you, Jonathan. The ones you sent an hour and change ago?
Yeah, those are the most recent.
Yep, just making sure that I present the right stuff. Start video. Sorry if this is a little bit rough. This is a last-minute handoff of this talk. Wrong camera too. There we go. Okay. Share screen. Sorry for the delays here. This was not an anticipated handoff. Okay. Just to confirm, the slide presentation is visible
Yeah, looks good.
and camera and audio are working well.
Yeah, it's working
Go
well.
ahead.
Okay, great. Hi, so I'm Phil Miller. I'm an alum of PPL also. I finished my PhD there in 2016, for those of you who are newer than that, and then worked at CharmWorks through the end of 2017. So today I'll be talking about the design and implementation techniques for an MPI-oriented asynchronous minitasking runtime from the Dharma system. So the team of people currently working on this code base is listed here. There's another, I think, half dozen or so who've previously contributed to the system and moved on to other projects as well. So this is a big team effort with a wide range of contributors from Sandia and contractors from outside the lab as well. So Dharma is a toolkit of libraries to support incremental AMT adoption in production scientific applications. So what that means is that our target audience, kind of riffing off of what Professor Kaiser said a few minutes ago, is particularly the simulation authors, the developers at places like the national labs and universities who have deep familiarity with writing MPI-based code, but recognize some need for an AMT system for reasons of excessive synchronization in their algorithms or load balancing, or from what we found, other motivations can sometimes sneak them into this direction as well. So the core module of the Dharma system is VT, which stands for the Virtual Transport. Excuse me. So this is an MPI-based implementation of an asynchronous runtime system. So we strive for extreme portability here, rather than trying to attach to the lowest level network layers on any given machine. And it's written using C++ 14 only, with some concessions to certain compilers that don't quite accurately implement the standard or have bugs in their implementation, but that are very popular among real machines and real users. So we've preferred to accommodate them rather than to say, no, everyone has to upgrade their compilers. So split out from VT is this checkpoint library, which for those of you familiar with Charm++, is comparable in some ways to POP, but we believe we've made some interesting improvements to it that we'll discuss later in the talk. There's a tiny support library called Detector that we use for checking various type traits in the within the runtime regarding user classes and messages and so forth. There's a load balancing analysis framework, which I won't get into in this talk, but I will discuss in mine later this afternoon. And there's a checkpoint analyzer, which we kind of treat as a sanitizer of sorts for the sort of code that's necessary to make all of this run. So I'll discuss that later in this talk. So here's a quick outline of our talk. We'll start with the motivation for developing our runtime rather than using one that's already in existence. I'll go over particular implementation ideas that have supported development of this runtime system and helped us achieve our goals. And also might just be cool ideas for people here to see and learn about. Talk about some of what we've done with serialization, give some preliminary application results. So first, the motivation for our particular development and for doing this in a fresh environment rather than trying to use something that's already out there. So MPI is kind of the dominant paradigm of distributed memory parallel programming, and it tends to go hand in hand with a single program, multiple data style of implementation. So there is a very deep ecosystem built up around MPI of developers, training materials, courses, experiences. There's implementations of MPI on every supercomputer and cluster platform in existence. That's typically one of the purchasing requirements that vendors have to provide good working MPI on the system, or it's not accepted. There's millions and millions of lines of code of applications and libraries. There's integrations with the execution environment. So all of the srun and bsub and MPI exec and so on that get jobs from the user's scripts to actually running on the big parallel distributed machines. There's lots of development tools for debugging and performance analysis, lots of research literature, and so on. So in our particular development context, the entire suite of applications from Sandia National Labs are developed on top of very large MPI libraries and toolkits, such as Trilinos, which contains solvers and distributed data structures and so on, STK, the Sierra toolkit, which supports unstructured and structured meshes, and a whole lot else. And there's basically no chance that a code base like that is going to be rewritten in much of any fashion. So instead, we've decided that the best approach is to consciously coexist and provide a transitional AMT runtime implementation that can make it straightforward to demonstrate incremental value to developers who adopt it. So to support that incremental adoption, we maximize our attempts at interoperability and embedding. So the expectation is that different parts of an application might all be initially written in MPI, and when AMT adoption comes into the picture, over decomposition or just expression as asynchronous algorithms can happen in small steps, one part of an application at a time. And that then means that there's going to be transitions between MPI execution and AMT execution, or SPMD and AMT execution, possibly many times per time step. And so that implies that any sort of context switch or handoff of control flow between them has to be very inexpensive because we expect it to be very frequent. So for domain developers of particular science or engineering applications, our AMT actually exposes a lot of its basic constructs in an SPMD, often collective form, especially for things that individually are not going to be performance sensitive, but do need to be part of the programming interface. So a lot of initialization and setup kind of code. For simplicity, we just say, yes, you can write that in your traditional SPMD and not think too hard about it being part of an asynchronous distributed algorithm. We've also chosen not to dive into on-node parallelism directly, but instead to coexist with the diversity of on-node techniques, including CUDA, OpenMP, COCOS, and so forth. And we actually have plans for how we can directly integrate our distributed programming model with the asynchrony that some of those on-node techniques can expose. And we also have actually developed a new asynchronous distributed protocol to safely interweave calls to collective-based MPI libraries into AMT execution, which I'll talk about later. And just as a side note, we've actually found that for some applications, the desire to checkpoint their application without intensive application-specific thought process of what data needs to be saved and how to represent it as like an HDF file or a similar application-specific format can actually be a backdoor to introducing the set of libraries in such a toolkit. If you can tell people, yes, just add serializers or puppers for all of your types, and then call this one function from our library, and checkpoints will get written out, and you can restore those and resume execution later. That's a good starting point for telling them, oh, hey, you have these serializers now, so it's really easy to make messages out of these objects, and it's really easy to migrate these objects around to support load balancing. So I'm going to get into some of the execution model and implementation ideas. Just to give a brief overview, the general execution model of VT is very similar to that in Charm++. There are messages in a dedicated structure or class types that get delivered to handler functions, which could either be a general function on a node, or they could be member functions of particular target objects. So one of the implementation challenges in runtime systems like Charm++, and from what we can tell, HPX as well, and as well as lower layers like GasNet or Converse, is that all of the handlers have to be registered in some fashion on every node, and that registration has to be consistent, meaning that the identity of a handler on node 1 has to be the same as the identity on node 7, so that a message saying run handler 22 gets what it's asking for. So one challenge that we've observed is that manual registration of handler functions is sometimes error prone. It sometimes demands big contortions of the programming model in terms of pre-processing. And it's often not exactly cleanly composable across separately developed modules of an application, because the registration logic in each of those modules is going to have to be called in turn from whatever root. And just as an implementation challenge, potential solutions to registration have to deal with function addresses being different across nodes. So you can't just send a function pointer because of address-based layout randomization, or just linking and loading differences from one process to the next. So there are a variety of potential solutions out there. So Charm++ does code generation from an interface file to support registration at startup, but it requires an extra step during compilation and during development to write out those interface files. And it also means that when you're putting together the application, you have to make sure that there's a proper tree of the interfaces between all of the modules to make sure everything gets imported correctly, which can be finicky at times. So another possible approach is to try to match the name or the symbol of some function or method at runtime based on various kinds of introspection. This relies on non-standard features that some C++ implementations might have and others won't, and it can be fragile. With large templates, you might run into symbol size limitations. You could also just run into the symbols being excessively large to deal with at runtime. So in the future, we'd like to see something possibly built on reflection that could ease a lot of this. But for the time being, we've actually developed a way using very nearly standard C++ to do this entirely automatically and statically using some tricks of template instantiation and the defined initialization order of static variables related to them. Just going to check that there's, okay, yeah. So this particular implementation has been found to work across a very wide range of systems that we've targeted. So GNU, C++ going back to 4.9, Clang going back to 3.9, and relatively widely available versions of the Intel and NVIDIA compilers as well, and without any special linker dependencies. You know, we don't require GNU LD versus Gold or LLVM or whatever either. And this technique is compatible with C++ 11. So in this particular piece, we're not relying on any C++ 14 features. As you can see here, we have a message send giving the message type and then the handler argument. And the handler is just defined as some bare function that takes a message as an argument and it has code to execute on it. And we give a destination and the message that's actually going to be passed. And the template behind this send function actually calls into registration machinery that creates a static registry at compile time that during process initialization, before any of the code in main can potentially depend on it, will register each of those handlers that gets referenced anywhere in the program and make sure that there is a unique and mostly deterministic identifier, you know, an index number associated with each one of them. So that registration occurs during what the C++ standard terms dynamic initialization of static variables. At notionally at load time, it can potentially be deferred. But the important point here is that this is entirely composable, that two pieces of code that were developed independently of each other with no consideration can both use message sends referencing their own handlers, and all of the registration will happen automatically without the application even having to call any special initialization or per module registration function itself. So we've found this to be highly stable and simplifies a lot of the implementation and usage by developers. So for details of this implementation, we give some of the implementation code in a paper we have upcoming at the EXA MPI workshop at SC20, or we can point you to where in the VT code base this is implemented. And we potentially will separate this out as a standalone library that could be used by others as well. So the execution or programming model of VT is based on what we call termination detection using epochs. So these can be basically, they represent the closure of all the work generated by a set of initial messages sent during some particular interval. So you can ask, the programmer can say, send one message to the next rank in a ring, and that will pass messages to the ring handler going one by one around all the processes. And this run an epoch rooted call will spin the scheduler and only return after all of the causally related messages in the chain have been processed. On a different note, there's also the run an epoch collective, which the rooted version, we started on rank 0 and only made that call on rank 0 to start the send. In the collective version, we start it from the send, but we capture the full set of messages that way. So it's just slightly different expressions of the structure. So what that's actually doing behind the scenes is it's creating one of these epochs that the runtime system is going to keep track of, activating it, running whatever function was passed in to generate the initial set of messages, deactivating it, telling the runtime system that the initial set of messages has all been generated. And so if the closure of messages that results runs dry, then we're done, and then runs the scheduler until that actually happens. So this is, for those of you familiar with Charm++, kind of a scoped version of quiescence detection, where we can talk about particular sets of messages rather than everything happening in the system all at once. For time, since it looks like this is running kind of long, I'm going to skim over details of this a little bit. But often there's some dependencies that need to be followed based on the work created by any given handler. So we use the chaining of these epochs together to create that structure, but while maintaining asynchrony. So this can be kind of comparable to a chain of futures, but we avoid some of the overheads of tracking the entire execution tree that you would need with futures by just counting up messages within each of these scopes and synchronizing only across the scopes rather than across the individual messages. So, excuse me. So we can make one epoch and add some work, and then following that, we can chain additional work onto it. So we've built the Empire application. We've ported parts of it to run on this execution model using VT. So it's an electromagnetic plasma physics simulator, and it has load imbalances from PIC particle distributions both initially and as their distribution changes over the course of execution. So most of the code in Empire is still implemented in MPI, and we've maintained the ability to have both an MPI and a VT implementation of PIC in Empire that have the same calling code without any awareness of whether it's going to run as MPI or SPMD or asynchronous code on VT. So the agnostic time stepping code makes calls to a front-end implementation that just says take various steps of the execution logic. And in the VT implementation, so in the MPI implementation, these are each SPMD operations that are complete by the time the function returns. In the VT implementation, these are instead functions that send messages to backend objects that are over-decomposed in these chained epochs, and they make sure that the dependencies are satisfied in the order that the various handlers for those messages get processed. So going from there, one of the challenges that we saw in working with closely coupled AMT and SPMD execution is that one often wants to be able to run some MPI library that has collective or communication operations that needs to coordinate across processes. But this might need to be invoked from asynchronous code. So we've developed a protocol that can actually arrange for the runtime system to set up to call a coordinated choice of which MPI-based operation to run at any given time, and have it all start collectively, even in the midst of broader asynchronous execution. So one just example of how this could otherwise be problematic is if you have two handlers foo and bar, and you do asynchronous broadcasts to each of them, but you want each of them to do ultimately call an MPI reduce, you need to make sure that those actually get run in the same order across all of the nodes and meet the application's intentions. So I'm going to skip over the details of this because I'm running long here. But the broad thrust of this is that we've developed a consensus algorithm that can pick out one of however many such calls have been set up by the application code and make sure that ultimately a common chosen application or operation across all processes gets run at the same time, and then execution of asynchronous tasks resumes. So I'm going to give a brief discussion of some of the things we've done with serialization, also to move forward implementation techniques, and this is mostly in the checkpoint library, so it can be shared across any other runtime system as well. So first is our handling of polymorphic objects, so hierarchies of classes that have virtual methods and need different behavior and might contain different members depending on which class is instantiated. So this is a problem that's come up in various settings and it poses challenges. So other existing techniques in PUP and Boost Serialize use explicit registrations of different types with some sort of string or other compile time introspection to come up with a string to register the classes, which is, of course, error prone or implementation dependent. And for templates, this could also be difficult and expensive because those representative strings could especially get very large. And you really want to avoid doing that like on a per instance basis. So we use the same static registration pattern that we discussed earlier for handlers to do the same thing for types in the polymorphic class hierarchy. And this generates unique consistent identifiers of every type across all the ranks in a job. We add one line of declaration to each class involved in the hierarchy. And we do some explicit instantiation to make sure everything gets put together properly. So in the base class, the user just has to declare that this is the root of some hierarchy of classes. You don't have to specify the type name. You don't have to specify a string or an integer identifier or anything like that. You just have to declare it. And then in the derived class, each class has to specify what its parent class is. So what it was derived from. So we have these two classes B and C that both derive from A. So they specify that. And then in the class D that might have a pointer to one of these, it's a pointer to A, the base class, but it instantiates C, one of the derived classes. And we can automatically serialize that and make sure that it will reconstruct an instance of C during unpacking. So the other cool thing we've done with in support of serializers is we've implemented a sanitizer akin to address sanitizer or undefined behavior sanitizer that compilers have. So this is a guardrail against the fact that serializers can be very error prone to maintain and to test, because the mistake of leaving some new member out of a serializer is the same mistake as leaving it out of a unit test. If you don't keep that up, then it can make difficult to find bugs. So reflection in C++ may ease some of this, but it might be many years before we can rely on that in compilers. So our prototype solution is basically a compile time pass that generates instrumentation that gets inserted during serialization. And then you can run either your application or your unit tests. And at runtime, it will report which serializers did or didn't at least look at every member of the classes covered. So I'm going to skip the implementation details because I'm out of time here, but we can talk about this offline. So just one application result here in Empire. We've benchmarked this, the MPI version and the VT version of a so-called B-dot problem, which is a standard diagnostic for plasma codes on 900 nodes, so 1,800 processes. And we got an overall 2.5x speed up for the application as a whole over the 1,600 time steps done here. So the spikes at every 100 steps in the VT implementation are load balancing, and you can see some other spikes that are mostly system noise. This cluster was particularly noisy, and in the MPI implementation, you can see the wildly varying time per time step because of interruptions to the job processes that the asynchronous execution of VT mostly flattens out because nodes aren't going to be as sensitive to the delays from processing on other nodes. So in conclusion, we're working on this AMT runtime VT that provides incremental value to application developers as they adopt it for any given segment of their application. You can modify one piece at a time, keep everything else in MPI, and not have to go through big contortions to get everything working. The serialization in Checkpoint that we've built is a nice standalone piece, and it's a good introduction to the overall toolkit for users, and it's something of a Trojan horse in that it supports adoption of VT down the line. And we're moving this into production applications in use in Empire. So I will stop there and invite any questions.
All right, thanks, Phil. I don't see any questions on the Google Doc just yet. We have time for a couple. Oh, sorry, there's one from Eric. Do you want to go ahead and ask that?
Do you want to take that in the afternoon? It's about load balancing.
Yeah, if it's load balancing focused, here, I'm going to stop sharing the screen for a moment just so that I can see.
Okay, yeah, let's defer that question for now then until the load balancing talk. Does anyone else? We have time for a couple questions if they're relevant here. Those we'll move on. Okay, well then if you think of any, we can just consolidate them into the talk you'll give later today. So let's move on. The next speaker is Laosi Arpila. And he is a collaborator with the Charm Group and has worked on things similar to what we've been working on for a while. He'll be talking today about distributed scheduling algorithms. So I'll turn it over to him.
Hello, can you hear me?
Yeah, sounds good.
Great. So let me see if I can put this in presentation mode for you, if that works like this. So can you see my slides?
Yep, everything's good.
Great. So greetings from France. And today I'm going to talk to you about some of the initial research results of collaboration with a colleague of mine, Joanne Cohen, who I think is also watching this presentation right now. And as said before, my name is Larissa Pila. I'm a research scientist at the National Center for Scientific Research in France and a member of the LRI lab. And I'll follow with this presentation. I'm going to follow a very traditional structure for the presentation, and we'll jump directly into our motivation. And well, the motivation here, I may be preaching to the choir, but the idea is that we have our applications that grow in scale, and they have bigger problems, more complex problems, they have more parallelism, and we have our platforms that are also increasing in size, more cores, maybe more nodes. And with all this increase in parallelism, what we have too is more potential for issues with loading balance. So this is actually really related to maybe the presentations in load balancing later today, but I'm in another continent, so the timing could be bad for me. And the things with loading balance here is they may come from the dynamic behavior of the application. They may come from performance variation of resources, or recovery from failures, or other issues that may appear during the execution. The standard way that we can try to fix loading balance during execution is by doing dynamic load balancing. It works well for several cases, several scenarios. Nevertheless, as we're worrying about scalability here, an issue may come with the overhead of centralizing information for the load balancing decisions, and also the sequential decisions that can be done in an algorithm like that. I mean, hierarchical load balancers can try to help on that, but we're thinking about another way to try to solve this issue is related to distributed load balancing. And this helps us avoid centralized information, and we see distributed load balancing in some ways, for instance, in work stealing in some runtime systems. We've seen papers in the past years related to also work stealing or dynamic load balancers that are distributed. Our work with Vinicius Freitas and other collaborators and colleagues were related to trying to batch tasks together to try to make decisions more quickly and also to keep some locality. Last year, we saw a presentation related to distributed load balancing in this same Charm++ workshop. And there are some other works, let's say, that try to bring something like distributed load balancing to our current and real runtime systems. But as I see it, we don't see many algorithms out there used in practice. And we want to have a vast trove of distributed load balancing algorithms, be it for comparison, be it to try to find something and improve and evolve. So one way that we were thinking about is what about looking for distributed algorithms from like problems that are related to scheduling and load balancing, but are not exactly the same that we see in our systems. For instance, balls and turbines problems, or problems related to game theory, or problems related to consensus. And instead of trying to reinvent the wheel, to see what can be brought from these algorithms and apply them to our high-performance computing scenario. And the main issue here is that when people are working on these distributed algorithms, they're focusing on very abstract models, which are far from the reality that we see for our applications. And they try to use little to no information because that helps them see the bounds or the conversions, improve the conversions of different algorithms in situations that you may not even know how many resources or how many tasks you have around. So these are very abstract, not easy to implement and apply directly. So what we've been trying to do together is trying to bridge this gap between theory and practice on distributed load balancing algorithms. And we've been doing some things together. The one that I'm going to talk to you today in our approach is related to finding ways to adapt and to improve distributed scheduling algorithms that are out there to be used in our real systems. So moving to the approach, what I'm going to show to you today is related to one specific work where we're taking an algorithm from the literature and trying to expand on it. So this algorithm was proposed by Petra Berenbrick and colleagues in the paper called Distributed Selfish Load Balancing. We're going to call this algorithm selfish. And the algorithm, it follows a structure of routes. So we have this M unitary tasks, and we have this N identical resources, and the tasks are spread throughout the resources. What we're going to do in a round is that we're going to take all tasks in parallel, and for each task, we're going to check the load of its current resource and the load of another resource at random. And if this new resource has a load that is lower than our current resource, we're going to try to migrate this task with a certain probability, and the probability is related to the ratio between the loads of these two resources. So the larger the gap in load, the larger the probability that the task is going to migrate. And the algorithm is really interesting because, I mean, it's very simple. It's not using much information at all. And it's supposed to find an epsilon Nash equilibrium in log the number of tasks, which is very, very fast. And it's also supposed to find a perfect balance with high probability in log m plus n to the power of 4. We look at this and we think, well, we can do several things to this algorithm to try to adapt it to our real systems. But as we were thinking about it, we chose to focus on the simplest thing that we could use and do, and to do a first step adapting this algorithm. So the first thing that we do is that we're going to add information related to the average resource load. In our case, it's the number of tasks divided by the number of resources because the tasks are unitary. We use this information to organize the resources in three classic kinds. We have the underloaded resources that are under the average load. We have the average loaded resources that are between the average load and the average load plus an epsilon, for instance, let's say 5%. And we also have the overloaded resources that have a load that is above this limit. And using these three kinds of resources, we can change this algorithm to try to define which resources can try to send tasks, which are our sources, and which resources can try to receive tasks, which are our destinations. And having these three kinds, we can build a simple 3x3 matrix where in each line we have a different rule for the sources, and each column we have a different rule for the destinations. So, for instance, the superior rule for sources mean that only overloaded resources can try to send tasks. The average is average loaded or overloaded, and the inferior is all resources can try to send tasks. On the destination part, the inferior means that only underloaded resources can receive tasks. The average means that average loaded or inferior or underloaded resources can receive tasks, and the superior means that all resources can receive tasks. So if we follow the rules that are for source and destination, inferior, superior, we have the original selfish algorithm, and we can also be the most restrictive and far from this algorithm using the superior inferior rules. So the changes to the algorithm in this case is that we're only going to consider tasks from an overloaded resource. And when we're going to do the comparison between the load of these two resources, we're also going to check if the destination resource is underloaded. And we're only going to do a migration with a certain probability if that's the case. So we have these 9 variations, I mean the 8 variations plus the original algorithm. And then we move to our experimental evaluation phase. And this evaluation is based on a simple simulator that I wrote using Python. I have to update the latest version of this unified scheduling simulator to have this distributed simulators integrated. And we were using simulation because we're trying to understand several of the details of these variations. And it's easier to run more tests because we can require a lot of resources like core hours to do experiments with distributed load balancing algorithms. Just to give you an example, earlier this year, we submitted a paper. We were working with one benchmark and around 1,000 cores, and with the debugging, finding the good parameters for benchmarks, running the experiments and having statistical significant results, we got over 40,000 core hours. So as we grow in scale, this can also grow very quickly. But here we're also focusing on having some easier debugging, and simulation is easier to reproduce and replicate the results because the simulator is deterministic. We're only changing the random number generator seeds to have different samples. We gather 3 metrics. The most important metric for us is the number of rounds for conversions because the algorithm follows rounds. And in this situation, the thing that we would like is to reduce the number of rounds for conversions when compared to the original algorithm, but it may not be the case, right? We're going to evaluate that. Other 2 metrics that are interesting are the number of task migrations, because this relates to how much data has to be moved, and number of load checks, because this relates to the communication between resources to gather information about the load of another resource. Before moving into more details about the experiments, I'll just have to put our hypothesis here that we're trying to test. I'm not going to run through all of the hypotheses right now, and in this presentation, we're only going to cover 3 of them, but they're registered here. And later, if you're watching this on YouTube, you can pause the video here and read all the hypotheses that we have. I'll read some of them later in this presentation. So more details about the simulation. So all tasks are making decisions based on the information that we have available at the start of the round. So at the start of the round, we have the load of a resource, and we have a fixed load for the other resources. All tasks are going to use this same information, and the information is going to be updated for the next round in the simulation. So we don't have to worry about ordering messages and the asynchrony in the simulation. We can just do a sequential simulation that's going to provide always the same results. The simulation stopped if a scheduling algorithm is not able to achieve conversions in 1,000 rounds to limit the time that these simulations can take. And we define conversions here is the situation where no resource has a load that is 5% over the average resource load. So if the average is 100, if everyone has 105 or lower, it's okay. If we have any resource has more, we go for another round. Okay, so about the simulation that I'm going to discuss, we have several numbers of resources. They are not very large here because we're trying to understand the algorithms in this initial research, and then we can expand later. We're changing the average number of tasks per resource between 50 and 100. All tasks are unitary in this experiment. And we have 31 different initial task distributions. So we have one distribution where all tasks start in the same resource, And then we have 10 that follow kind of a normal, kind of exponential, and the CDF of an exponential distribution. Combining all of these scenarios with the 9 schedulers and 10 samples, which means 10 different random number generators SIDs for this each scheduler in each scenario, we have over 20,000 samples that were gathered here. Just to show you what I mean by the distributions. So here we have 3 figures with the examples of initial load distributions for 100 resources and a total of 10,000 tasks. So in the left, we can see follows a normal distribution. It's important to say that in this histogram, each bar is actually the load that we have in 5 resources together. And in the middle, we have our exponential, and in the right, we have the CDF of the exponential, which is kind of like a logarithm curve here. So we see a lot of loading balance in the normal and exponential distribution, and the CDF of the exponential, we see that they're close to the average, which would be around 500 here because we have buckets of 5 resources, but there's also some resources that are severely underloaded. Okay. Having that, we move to our first hypothesis, that when compared to the original selfish algorithm, the addition of the average resource load, it should decrease the number of rounds necessary for convergence. What we have in this table is the mean, the average number of rounds for convergence for all the experiments with each of the 9 variations of the scheduling algorithms. So different numbers of resources, tasks, and distributions. They're all bunched up here in one single number, okay? And in the last row, last column, we see the value of 41 for the original selfish algorithm. And we see that the other values are smaller than that, which would indicate that on average, we're taking less rounds to converge. When we look at the details, we also discovered that there were some cases where the algorithms did not converge in 1,000 rounds, especially for the original selfish algorithm and for one of the other variations. We discount them when computing the average. We see that the average decreased, but not much, and we still see a difference. But the mean of a bunch of values doesn't mean much in the general sense for us. But for instance, if we look for the median number of rounds for convergence, we see that the median number tells us a slightly different story, because if we look at the first column where the destinations are set only to be the underloaded resources, the median number is actually higher than the number that we have for the original selfish algorithm. So in a sense, we see that there's more to be investigated here. We cannot just base everything on mean here. So another way to represent these results is by comparing the variations in the original selfish algorithm in this figure. So what we have here is each line is one of the variations, and the value that we have is related to the value that the average number of rounds that we have for a variation for a given scenario, number of tasks, resources, and original task distribution. And we subtract from this the average number of rounds that we have for selfish. We sort these values for each of the algorithms, and then we plot them here. What we see is that the original selfish algorithm, it's performing very poorly for around 25 cases. Then at this scale, they seem to be kind of similar. And then there are some situations near to the x-axis, near to 250, where other algorithms are performing very poorly. If we zoom in here, what we see is that after those initial cases where the original algorithm performs very poorly, we see this, for instance, this red, blue, and pink lines that are above the others that are performing worse than the original algorithm. And these 3 lines represent variations on the algorithm where only the underloaded resources can be used as destinations. Those are the first column that we had on our table. So this provides us some extra lessons that maybe using only underloaded destinations for this algorithm can be a bad idea. But we also see that there is two lines that are the lower ones, the purple and brown lines, which are selfish average average and selfish average superior, which say to us that using overloaded and average loaded resources as sources can be a good idea. It's not always a good idea. There's a situation where it's not performing that well, but it's just some extra lessons that we took from these initial results. When we go to another hypothesis, the hypothesis 6, where we're thinking about the original task distribution, where we're thinking that the original task distribution, the original mapping before scheduling, it can affect the number of rounds that the algorithm is going to take to converge. So we would expect to see with different task distributions, we would see different numbers of rounds for the different algorithms. What we have here are 3 figures, each figure for one variation of the selfish algorithm. So we have on the left the original, in the middle the average, and on the right the most restrictive variation of the algorithm. And in each figure we have on the y-axis the average number of rounds it takes to converge for that algorithm, and for each column, each bar is a different initial kind of distribution. For instance, exponential covers the 10 different exponential initial distributions for different numbers of resources and numbers of tasks. And we see some interesting results here. For instance, for the original algorithm, we see that the single, where all tasks start in the same resource, is actually converging faster on average than the other ones. And meanwhile, the most restrictive algorithm, the original single mapping is actually providing very, very poor results. And while for average, there's not a large difference between these results. But again, these are averages. They hide a lot of information. If we change our view, instead of using the averages, we're plotting the results using box plots, we can see that for the original algorithm, usually they are very close to a small number of rounds. There are a lot of outliers that go up to 1,000 when the algorithm doesn't converge in time. For the most restrictive situation, we see that the initial task distribution with a single one is providing a large variation of bad results. Meanwhile, for average, we see that in the worst scenario, we were taking up to 20 rounds to converge, which is much, much faster than this other variations. And when we see all the different box plots for the different distributions, they are basically the same without considering the outliers. We have some statistical methods that we have used for the evaluation, but that I'm not going to cover them in this presentation. Finally, the last hypothesis is that the higher the number of resources in a scheduling scenario, the higher the number of rounds that we're going to take to balance the load. And this may be counterintuitive if we think about the complexity of the convergence for an epsilon Nash equilibrium that was only related to the number of tasks. But we would think that by having more resources, it may be harder to find a resource that can receive a task. And this is kind of what we're seeing here. So we have 3 figures for the 3 different algorithms that we had for the previous hypothesis. In this case, we have the average number of rounds in the y-axis, and each of the bars is a different number of resources. And as we see here, in general, as the number of resources grows, also grows the average number of rounds. But there's something hidden here, is that we're having 50 tasks per resource. in these situations. So actually, when we're increasing the number of resources, we're also increasing the number of tasks in our system. But, well, we can see that if we compare for the same algorithm, the same number of tasks, for instance, in this case, 5,000 tasks that are in the left distributed over 100 resources, and on the right distributed among 50 resources, is what we see is that there's still a jump in the average number of rounds that it takes to converge. So there's still a difference here, even when the number of tasks is equal. And what's interesting when we're also comparing these two figures is that we see that the more tasks per resource we have, the faster it is to converge. So it's easier to have a load of 105 tasks or lower with 100 tasks per resource on average, when compared to 50 tasks per resource, where the conversions would require at most 52 tasks. So a lot of having a lot of tasks in these situations is good for conversions. So to conclude this presentation, these were only some of our first steps trying to bridge this gap between theory and practice in distributed load balancing. The hypothesis that we had for these experiments, they seem to hold. But I mean, we're still planning to run on larger experiments with some other hypotheses that come after these first experiments. So we want to run larger scale, for instance, more resources, more tasks, or even less tasks to see how it affects the results. Run experiments with non-unitary tasks, which reflect what we see when we're running a real application in Char++, for instance. Try to add more information and techniques as we see the algorithm converging to a good solution for systems, and then try to implement it in something like Char++ and try to run it in a real HPC system. But first we have to filter the variations. If not, we're going to require all the resources available in the supercomputer to run our experiments. Just before finishing this presentation, I'd just like to have two final remarks. The first one is that I think as a community, we should really get some standard load balancing simulators. And I have some ideas of simulators that are not focused on load balancing, but can be used for that. Today, I learned also about the load balancing analysis framework from Dharma. And if you know of any load balancing simulators, I would love to know more about it. And this should make it easier for us to compare algorithms and results, and it should help us avoid counting on supercomputers all the time. And the second thing is that I think we really need some standard load balancing benchmarks with well-documented parameters. And these well-documented parameters are important because if we change, for instance, the scale we are running a benchmark, it may also change the loading balance that we see there. So having these well-documented parameters should help us be more productive when running these kinds of experiments. I see TaskBench doing some nice work in the right direction, but I don't think that's just a solution for us right now. They're not focused on load balancing. As far as I know, they don't even have persistence load imbalance right now in TaskBench. So I would like to thank you all for coming and seeing my presentation. And if you have any questions, I'll be happy to answer them now, or my email is available for your questions. Thank you.
Thanks for your talk, Laercio. Does anybody have any questions? I don't see any on the Google Doc, but if anyone has anything, they can feel free to ask just now. There was some discussion about complexity in the Zoom comments here, but it seems like that's been answered.
Oh, yes. It's the last option, log m plus n to the fourth power.
I think I would like to endorse your point about needing that simulator. I do think that we probably have done it a couple of times and dropped it a couple of times. So we need to bring it back. But the simplest point to make there is that we can do it because of virtualization, right? The same way we did in Big Sim. You just pretend that you have 10,000 nodes by having 10,000 user level threads running as them and doing the algorithms. As long as that is okay, then I think we can do that algorithm. And in fact, you can even do simulators even simpler than that for some of the algorithms that can just have a sequential program doing the behavior of the distributed algorithm.
Yes.
If you want to be kind of strict about the distributedness of it, you can do it with some user level threads or threaded methods, I think.
Yes, I agree. But we really need something more standard that, let's say, most of the people agree.
Yeah, on that front, Phil here, I'll be talking about the load balancing analysis framework in my talk later today. It doesn't handle task-to-task dependencies like Big Sim would, but it does capture some of the broad synchronization structure between sets of tasks, and maybe that can be a decent basis for this. And it means that you can just do the simulations entirely in a single sequential process using just statistics files.
Yep.
I'm not sure I'll be able to be around later today, but I'm sure to watch the video later if that's the case and contact you.
Yep, great, thank you.
And all the talks will be recorded and available later on, either on the YouTube channel and then later on edited versions somewhere. So.
So let me stop sharing.
Ronak?
That concludes the session. Are we going to take the regular scheduled break now?
Let's do a 5-minute bio break. That seems to be the consensus in Slack here, and continue. So we'll make up at least some of the difference. Well, we'll make most of the difference up that way. Is that okay? All right, 5 minutes. And maybe you can open a couple of rooms if you can. So if there are people who want to just discuss something quick, you can discuss here too. But if you want to just talk about something with Larcio, who's probably who's here for a short time because it's late in France, you could do that. There's a breakout room.
Hi everyone, just a quick check-in to let you know we'll be meeting back together in about another minute or so.
We can see the slides up now.
Oh, sorry, I shouldn't have realized I can just have to type.
Yeah.
Okay.
But you can try moving them back and forth.
Yes.
Just to make sure that works.
1 second.
Advancing. Yep.
Sounds good. Okay. All right. So yeah, just let me know when I should start. And I have 25 minutes.
Yeah.
Yep.
Okay.
Okay, so hi everyone, I'm Zane, and this seems like a good time to start our next session on performance and languages. First, we'll be hearing from Abhinav Patele, former PPLer and computer scientist at Lawrence Livermore, who's now an assistant professor at the University of Maryland, and he'll be giving a talk on Hatchet. So Abhinav, whenever you're ready.
Yep. Hello, everyone. I'm Abhinav. I used to be a computer scientist at Lawrence Livermore until last year. I spent about 8 or 9 years at Livermore, and then last year I moved to the University of Maryland as an assistant professor. And today I'm going to talk about a performance tool that we developed at Livermore, and we're still developing collaboratively with them, which is for performance analysis. It started as a tool that was developed at Livermore, but over time, especially this summer, we had several summer interns from different places contributing to it. It's an open source tool. So we have students from UC Davis, University of Tennessee, Knoxville, and Arizona working on it, and I have some of my students working on it. The tool is called Hatchet, and we look at how we can analyze calling context trees or call graphs using Hatchet. So as we write parallel programs in high performance computing, I'm sure all of you know, understanding performance bottlenecks is critical to optimizing HPC codes. Profiling and tracing tools can help us identify what parts of the code consume the most time. So here are two GUIs, one from HPC Toolkit. This is the HPC-T view that shows gprof data here. And then the other one is trace data in Vampire. And you're looking at how much time do you spend in different functions. Many tools also provide the file and line numbers for different functions. And you can try to trace performance problems to specific parts of the code. Since I'm a PPLer or ex-PPLer, I think I can throw some light banter. So if you're sick and tired of looking at traces from projections, I think this is a good talk to look at. And hopefully I can convince some of you to start looking at some other tools. So one of the main things people want to do when they're looking at performance problems or bottlenecks is they want to attribute performance or time to code. This requires a reasonable understanding of the code structure. So you need to understand where does the control flow start, what functions are called, and what subsequent things get called, and so on. There are many sophisticated profilers that can attribute time to calling contexts. Some examples of measurement tools are HPC Toolkit, and hopefully John will talk about HPC Toolkit in his keynote today. Caliper is a tool that comes out of Lawrence Livermore. Scorpy, Tau, gprof, all of these are tools that you can use for looking at performance profiles. When we started working on Hatchet, one thing we noticed was that there was a limitation in the current analysis portions of these tools. One, they only support their own unique formats, and also they have limited support for saving or automating the analysis. So once you do an analysis for one data set, if you wanted to do a similar analysis on another data set, you have to load it back, follow the same steps again, and do it. Most tools only support viewing one data set at a time. So if you have to compare two timelines, you have to pull up two projections or two HPC viewers and then look at them side by side. Finally, most of these tools do not have any programmatic way of analyzing the data. So there's no way to write small programs or scripts to read the data in and do some analysis. And that also boils down to having a lack of capabilities to sub-select and focus on specific parts. And that's where the idea of Hatchet was born. But before we go into that, let me just give some definitions of the kinds of data that the Hatchet tool focuses on. So we focus on data that's a hierarchical context. So for example, calling context trees is one example. Calling context trees represent different call sites in your program, and all the functions that the control flow had to go through to get to those leaf nodes. So for example, we see here that program execution starts in foo calls some other functions and so on. And finally, you reach those leaf nodes that are Baz and Grolt and so on. Now, each of those, let me see if there's an animation here. Yeah. So each of these paths from the root to a specific leaf node is called a call path. And that gives you a calling context for where was that call site called. Different profilers will store different amount of information on each node. So you might have the file and line number, function name, call path. You might have load modules, the process ID, thread ID, and so on. Typically, tools will also have performance metrics. So you would have the most common one is time. So many tools will store the inclusive time and exclusive time for each node. You might also have other metrics if you enable, let's say, PAPI, and you have number of flops or cache misses, etc. Now, you can go from a calling context tree to a call graph by merging all the nodes that have the same name. So for example, in this case, we see here that the node in maroon, that's Garply, is called multiple times. So if you merge those nodes into a single node, you now get a graph where a node might have multiple parents depending on what functions we're calling it. Hatchet handles both of these kinds of data. We do not handle traces currently, although that's something we are considering. If there are traces that have hierarchical calling context, but currently we only handle performance profiles where the data has been aggregated over the entire execution. So this is where, like, looking at the shortcomings we found in the analysis tools in HPC, that's where the idea of Hatchet was born. We wanted to create a Python-based library that enables users to do programmatic analysis. The main idea in Hatchet is to have an in-memory representation of your call graph or calling context tree. The other key idea is we leverage this Python library called Pandas, which supports multi-dimensional tables. The novel thing we have done in Hatchet is we connect the graph to the pandas by using the nodes in the graph to index into the data frame. So we use a structured index that's the graph, and that's used to index individual rows in the data frame. And then once we had this central data structure in Hatchet, we added a set of operators that we think are common operations people do on or people might want to do on performance profiles. So we add functions to filter and prune the tree and aggregate profile data in various ways. We have also added operators that help you compare data sets from multiple executions. Please feel free to ask questions in the middle, or raise your hands, or add comments in the chat, and I can answer them as I go. So just a quick intro to what Pandas is. Pandas is an open source Python library. It has a main data structure called a data frame. This is a two-dimensional tabular data structure. It supports many operations borrowed from SQL databases. In the data frame, there are rows that are used to store different entries in the data frame, and columns might store different values for each row element. By default, each data frame has an index. You can also have multi-indexes in data frames, and we use that because each node might be collecting data for multiple MPI processes, and for each MPI process, there might be multiple threads. So we use a multiple index to store data in a hierarchical format for each node, MPI process, and thread ID. Okay, so what's the main data structure in Hatchet? It's a graph. This is an in-memory graph where we read in the data from our input data file, which might be from HPC Toolkit or Caliper. Each node is assigned a unique key, which enables using these nodes as index in the data frame. Each node also has a frame that describes the code it represents. So some profilers might have complicated or might have complex node types, where a node can be a function, or it can be a loop, or it can be a statement node. So we store that information in a frame, and the frames don't have a rigid schema, so you can change what you store in the frame. The nodes define the structure and connectivity of the graph. So a parent might have multiple children, a child might have multiple parents, and it defines the caller-callee relationships between the nodes. And then we connect the node to a data frame. So the central data structure in Hatchet, which we call a graph frame, has two parts. It has a structured index graph object, and then it has a pandas data frame. As I said, the graph stores the caller-callee relationships, and then the data frame stores all the numerical and categorical data. So this is what the graph might look like. And then for each node in the graph, let's say we have main as a node, that particular node will point to a particular row in the data frame. And on that node in the data frame, we store all the both non-numeric or categorical and numeric features. So you might have time, inclusive time, the name of the node, file and line number, and so on. Okay. Now, when there are metrics per MPI process, each node has multiple rows in the data frame. So for example, if you have two ranks that you are running your program on, then as you can see here, now instead of having a single index, which is just the node, we have a multi-index that's node comma rank. If you also have threads, it will be node comma rank comma thread. And then for each node, so program root here has two MPI ranks, 0 and 1, and different data, especially in terms of the numeric metrics, different data might be stored for each MPI process. Typically, the file and line numbers and modules for these SPMD programs are all same. They're all same for these same MPI ranks or different MPI ranks. Now we have immutable semantics for graph nodes. So anytime, since we are using the graph nodes to index into the data frame, any operation that modifies these graph nodes in place creates a new graph frame, so that we don't index incorrectly into the data frame. And we implement this using copy and write semantics. So every time you want to write to the same graph, we make a copy of it and then write to it. So any operations that would do something like that follow these semantics. So let's now talk about how do we use Hatchet. So the first thing is it's a Python code. You can install Hatchet by either doing a git clone of that repo and running install. There's a script for installing Hatchet, or you can use pip and just say pip install Hatchet. Once you have Hatchet installed, you can import Hatchet in your regular Python script or in a Jupyter notebook. If you have a directory with the HPC Toolkit database, you can use the from. These are static methods defined in the graph frame. So you can use from HPC Toolkit or from Caliper, from call grind. We support many tools by now, so you can use any one of them and then import data. So yeah, here are two examples for HPC Toolkit and Caliper. If there is a data set that we do not have a reader for. The Hatchet is open source, so we encourage people to contribute readers, and we are happy to help you. It's very simple to write a reader. We just need to organize the input data in terms of a graph and a data frame. So it's fairly straightforward to write a reader and then start using Hatchet. Okay, so once we are able to load data into Hatchet, what are the various operations that that a user can do? So we provide a filter operation. So for example, if you're interested in looking at, in my graph, what are the top functions where I spend most of my time in? So let's say this is your original data frame, and I can apply a filter to it saying, I want to filter by the time column and only look at nodes where I spend more than 10 seconds. So this is how you would specify it. That's the code at the top, single line. And then you get a reduced data frame or a smaller data frame that only has those nodes that match your filter. Now, once you filter a data frame, you have a smaller set of rows. Your graph still looks like it has all the nodes. So we also provide, maybe I'll go to the squash operation first. So we also provide a corresponding squash operation, which goes with filter. So once you've filtered the node and you have a reduced set of data frames, we probably want to remove those nodes in gray that are still in the graph. So that's what the next operation does, which we call squash. It takes the original graph that you had and compares that with the filtered data frame and removes any nodes that are not in the data frame anymore. So basically, it takes children whose parents have been filtered out and connects them to the nearest ancestor. Okay, let me come back to this operation. Now, since most people are running codes that are running on multiple processes, and all of these tools will collect data per MPI process, we also allow you to drop the data per process. So you can use drop index levels, which is saying drop the second index or the third index if it's rank or thread. And you can specify a function you want to use for dropping the rank index or the thread index. So you can say, I just want to keep the max time. What is the max time each rank spends in a particular node? Or you can say, I want to look at the average time spent in each node. So you can use these NumPy functions for doing it. So let's say this is your data frame where you have data for 4 processes. You can use drop index levels, and then you only have a single index after that, which is the node. And then your time data is just once per node. That is an average or max, depending on the user supplied function. Okay, now these were some operations that you could do in a single data set or a single graph frame. There are many more operations that are in the manual, so you can look at the Hatchet, read the docs to take a look at that. But now I'm going to start talking about operations you can do if you have 2 different data sets. So let's say I have 2 HPC Toolkit or Calibre data sets that I read into those 2 graph frames, GF1 and GF2. And I want to look at what is the difference of time I spend in the different nodes when I do these 2 different executions. Now, there are many cases when people do different executions. You might be trying to compare, for example, in NAMD, if I run APO-A1 versus STMV, what is the performance difference? You might be trying to scale your application on different number of nodes and trying to compare, as I scale up, how much time do I spend in different functions or call sites? And the subtract operation can can help you look at those things. So here's a toy example. Let's say you have a left graph and a right graph, and you spend different times in those graphs, although the color scales look somewhat similar here, but you'll notice that the PSM2 nodes at the bottom are different in the color or in the color and correspondingly the time spent in them. Once you do a subtract operation, the Hatchet does a pairwise subtraction of all the nodes matching the unique calling context and tells you what is the difference of time across those 2 executions. Now, if the graphs are structurally different, we first unify the graphs so that they look structurally the same, and that requires some operations of unifying the graph, matching up the data frames. But once we do that, we can use a subtract on the corresponding data frames. And then for the unified graph, which is on the right side, you can see that if I subtract those 2, I spend a lot of time in PSM2 and MPI in terms of the difference. So maybe I want to focus on those as I scale up and see where my performance bottlenecks are. So what I was hoping to do, but I didn't get enough time to work on this, was see if I can show something for a charm example. And I don't have a very interesting case, but I can at least show that things work for charm. So what I did was I took Jacobi 3D from tests under charm, I ran that with 1 VP or 1 char per PE and 8 chars per PE. And let me show you what the script looks like for doing this. So basically, I ran HPC Toolkit on those two things. These are the two directories that hold the data that HPC Toolkit writes out in the database directories. I load them in from HPC Toolkit to GF1 and GF2. I drop the index levels since I was running on multiple processes. Once I drop the index levels, I do a subtract. The filter was not working for some reason. There's probably a bug in Hatchet. But once you do a filter, you can print the graph in the data frame and look at where am I spending my time. So the output here is showing once I do a diff, and this is a terminal output, but we also support many other file formats for looking at the output. You can see the numbers displayed here are the difference in time between those two executions. So I can see that in this function, I spend a lot of time. So red is high, green is low, yellow is somewhere in the middle. For the red or green arrows tell you that those nodes only exist in one of the trees. So the red arrows pointing to the left say that those nodes were only in the left tree. The green arrows tell me that those nodes were only in the right tree. So I can see that these MPI operations were not in the left one for some reason. And so the other thing that Hatchet is useful for, or generally profilers are useful for, are if you're not aware, if you're not familiar with the code and you want to figure out what the control flow looks like, it's a good way to figure out what calls what. And since Charm is complex, this is a good way to figure out where you start with user code and what are the other things you call as you go through the execution. So this is a simple example where you can take a look at, what are the nodes where I spend time in when I run with different virtualization scenarios. Okay. We provide other algebraic operations. So you can do an add over graph frames. You can do a multiply. You can do a divide if you want to calculate speed up between a run that's running on more processes versus less processes. And you can change the visualization and look at what the result looks like. Also, Hatchet is not a visualization tool. So the ideal thing when you have a large graph is to look at the data frame. So let's say you wanted to look at what nodes do I spend most of my time in. I would probably just print the data frame sorted by time and look at, okay, these are the top nodes where the difference in time was the highest. Yeah, so I already talked about visualization. These are some graph formats we support. We can do terminal output or std out. We can do dot format outputs. We can output to flame graphs. And then recently, we have also added an output for Jupyter notebooks. Now, in the remaining time, I'll try to go over some analysis or sample analysis that we have done using Hatchet that gives you an idea of what are the various kinds of things you can do, which would have required a lot of time staring at a GUI, or it would have required a lot of scripting to do if you were trying to analyze this data yourself. So there's a question from Niels about, can you sort my inclusive and exclusive time? So I'm assuming you're asking about sorting by one of those columns, sorting all the nodes by one of those columns. And yes, you can do that. I mean, some of those operations, so since we use pandas and data frames, you actually have access to the data frame. So any operations that you can do in the pandas API, you can do on the data frame. There are some things that we discourage people from doing that would modify the data frame, because then it breaks the mapping between the graph and the data frame. Of course, you can do them, but then some operations would no longer work once you break that mapping. Okay, so let's say you wanted to look at a gprof type flat profile. So you have a full graph with a calling context, and you wanted to see, I just want to look at what are the top functions in which I spend my time. So you can use the group by operation in pandas. This groups all the rows in pandas by a certain column. So if I use name, it will group all the functions that have the same name and create a single row or single group for them that you can later reduce to a single row, and you can provide the reduction operations. In this case, we're using sums. This will tell you the sums of times I spend in each function by name. And then you can output this. So you can print the data frame. You can sort it by time. Maybe that was the question. So you can sort by inclusive time or exclusive time, and then look at what are the top functions in which I spend my time. If you wanted to identify load imbalance in a given execution, so if you have data for all MPI ranks, You can use drop index levels twice. So you can say, I want to drop my second column in the multi-index, that's rank. Once I drop it by getting the average across all MPA ranks or processes, and then once I drop the columns by getting a max across all those processes. And then I can do a max by mean to look at the imbalance. And again, I can print the data frame or the resulting data frame with the imbalance column. So you can see those are the functions, and this is Lulesh, I think, where I see maximum imbalance across 512 processes. You can also compare two executions. So we have already talked about this. So I'll skip this. You can do a diff or subtract to look at the executions. You can also filter by library. And in fact, recently we have added a complex way to filter by call path patterns. So what I'm showing here is a simple filter where you can say, I want to only look at the functions that start with MPI. So this filters your graphs by functions that start with MPI, and then you can compare those two graphs. Recently, we've also added a functionality to specify call path patterns. So you can say, I want to filter the graph by foo calls bar or MPI calls PSM2, and only look at call paths that match my user filter. So you can use those and filter the graphs in various ways to look at a reduced set of examples. And then finally, I want to talk about one study which can be hopefully done easier than what I did long time ago. So when I was still at PPL in 08, we had this NAMD paper looking at analyzing its performance, optimizing performance and analyzing performance. We looked at trace mode summary logs, which is one of the features in the projections library, to output some high-level summary of time you spent in different functions. These plots were created from those logs. It required a lot of scripting, many developer hours were spent on looking at, if I run NAMD on 1 through 4096 processes or processors, where does my time go up? Where do I spend most of my time? With Hatchet, you can use a few lines of code. So this is showing using the Lulesh dataset that we have running from 1 through 512 cores. You can run a for loop on those datasets, do some simple operations. Then we use a pivot to change how we want to display the data. And you can use, this is about 10 lines of code built on top of Hatchet, and you can print a graph like this. So on the x-axis, it shows the number of processes that I'm running Lulesh on, and the y-axis shows the time spent in different functions. So with a very few lines of code, you can do complex analysis that would have taken many, many lines of code in a tool previously. Okay, so in summary, Hatchet is a tool. It's an open source tool based on Python. It leverages the power of pandas to do performance analysis in HPC codes. And actually, you can use this for Python codes. We also now support various Python profiling tools like cProfile. We are adding a reader for PyInstrument. So you can also use it for looking at Charm for Pi performance. We use a graph to index into a data frame, and that helps us do programmatic analysis on hierarchical data. Let's say, yeah, this says that the implementing a query language is in the future, but it's already implemented now. So if you use the developed version on GitHub, you can get our bleeding edge version. And so there's the link to the GitHub repo and also the link to the docs. So I'll stop here. Thank you. And I can take any questions.
Great, thank you, Abhinav. I don't see any questions in the chat or in the Google Doc, but if anybody has any last-minute questions, please go ahead and speak up.
Thanks, Niels.
All right, well, then we'll move on to our next talk, which is going to be given by Jamin Choi here at PPL. He's going to be talking about achieving computation communication overlap with over decomposition on GPU systems. So Jamin, whenever you're ready, you can go ahead and start.
Yeah, thank you for the introduction, Zane. So let me set this up. All right, hello everyone. Welcome to my talk. So my name is Jamin Choi, I'm a PhD candidate in computer science here at UIUC. And today's talk, I'll talk about how we can improve the performance of applications on GPU systems by applying over-decomposition to achieve computation-communication overlap. So as many of you probably know already, there's an increasing gap between the single node performance and the internode communication bandwidth on modern supercomputers, especially with the single node performance outpacing the internode communication performance. So I believe this can be tackled from at least two different directions. The first of which is where we can improve the communication performance itself with optimizations in the software and also better utilization of the hardware support. And this includes things like GPU Direct, Sharp for collective communication, and hardware tag matching. And secondly, we can try to reduce the impact of communication on the overall performance using techniques such as computation-communication overlap. And this will be the focus of today's talk. So there are many ways in achieving computation-communication overlap. MPI can do this by using the non-blocking communication primitives and placing independent computation while the communication is going in the background. Over-decomposition is another method we can use to achieve computation-communication overlap. So with over-decomposition, so basically what it does is you can overlap the computation of one subdomain with communication of another subdomain. So for example, let's say we are trying to run a very simple 2D particle simulation on 4 CPU cores. So with MPI, what you would generally do is you decompose the problem domain into 4 subdomains and map each subdomain to a single MPI process. But with over-decomposition, you can decompose the problem domain into however many subdomains you like. So in the example, you can see in the diagram here, we decompose it into 16 subdomains or 16 chars. And then the runtime system, the Chum++ runtime system, will map these 16 chars to the 4 CPU cores. So these chars can, of course, can communicate via messages with each other. And these messages contain data that's necessary for computation. And they also can initiate computation on the receiver chars. And these chars are mapped to the PEs, or processing elements, which is generally a CPU core in Chum++. And there is a scheduler and a message queue that is associated to with each PE. And the scheduler continuously looks at the message queue to check for incoming messages and executes the next message in the queue, which is the entry method, designated entry method of the target char. So this process is asynchronous message-driven execution in Chum++. So how does GPU execution come into this picture? So generally, a Chum++ programmer can write code inside the chars method to offload work to the GPU. But the problem is how to detect when the offloaded work completes. So the simplest method is to just use synchronization calls. So for CUDA, for example, assuming NVIDIA GPUs, you can use CUDA stream synchronize, which makes the PE wait and block until the GPU work that was included in the specified CUDA stream complete. But this is not great for achieving computation-communication overlap with over-decomposition, because this prevents the PE from, or the scheduler from, executing work of other chars that are waiting in the queue, and also progressing communication in the case without communication threads. So what we really want is the process that's depicted in the diagrams here. So first, a char can asynchronously offload work to the GPU, which is relatively easy. You can do asynchronous kernel launches and data transfers using the regular CUDA API calls, for example. And then once the char offloads work, we want that char to actually relieve control or move aside so that the scheduler can perform work for other chars and also progress communication. So that's the second step, where the scheduler progresses communication and executes entry method of the next char in the message queue. And the important thing is when the runtime has to know when the GPU work completes, so that it can enqueue a new message in the message queue asynchronously. So this means that after the purple char, which is the second char that was in the queue, finishes executing, the target of the message that was enqueued by the runtime, which is the message D in this case. For example, in this case, it will execute another entry method of the original char that offloaded work to the GPU. So that's step 3 here. So this allows communication overlap when we have over decomposition. So as we've just looked at, so we want to support such asynchronous progress or detection of GPU work in the runtime. So we want to avoid synchronization CUDA API calls. And some of you may ask, why can't we just use the asynchronous versions of the CUDA API calls, such as CUDA callback or CUDA events, to determine if the GPU work is complete? But this isn't feasible in Tran++, first of all, because of the scheduler-driven execution. And second of all, when you want to use the CUDA callback function, a feature in CUDA, the CUDA generated thread is dissociated from the Tran++ runtime. Excuse me. So the API that we provide, the runtime provides, is called happy add callback, which allows the user to schedule a Tran++ callback along with a CUDA stream. And this means the Tran++ callback object will be invoked when all the GPU operations in the specified CUDA stream complete. And we currently have 2 different compile time configurable mechanisms, which are based on CUDA callback and CUDA events. And the CUDA events one is the default. And you can also find more details about this inside the Tran++ documentation. So another important consideration that we have to think about when we want to achieve communication overlap is we need to prioritize the communication-related GPU operations in the application. So the most straightforward way of using CUDA streams in Tran++ is you just associate one CUDA stream to each char. And this allows all the GPU operations that are enqueued to the same stream to execute in order. So it's very simple to implement. But the problem with this approach is that it will cause delays in the communication-related operations, such as host-device or device-to-host data transfers, as well as some kernels that are related to communication, such as packing and unpacking. And this is because since many chars are maybe using the same GPU, and so many CUDA streams can be mapped to the same GPU. Some computational kernels that were offloaded by other chars on other CUDA streams may be executing when another char needs to execute the communication-related operations inside its CUDA stream. So what we need to separate the CUDA streams for compute and communication, and also with a higher priority set for the communication stream. So this works for many applications, but you may actually need a more complex design of using CUDA streams and associating them with chars, as we had to do for MiniMD, which is one of the applications proxy apps that we looked at, which is described in the ESPM2 paper. So these 2 diagrams or figures show the execution timelines of Jacobi 2D, which is a very simple proxy application that performs the Jacobi iteration on a 2D grid, with 4 chars mapped to a single PE that is using a single GPU. So on the left, we have the timeline of 4 different CUDA streams, so 4 different chars, and a single CUDA stream per char. So as you can see in the diagram, there are some delays in the communication-related operations. In this case, the device-to-host transfers and the packing kernels. And this eventually causes idle times between iterations, because some chars are waiting for data to arrive from its neighbors because of the delay in communication. On the right side, we have implemented separate compute and communication CUDA streams per char. So now we have 2 different CUDA streams per char, with the communication stream given the higher priority. And as you can see, this allows, this prevents the delay in communication, and thus we do not see any idle time between iterations. In this specific case, we have we see that the communication is completely hidden behind the computation. So to evaluate the performance impact of our approach, of applying over decomposition and achieving computation overlap to improve application performance. We use the following two leadership class systems. One is Summit at Oak Ridge National Laboratory, which has 6 GPUs per node, and Lassen at Lawrence Livermore National Lab, which has 4 GPUs per node, and using the PEMI LRTS and SMP version of Tran++. And here we also just use one process, which has 1 PE and 1 CPU core per GPU. So for example, on Summit, we use 6 PEs mapped to 6 GPUs per compute node. So just a brief introduction of the benchmarks that we use. So we're looking at some iterative proxy applications. The first of which is Jacobi 3D, which performs the Jacobi iteration on a 3D grid, which is over-decomposed into chars. And this performs near neighbor exchange of the halo data, where each char is exchanging its data with up to 6 neighbors. And MiniMD is the second one, which is a proxy app for the LAMMPS molecular dynamics code. So this was converted from MPI Cocos to Tran++ Cocos to enable over-decomposition. And it should be noted that the CUDA-aware MPI in the original code was converted to use explicit host device transfers as well as host messages, because Tran++ does not currently have production level support for direct GPU to GPU transfers. I'll talk about that at the end of my presentation a little bit. And Cocos is retained as the performance portability layer, which is responsible for the computational kernels, as well as the intra-process data movement. So MiniMD performs neighbor exchanges of the atoms, and also performs the Lennard-Jones force calculation. So let's start by looking at the performance results of Jacobi 3D on a single node of Summit on the 6 GPUs that it has. So this plot compares the 3 different implementations. So this all the 3 different implementations use the separate compute and communication streams, as we just talked about. But the difference is the runtime support. So the blue line directly uses CUDA stream synchronize, which is a synchronization CUDA API call, instead of using the runtime support. Whereas the red and the orange lines use Happy, which is the short for hybrid API, and the support for GPUs inside the Tran++ runtime. And we are varying the over-decomposition factor, which is basically the degree of over-decomposition. So with a ODF of 1, it's just basically an MPI-like decomposition where we just have where we have 6 chars on 6 Ps, for example. And as we go higher, for example, to an ODF of 16, we have 16 chars per PE. So we are reducing the granularity of each work unit or char. And as you can see, the Happy versions, the ones with the Tran++ runtime support, perform much better than the CUDA API one. And also, the over-decomposition factor of 4 performs the best compared to the original ODF factor of 1, and up to about 50% of performance improvement. So that's the single node performance of Jacobi 3D. And let's move to some scaling performance. So the weak scaling performance plots are on the top, and the strong scaling performance plots are on the bottom. And the top 2 plots are, and the left plots are for Summit, and the right plots are for Lassen. So let's start with the weak scaling plots. So ODF1 is the baseline where we do not do any over-decomposition, which is the green line. And then ODF2 and 4 performs the best for weak scaling. For small scale, ODF4 performs the best. And after a certain point, ODF2 starts to perform better. So we're still investigating as to why this crossover is happening between ODF2 and ODF4. We have observed that the idle times between iterations are continuously increasing in the case of ODF4 at large node counts. And for strong scaling, we see that ODF2 is performing the best over the composition factor of 2 at most configurations, up until about 3K GPUs on Summit, where ODF1 catches up and performs the best. So this is somewhat expected because over decomposition is trying to make the work units even smaller where the strong scaling is also making the work unit smaller. So we expect the effect of the performance improvement from over decomposition to kind of degrade as we go into the tail end of strong scaling. So let's move to MiniMD, the second proxy application. So MiniMD plots also have the MPI baselines, but the MPI ones are mostly for reference because the communication pattern in the MPI version and the CHAN++ versions are slightly different. The MPI versions perform a set of MPI send-receive calls for each neighbor exchange, whereas the CHAN++ versions do a complete non-blocking exchange for all the different neighbors at the same time. So this change was made to allow more room for computation overlap in exchange of more memory usage. And the two different MPI lines, the black line is MPI HS, which is the version that was changed to move the GPU data through the host. And the MPI CA is the original CUDA-aware MPI version, where the data, the neighbor data, the halo data is exchanged between processes directly between GPUs. And if we first look at the weak scaling plots, the top two plots, we can see that the CHAN++ versions with the over-decomposition factor of 4 performs the best across most configurations, except for a single node on Summit. So it even beats the MPI, the CUDA-aware MPI versions, although the CHAN++ versions are not using the direct GPU to GPU transfers. But this is possible because of the overlap of communication, improving performance. So if you look at the strong scaling plots, it's a similar story to Jacobi 3D. Although ODF4 is the best performing one at small scale, and then which is caught up by ODF2 and then eventually ODF1. Again, because over decomposition is making the work units smaller. So to conclude, so we've seen up to about 50% and 47% improvement in overall performance by using over decomposition to achieve communication overlap using two different proxy applications, Jacobi 3D and MiniMD. So the contribution of this work is that we demonstrated that with careful design of the application to prioritize the communication and also support for asynchronous progress of the GPU work inside the runtime system, we're able to effectively achieve communication overlap, which significantly improves performance, especially in weak scaling scenarios. So as future work, we are also trying to tackle the first direction that we just talked about in the introduction, where we are trying to improve the performance of communication itself by using GPU messaging, which essentially allows direct transfers between GPUs. So let me briefly talk about the GPU messaging that's coming up in the next release of CHAN++ 6.11. So this will allow direct transfers between GPUs using technologies such as GPU Direct and CUDA IPC, bypassing host memory. So currently we're supporting inter-node messages within the same node. And we're also actively working on support for inter-node communication. So we currently have two different APIs. One is the regular API, which is basically for point-to-point messages between chars that want to exchange GPU data. And this is currently experimental in the 6.11 beta because we're undergoing some performance optimizations. And I'll show you the performance in the next slide. So the uses of this is similar to the zero-copy post-entry method API, where the sender char sends some metadata to the receiver, and then the receiver performs a get operation to move the GPU data from the sender to the receiver. So some more details can be found in the documentation here. And the second API is the persistent API. So this will be used for persistent point-to-point messages between chars, which have reuse of the same set of GPU buffers between iterations. So this will be particularly useful for iterative applications. And this will also be part of 6.11, and it's currently on a branch right now, but it will be merged for the second beta. So let's move to the performance plots for this GPU messaging feature. So this is using the OSU latency benchmark, the MPI CUDA-aware MPI version, and also the CHAN++ converted ones, running this on a single node of Summit. So the plot on the left is the inter-process benchmark, whereas the plot on the right is the intra process within the same process. And that's why we have the MPI line only on the left plot. So the MPI plot, the CUDA MPI plot is in the black line here on the left. This compares against the Charm++ versions. So Charm H is the version where the existing version where you have to move the GPU data to the host and then do a host-host message and then do another hosted device transfer at the receiving end. And Charm D is the regular GPU messaging API we just talked about. That is kind of similar to the zero copy API. And as you can see, it currently performs worse at small message sizes up to 8 kilobytes, and then starts to perform better at larger message sizes in terms of latency. And Charm P is the persistent GPU messaging API. So this performs much better than all the Charm++ versions and the MPI version. You still have to, of course, compare this to the MPI persistent messaging, which MPI has. But yeah, it's currently performing relatively well. On the right side, again, the Charm P, the persistent version, performs much better than the Charm D and Charm H versions. Yeah, so this concludes my presentation. Thank you for listening, and please let me know if you have any questions.
Thanks, Jamin. So far, no questions in the Zoom chat or in the Google Doc, but if anybody has any last-minute questions, feel free to speak up or just type it and we'll get to it.
So it looks like Forrest has a question.
Yeah, can you hear me?
Yeah, we can hear you.
Yeah, I had a question. What was the percentage of time that you're, let's see, do you have a good handle on what the percentage of time of kernel launch overhead had in the decomposition? Because when we were working on similar problems, we found that kernel launch overhead became the dominating, I guess, time.
Mm-hmm. So I don't currently have like a complete analysis of that, but so I did do a couple of MBProf runs to kind of just see that in overall. And yeah, we did see that because with over decomposition we have finer work units, and each work unit is offloading a certain set of work. So we have an increase in the number of CUDA API calls it has to make. So that's one of the reasons why a higher degree of over decomposition starts to perform worse.
Yeah.
But I'm not aware of like exactly the performance ratio of how much it attributes to performance.
Yeah. About how long do your kernels take? Are they on the order, let's see, once it gets down to like a couple microseconds, that's where the launch overhead seems to dominate. If it's 100 or tens of microseconds, it doesn't seem to matter.
So these ones run relatively long. So some of them run for hundreds of microseconds, and some of them for milliseconds.
Yeah, yeah, probably not hitting there then. Okay, thank you. Very good work.
Thank you.
We have another question from Nils about running it in the 6D stencil code. Nils, would you like to ask it in voice?
We might have to allow permissions for him to speak.
Yeah, so nice talk. I guess this is sort of a use case or example use case question. So I know the national labs, us, basically everybody in astrophysics, sort of the next big frontier is doing full neutrino radiation transport. And this involves solving the Boltzmann equation, which has 3 spatial dimensions, 3 momentum dimensions, and then 1 time dimension. So it's sort of particle interactions, but you can sort of model them as statistical distributions in space and time. And 3D stencil computations are sort of as difficult or as expensive as we can realistically sort of do nowadays on CPUs. And so what would be interesting to see, it would be sort of a 6-dimensional time evolution on GPUs and seeing a comparison to CPUs, because that's sort of where we think we will be able to get sort of the most bang for the buck in terms of taking advantage of GPUs, because you just have a buttload of floating point operations to do.
Right. So I guess the memory layout will be more difficult to handle, but I'm pretty sure it's possible to do a 60 version of it. Shouldn't be too hard. Yeah.
The interesting things are the ratio of the ghost layer to the inner layer changes substantially, right, compared with 2D. And yeah, it'll be worth seeing how that goes. I thought we need to do 4D, which is what Milk has, for example, and 6D will be nice. Yeah.
Yeah. Yeah, and so this is sort of where, you know, our hope is that discontinuous Galerkin or these spectral type methods would work there, because you basically don't have ghost cells anymore then.
Well,
so that helps that. But, you know, either way, it's sort of, you know, the people who are currently solving the Boltzmann equation are doing it with just second order finite difference. So they have, you know, one ghost cell. But yeah, just a thought of like, this would be a very interesting example where there would be a lot of people very interested in seeing the performance results and how this works on GPU.
Yeah, I'll definitely look into it. Thanks, Nils.
So can you go back to your performance plot for short messages, or whatever the message site, where I could see the 10 microsecond versus 50, not even 10. Yeah, this one on the left, no, on the right. Right.
It's slightly over 10 microseconds, but yeah.
Yeah. The inter process on the left, the difference between the red and the black is significant. I mean, huge. Do you know what accounts for that?
So I think one of the reasons is you're performing kind of like a get operation, right? Instead of the sender directly pushing the data to the remote buffer. So I think that's one thing that can be optimized to lower this down. But currently, a lot of the overhead involves the calling of CUDA API calls. So if it can cut down on the number of CUDA API calls, that would help a lot too.
It's not number of hops somehow too? Like
not really, no. Well, there are like two hops, I guess. One from the sender to receiver, and then the receiver invoking the memcopy.
Yeah, which is itself 2 hops.
Right.
In effect. Well, I see. Okay, yeah. Yeah, working on that would be good. Of course, you can combine the red and blue, I suppose, right? By just having a threshold for at what size to switch to what protocol.
Right, yeah.
Yeah, okay.
Great. Any other last minute questions before we move on? All right, thank you, Jamin. Next, we'll be hearing from Justin Zadeh, talking about advances in Charm++ based languages. Justin, please go ahead.
All right, can everyone hear me?
Yes, we can hear you.
Okay, so I'm Justin Zadeh, a PhD student at the Parallel Programming Lab. And today I'll be talking about some of the advances in the Charm++ languages. Just to give a quick overview of the talk, I'm going to do some comparisons between Charge, which is our general purpose programming language, to Charm++, and give some examples along the way, and talk about some of the embedded domain-specific languages that we've been working on within Charge, briefly discuss some of our future work, and then wrap up the talk. If time allows, I will provide some more substantial examples as well towards the end. So, like I mentioned, Charge is a general purpose parallel programming language. It's based on the Charm++ runtime system, and its primary goals are to lower the barrier of entry to the Charm++ ecosystem by improving developer productivity. It accomplishes this by supporting Charm++ concepts as first-class citizens. So this includes chars, proxies, char arrays, and all of the familiar concepts. And we use static analyses to facilitate and encourage parallel programming. So we want to try to verify things ahead of time if we can. And we also would like to bring some more modern features to Charm++. All of this is fine and well though, but unless it generates performant code, it probably won't see adoption. So that's another high priority task. And we also would like to try and ensure some degree of performance portability along the way. So historically, HPC developers have been unwilling to adopt new languages entirely. So some other last minute concerns would be providing like mechanisms for wrapping existing code in charge, like a foreign function interface, and making sure that our code is usable by other applications so that we can do piecewise migrations of applications to charge. The most recent iteration of the syntax is somewhere between C and C++ and Scala. And this maintains some degree of familiarity while allowing us to bring in those modern language features like type inference and pattern matching. So this will be familiar to anyone who's sort of done Charm++ development, but I just would like to take some time to compare things. Classes are made into char types using the char keyword, and we have a main char keyword for main chars. And then you can also append various modifiers to that keyword, such as array1d for collections. And then we also have a proxy type that we use to denote proxies. And here's an example of what that looks like. We would have a main char named main, which has an entry definition, an entry method for its constructor. And within that constructor, it creates an array proxy, which is an array of 1D or a 1D array of chars called hello. And the key thing to note here is this proxy n semantics, which would kind of be like CKnew in C++. So everyone knows that we access chars through proxies via entry methods. And in charge, these are just char member functions tagged with the entry keyword, which may itself have various attributes such as local, threaded, async, and etc. I mentioned async and local particularly because only these types of entry methods may have return values. And in charge, there are some niceties for handling these types of entry methods. So sync entry methods will block the caller until they complete, which means that they have to be run in their own user level thread so that they can be blocked. So only threaded entry methods are permitted to make calls to sync methods, and we enforce this using static analysis. Then we also have asynchronous entry methods, which return a future value that may be pulled upon until that value is available. This waiting operation would itself be like a call to a synchronous method, but polling is not worth noting. Or polling is not a synchronous call, sorry. So here's an example of what that might look like. If we had a char that had an asynchronous function and a sync function, and both returned an int value, when we called them within a threaded entry method, we would just say thread test proxy.sync func, and then that would wait on the value, and it would just return an integer value. But if we call a asynchronous function through a proxy, it's automatically wrapped as a future, and then that future value can be waited upon using this hashtag symbol. One other thing to note is that charge has traits kind of like Scala, and these can be used to share interfaces between chars. They can't be instantiated directly, but you can have proxies of trait types. And here's an example of what that looks like within charge. We just have a responder trait, which is templated with some value t. And then this class here, my int responder, implements it with some specialization to just integer values. And then we also have to specify that it's an override within there. So one other nice sort of feature that I'll talk about within charge is the support for custom reducers. You can just use the reducer keyword to tag a reducer, and you tag it with the type a value that's being reduced. So in this case, this is like an integer max function. It selects the bigger of two values. And the left-hand operation can be, sorry, the left-hand argument is sort of like an accumulator usually. And so then you would just, instead of having to do the registration yourself and keeping track of an ID for the reducer or perform any sort of message unpacking, the compiler handles all of that for you. So the typical Charm++ application compilation process is that you would provide like your C, C++ source files and a Charm interface file and any other headers and that kind of stuff. And all of that would be compiled to form the Charm++ application. But in Charge, we simply write one .cp file, and that's compiled via the Charge compiler into all of the other familiar headers and wrapped into the application for you. We also have some support for various types of code analysis and transformation passes. And we have a rewritable intermediate representation that's shared between Charge and some of its embedded domain-specific languages. These passes are ordered according to dependencies. And I'll talk a little bit more about that later, but they can sort of be interleaved, and that's why there's that sort of symbol there. So why would we want to support embedded domain-specific languages? Well, a single programming model may not be suitable for representing the entire application. And we would like to give users the ability to choose the right tool for the right job. There may be some types of models that are incomplete and cannot represent all types of parallel computation, but can provide elegant representations or optimizations to certain classes of computations, such as Charisma, which I'll talk about in a moment. Furthermore, this sort of multi-model approach encourages modularization and thereby library use and code reuse. And embedding allows different models to exist side by side, trimming any redundancy that may have existed previously. And the execution of all of these different models can be interleaved simultaneously. So a familiar example would be stack-like operations. And within Charge, we have support for a when keyword that's internally implemented using futures. So pass goes through and does this simple transformation to every when method. Basically, it creates an entry method for that sets a future value, and then within the entry method that called that when, or within the entry method that contained the when block, it's tagged as a threaded entry method, and then that polls on the future value. And I mentioned this because Charisma, which is a language for orchestrating the global view of control for parallel programs, is internally translated to stack operations. So Charisma is a language. Previously, it was a standalone language that employs a macro data flow approach for parallel programming. We represent this data flow using a publish-consume paradigm, which can capture a wide range of static data flows, but not any sorts of data-dependent data flows. So a simple example of that would be just every neighbor in every element within a 1D char array sending a value to its rightmost neighbor, and then the last element wrapping back to the first element. Within Charisma, it would look something like this. We would have a placeholder array, which is sort of like a fixed size indexable channel, but it doesn't really get created at any point, and I'll show that what I mean by that in a moment. The actual orchestration code is this for loop here, which goes through all of the indices within the index space of a 1D char array. And then every element produces a value, sends it to its rightmost neighbor, via the values placeholder. And then every element goes through and consumes a value from that placeholder. And there's an implicit barrier at the end of the for. So what does this get compiled to? Well, it just gets compiled to a when block. So each value, so now every element is producing a value and sending it to its rightmost neighbor. And then when that value is received, it's just consumed in line. A slightly more sophisticated example would be just Jacobi relaxation. And so here we have two placeholder arrays, one for the left elements and one for the right elements. And every char is going to produce two values. We'll return a tuple in this case, and then consume those values in a compute function and do a global reduction over the error. And this will continue to loop until the error goes below some threshold. So why would we want to make Charisma an embedded domain-specific language? Well, like I said, it was a standalone language before, and this meant that orchestrations were separate from everything else in a dedicated file, and char structures were in fact defined in multiple places because the char structure had to be within the orchestration file and within the charm interface file. So by making it a DSL, we avoid this redundancy. We're also able to reuse parts of the shared infrastructure, such as type checking, and all of the orchestration definitions and entry methods can be within the same place, as shown here. As entry method, or as orchestrations have become a special class of entry methods, the chars managing an orchestration are readily apparent, whereas before this was entirely invisible to the user and just simply internally managed. And by that I mean that, so now you can see that Jacobi 1D is the char that is, so I would say, managing this orchestration because it's where the communication is taking place and where the computation, or where the values are being routed. So the next embedded domain-specific language that I would like to talk about is called multi-phase shared arrays. And multi-phase shared arrays are arrays that have a shared global address space and can be synchronized between read, write, and accumulate only phases via a barrier operation. This stems from the observation that applications tend to access arrays in phases of reads or writes. So we do not allow interleaving of reads and writes, and this phased in execution model leads to like a simplified PGAS model. Updates and invalidations are only necessary at the time of the barrier, and remote values only need to be fetched during read phases. So this allows for various simplifications. Before, it was just a library within C written in C++, and this had some downsides because its syntax was a little bit verbose and complicated at times, and there was no support for custom analysis passes for correctness checking. For example, we don't want users to do a read operation when the array's in a write phase. So to overcome these limitations, we're working on an embedded domain-specific language where users can manually infer or can manually specify phase changes, or the compiler can infer them for them. The cornerstone of all of this is phase analysis, which is built on control flow information. So here's an example of what that would look like. So this entry method would be within a 1D char array. Every char within that array is going to enroll in the MSA, which tells the MSA how many chars to expect at the barrier. And then it's going to do a bunch of writes to that MSA, then do a bunch of reads to it, and eventually contribute a value somewhere. And if we take the CFG for that, the control flow graph, we'll see that there's one node within the each for loop where there's either a read or a write operation. So phase analysis starts by propagating this the phases between nodes. So the write is sent to all of the nodes that it can reach before the next operation, and the read is propagated to all of the nodes that it can reach. And then we insert two phase changes accordingly, one to be the initial change from the unknown status to write, and then later a change from the write phase to the read phase. And sometimes these phase changes may be inserted in like a redundant way or inside of loops. And we don't want to do a write sync when we're already in a write phase. So we have an analysis pass that goes through and eliminates those redundant phase changes. And if there is a phase change within a loop, we don't want to do it every iteration of the loop if it's the same phase. So like if every iteration of the loop has a write change, then we just want to move that to the beginning of the loop, which is what we can see here. So as for some of the future work, this talk really doesn't have anything to say about the performance yet, because we haven't done much evaluation there, and so that'll be a major priority going forward. And we have to also develop like a simplified intermediate representation, because the rewritable intermediate representation that we're using right now is actually charges AST itself, and this can be a little bit difficult to extend, and it's pretty hard to compile. So we would like to move towards something that targets LLVM or MLIR as we go forward, or maybe just like a simpler intermediate representation that still maintains, or that's still compiled to C++. We also don't have any interoperability in the current iteration. In fact, the code is generated in a way that's pretty unusable by existing applications, and there's no foreign function interface or anything like that. So suffice to say, the current iteration of charge is still unreleased. We have some quirks to work out, but if you would like to test a pre-alpha version, feel free to reach out to me. We're also looking for other candidates for embedded domain-specific languages. So maybe a language that performs HPF-like array operations, something specialized for tree operations. We're still trying to think about what would be useful on that front. So to conclude, Charge is a general-purpose parallel programming language based on the Charm++ runtime system. It supports multi-model development of parallel applications by embedded domain-specific languages. We have a couple of examples, SDAG, Charisma, and MSA, as far as languages that are currently embedded within Charge. And before I hand things over for questions, I think I would just like to show a couple other example programs. Namely, this is just a simple Fibonacci computation here, where it spawns two chars underneath it, and or where it recurs into two chars every time. And so here's sort of where some of that C++ familiarity comes in. We would take in some command line arguments and then convert the strings to integers and etc., and just print the results out, create a new Fibonacci, which has this trait responder, and then it'll recur and create two more underneath it and continue going. And there are just a couple other example programs that anyone who's interested, I could share with them as well. So with that, I will go ahead and conclude my talk.
Thank you, Justin. Looks like we have one question in the chat from Nils. asking if you're planning on writing syntax highlighting plugins for editors.
Yes, that would be desirable. Syntax highlighting for like VS Code would be probably one of my first priorities, but other ones could be considered as well.
Great. Are there any other questions in the chat? If nothing posted in the Google Doc or anything last minute you'd like to discuss with Justin? Well, are there any other questions or anything last minute that someone would like to discuss with Justin right now?
We do have an announcement after that, so don't drop off. All right. So I think who wants to do that? We will be doing, like we said, a workshop picture, well, workshop video today. All that it would mean is that, and we will do that after the keynote. We could do it now, but just as a rehearsal. But I think if people are ready, just turn your videos on, and so we can see what that looks like. But we will do one at the end of the next keynote at 2:50. And that will give you a chance for people to do whatever changes in their apparel they want to do for the group picture. In any case, we will do that at the end. Jamin, Matthias, any other announcements from you? All right. So all that we'll be doing is we'll be waving for about 30 seconds while we switch from one window to the other window and record it. And we'll probably take a screenshot of each. And that will be our workshop picture. So, all right, thank you. We have a longish lunch break, and we actually finished 8 seconds before our time. So thanks for people for making up, taking short breaks and making up. We will resume at 2 o'clock Central. And for our European participants, thank you, and the Indian ones, right? Parikrit still there? Yeah, who stayed up pretty late last night. We'll see what he ends up doing today. All right, bye then. Pathikrit, not Parikrit. Hey, Hartmut. I said that I should get you back. I'm not sure it was the right thing. I didn't announce it. So let's, and people are actually gone to get real lunch in some cases. I'm about to go get my real lunch. And then I will come and chat with you. But if you have other things to do, that is fine. If you don't, just wait there. Are there people who want to discuss follow-up questions from the morning talk with Hartmut? I suggest you start a room 1 or something, and then go there if there is someone, or you can just continue here for that matter. It doesn't matter. Other people can go in rooms if there are other discussions. So, like I was saying, I'm not sure. Everyone is getting lunch or something, Hartmut. So let me go get my lunch, and then I'll be back. Yep. Just checking if the sound is working. Someone can reply, please.
Yep, I can hear you.
Okay, good. John, you want to test your, oh, can someone give John control of the screen so you can test his slides? We'll start.
I think he has permissions already.
Oh, he has permissions already. Okay, yeah. Excellent. And John, say something so we can test your microphone.
Can you hear me?
Yep.
Can you see me?
I can see you. Yep. Hopefully the sound, it was short. I think I could hear you very clearly, but yeah. But a longer sentence will help.
Okay, how's that?
Yeah, that's good. And I asked you a question on private chat, but we'll start in a minute or two. We'll let people trickle in.
Okay, I just sent you a brief email reply.
Okay, yep. Yep. All right, okay. We'll aim at like 50 plus minutes of talk and 5 plus minutes of questions, hopefully 10, so it can go 1 hour and maybe a little over.
Okay.
If you need a little bit more time, that's okay. All right. Welcome everyone to the afternoon session of the 18th annual workshop of CHAM++ and applications. The keynote speech that begins this session is from someone whom we have been waiting to hear from for a while as well. So I'm very happy to welcome John Miller-Crummy, Professor of Computer Science and Electrical Engineering and Computer Science at Rice University. All of us know him because of his association also with HPC Toolkit. He's been leading that project for many years now. Probably not as many years as we have been doing CHAM++, but maybe close. So, and it's a very successful project. It's being used in the ECP project as well. So prior to ECP project, it was being used all along. It's not just designed for that, but ECP project is playing a big role. And the exascale machines, as we know, are pretty complex and large. And to do the performance analysis for those would be a challenging task. I also knew of John's work on debugging and race conditions. That's one of the interesting things from early on that I remember. I think in connection with that, he has this Dijkstra prize that he received. He's also an ACM fellow. And without getting in a long description, I would let him talk. So, John.
Thank you, Sanjay. I'm glad to join you for the workshop. The timing could have been a little bit better for me. As it turns out, there's a concurrent exascale workshop at Argonne that I'm trying to also attend. So I've been sort of in and out for various sessions for this workshop. I got to hear Jeff's keynote yesterday. So Jeff was talking about the long-term future of heterogeneous applications. I'm going to talk about something that's a little bit closer to term, which is the forthcoming DOE exascale supercomputers. And so, as many of you know, all of the forthcoming DOE exascale supercomputers are GPU accelerated. There's Aurora at Argonne that's based on Intel Xeon processors and forthcoming Intel Z Ponte Vecchio GPUs. There's an AMD-based system going in at Oak Ridge, and it has AMD Radeon GPUs. And then finally, the El Capitan system that's supposed to be installed by Livermore in around 2022 is supposed to have next generation AMD CPUs and AMD GPUs. And so with all of these GPU accelerated systems, over 95% of the flops come from the GPUs. And so it's very important to be able to use the GPUs effectively. So as Jeff was describing yesterday, there's a variety of programming models for these forthcoming exascale systems at the node level. So they're the native programming models that are available from the platform vendors. There's Intel's DPC++, which is extensions to the SYCL specification developed by Khronos. And there's AMD's HIP, which is a CUDA-like model. Finally, there's the directive-based models, the OpenACC model, which has been used for quite a few years for writing applications for the Titan supercomputer. OpenMP is being extended with offloading to support offloading parallel regions and loops to GPUs. And then last, there's a set of template-based programming models that are being developed in the DOE. Lawrence Livermore's Raja programming model and Sandia's Cocos model, which are intended as abstraction layers to support portability. So an application developer can write their code using either Raja or Cocos templates, and then the templates can be instantiated with whatever underlying programming layer makes the most sense for achieving the best performance on a particular target platform. So these are the node level models. Now at a higher level, there's a diverse set of global programming models. There's the message passing interface, of course. There's also partition global address space programming models and the object-based Charm++ programming model. And these are not just my own musings. This is actually something that came from the Frontier specification sheet. And so they're actually expecting these models to be used on these large-scale systems. So this has some implication for tools. In particular, tools need to be able to work with every one of these models and every one of the node-level programming models that I just described. So there's quite a few performance analysis challenges for GPU-accelerated supercomputers. We're concerned about understanding the computation performance, where the principal concern is keeping the GPUs busy and computing productively. So we really need extreme scale data parallelism in the applications. There are data movement costs within and between the memory spaces of the CPU and the different GPUs. There's communication between the nodes, there's I/O. And then there's lots of ways where you can hurt your performance. You can have insufficient parallelism in your application, load imbalance, serialization, replicated work, or various kinds of parallel overheads. There's very complex hardware and execution models. So there's multiple compute engines, multiple GPUs and CPUs that have vastly different characteristics and capabilities and performance concerns. There's multiple memory spaces with different performance characteristics, high bandwidth memory and DRAM. And there's complex memory hierarchies on both the CPU and the GPU, which are different. And then finally, with the GPU executions, there's also asynchronous execution in offloading kernels for asynchronous execution. So there are a variety of measurement challenges for tools, constructing tools to measure the performance on GPU accelerated supercomputers. We've got extreme scale parallelism. And what that means is that if there's any sort of serialization inside our tools, then our tools are going to disrupt the parallel performance. Also, there's multiple measurement modalities and interfaces. So on the CPU, we use asynchronous sampling to measure the performance. There's a callback interface for measuring when GPU operations are launched and sometimes completed. And so that's actually the principal measurement modality for OpenCL. And then there's also GPU event streams that are provided by the NVIDIA and AMD interfaces, where they'll provide a stream of activities indicating kernel launches and timings and other performance information about what's going on the GPU. So one of the key things is that there are frequent GPU kernel launches. And so what that requires is for us to have a very low overhead measurement substrate if we're going to be watching every GPU kernel launch. And I also want to mention that there's an important component that's being provided by the vendors. They're providing these measurement interfaces. And so the tools that we build can only measure what the GPU hardware can monitor. And in particular, support for fine-grained measurement is essential for diagnosing GPU inefficiencies. And so today, NVIDIA is the only one who has support for fine-grained measurement of GPUs. So there's also a collection of engineering challenges for developing performance tools for complex applications that are part of the exascale computing project. So there's the composition of programming models, the composition of the node-level programming model, and the global programming model is the most notable. But then there's also the composition of things like CUDA and OpenMP offloading within the same program. We've seen application binaries from the national labs that exceed 5 gigabytes. And so anything that we do with binaries has to be efficient. There's HPC libraries that intercept system calls like mmap and open and close. And these are libraries like OpenUCX, which is a communications substrate that's used underneath MPI and other things. There's also quirky application characteristics that we have to cope with. So for instance, when monitoring NAMD running on top of Charm++, we found that exit is initiated by a non-initial thread. And that's something that we hadn't really expected. And then working at the national labs on national security applications, they also have some things where they fork non-readable applications. And so we have to be able to cope with the fact that we might not be able to read the application on disk. We might not be able to read its code while it's executing in memory. And yet, the tool still has to survive. So there's also complications with dynamic library loading that acquire implicit locks, provisioning thread local state, which requires implicit locks, forking processes, interactions with the vendor tool substrates, which are creating threads, and callbacks that may happen on various threads. There's interaction between the tools and the software stack, like we're using asynchronous sampling, and so signals are interacting with all of these other capabilities that I just mentioned, forking and dynamic libraries and implicit locks. And there's a lack of vendor documentation on their tooling, and so they have non-standard GPU binary formats. And so all of these are challenges that we have to deal with in our project. So as Sanjay was talking about, all of the engineering challenges with Charm++, I can totally relate. So a lot of the HPC Toolkit project is sort of careful engineering to be able to monitor large and complex applications. So for GPU performance tools, what has been done in the past are tools that provided a trace view, which are a series of events that happen over time for each process thread and GPU stream, or they provide a profile view, which shows a correlation of performance metrics with program contexts. So there are a number of different tools that have been developed. The GPU vendors, there's NVIDIA's Nsight Systems, Nsight Compute, and NVProf. There's Rock Profiler from AMD and Intel's VTune. There's also some third-party applications that provide some support for monitoring on GPUs. There's Tau and Vampire Trace and ARM Map. So Some shortcomings of those tools for analyzing complex GPU accelerated applications are that they lack a comprehensive profile view to analyze the complex CPU calling contexts in which GPU APIs are invoked, and also understanding the sophisticated GPU calling contexts that arrive out of OpenMP or Cocos or Raja, where there's a significant amount of generated code. So the code that executes looks a lot different from what you've written as an application developer. And so you need to know what's coming out of the Raja or Cocos templates to execute on the GPU. And so at best, existing tools provide only, they attribute runtime costs to a flat profile of functions that are executing on the GPUs. And as you'll see for these template-based programming models, that's not enough. So let me briefly introduce you to the HPC Toolkit performance tools, and I'll give sort of an overview of our sort of CPU-based capabilities to just give you a sense of what the toolkit is like. And then I'll talk about what we've done for extending it for GPUs. So at a high level, HPC Toolkit operates as a first-party tool within an application's address space. It employs binary level measurement and analysis. So we're observing executions of fully optimized, dynamically linked or statically linked parallel applications. It supports multilingual codes with external binary-only libraries with compositions of multiple programming models. On the CPU, we're collecting asynchronous samples, which is an effective measurement modality because it has controllable overhead. It minimizes error and avoids blind spots where we can't observe libraries because there's no instrumentation. Using sampling, you can observe everything. It also enables efficient data collection for large-scale parallelism. So for GPUs, we've extended this to use some GPU performance measurement APIs that are provided by the vendors. So there's callbacks to monitor launch and completion of GPU operations. NVIDIA and AMD provide these activity API interfaces that provide information about asynchronous operations that are executing on GPU devices. And NVIDIA supports PC sampling for fine-grained measurement at the instruction level, and Intel provides GTPin for instrumentation of GPU binaries also for fine-grained measurement. So what HPC Toolkit does is it associates metrics with both static and dynamic context, so loop nests, procedures, inline code, and calling context on both the CPU and the GPU. And so I'll get back to the GPU calling context in a few minutes. So our tool enables you to specify and compute derived CPU and GPU performance metrics of your choosing. And so diagnosis often requires collecting more than one species of metric and then computing equations based on that combine these metrics to gain some insights. So things like GPU utilization. And then finally, the tool supports some top-down performance analysis. So you can identify costs of interest and then drill down to the causes, moving up and down call chains or looking at things over time. So I'll start by introducing the overall workflow for HPC Toolkit that we developed for monitoring on CPUs. And shockingly, the workflow really hasn't changed very much for working with GPUs as well. And so while the workflow is very similar, in fact, internally, the tools have changed drastically. So what we start with is you compile and link an application program as you normally do and produce an optimized binary. And there's nothing special that's needed. You don't have to change your make files. The only thing that can be helpful is if you're compiling with optimization and you don't add a -G, then we can collect information at the routine level, but we can't map it back to individual source lines. The only way you get line level information out of the compilers is to add some kind of -G option. Sometimes the compilers will have a different option like -G opt that says, I want line map information for optimized code. So you compile your program the way you normally do, and then you launch your application. For dynamically linked applications, you launch it with our script, HPC run. And what that does is it collects statistical call path profiles of events of interest on the CPU. And I'll talk about GPUs later. And then where necessary, we're intercepting interfaces for control and measurement. So for instance, we'll intercept interfaces for thread creation and destruction and process exit and whatnot, just so that we can control things. And then we also have to make sure that we maintain control over signal handling and we understand what the application program is doing, and we interpose ourselves between the application and the underlying system. So when we're measuring on the CPU, we're collecting call path profiles. And so what happens is we get an asynchronous sample saying that, say, a timer has gone off, and we'll find that we're at a particular instruction in some routine C, and then we unwind the call stack to find that we were called from B, called from A, called from main. And so from one asynchronous sample, we'll collect a call path that says sort of where the cost was incurred. So the cost might represent time, or it might represent some other costs such as cache misses or instructions. And so then as the application runs over time, we'll take these individual call paths and we'll knit them into a calling context tree. So conceptually, there's sort of main at the top, and a subtree in this might represent, say, an initialization routine and a solve routine and some post-processing routine. And the important thing is that measurement of this is proportional to the sampling frequency, not the call frequency. It's proportional to the sampling frequency and the depth of the call stacks. And so what we're collecting here is a tree that has metric counts that are attributed to the nodes. So it's basically a tree with weights. So then to interpret this data that we collect at runtime, we perform binary analysis offline of an application binary. So we extract information about the line map and the debugging information that's been recorded by the compiler from the executables. And then we also parse and analyze the machine code to recover the control flow graph and recover loop nests from the control flow graph. And we extract these loop nests and identify inline procedures, and then assemble a source level program structure file that maps all of the machine code back to the source code. So to do this, we use the Dynans toolkit from the University of Wisconsin. We've been working very closely with the Dynans team, and so we use this instruction API and parse API, which parses application binaries. The SymTab API will read all of the symbol information that's recorded from the compiler, and then the data flow API enables us to do things like program slicing and understand where say, if I'm looking at, say, a register, I can look back in the control flow and find out who defined it or who loaded it. So this works for a number of CPU architectures, and we've been working with the Dynans team to extend it to support analysis of GPU binaries as well. And so it has reasonably complete functionality for parsing GPU binaries for AMD GPUs using the Vega instruction set. And it has some lightweight support that we use to work with CUDA and Intel GPU binaries, but a lot of the information we're collecting from the outside and sort of putting it into Dynans for further analysis for instance, analysis of loop nests. So then the rest of the workflow, we take these call path profiles, we combine them with the program structure information, and correlate and combine multiple profiles for multiple threads, multiple processes, multiple executions. And we take all of the measurement data and we correlate it with the static program structure, things like procedures and files, in the dynamic program structure like call chains. And then finally, we assemble information for presentation. And so we have two user interfaces, one that provides a code-centric view and one that provides a time-centric view, and that allows you to explore the evolution of behavior over time. So here's our code-centric view with HPC viewers. So this was originally developed for analyzing sequential code, but for parallel code, what we found is often most useful is to basically sum over all of the threads and over all of the processes and associate the performance data with the code, because if you're having performance problems, you need to go change the code. And so you need to understand how the performance information is associated with the code. So in this view, we have a source pane at the top, a navigation pane, and a metric pane. And then we have a couple of things for view control. So you can see sort of a top-down view of call stacks, a bottom-up view of call stacks, and a flat view that just shows how costs are attributed to procedures. There's a couple of things for controlling metric display. And so the highlight really is that we have these very detailed calling contexts that we use to attribute program performance. So we get to see function calls in full context. We see information about inline procedures, inline templates, outlined OpenMP loops, and sequential loops. And so the things that are shown in blue are what we actually measured at runtime. And then all of the other information about inline procedures, inline templates, outlined OpenMP loops, and sequential loops is all information that we gather with our binary analysis and overlay on top of our dynamic measurements. So in a profile view, we compress out the time dimension. And so the profile view may often tell you that there's a problem and it's at a particular routine, and you won't understand how that problem arose. So for instance, if there's some sort of load imbalance, and you can see that there's a load imbalance because different processes or threads are spending a different amount of time in there. But if we want to understand how that load imbalance arose, we have to see a trace view, how the program evolved over time. So I mentioned how we're doing this call stack sampling. So to trace programs, what we do is, instead of combining everything together in a calling context tree, what we can do is collect a trace of these call chains over time. So we're collecting a trace of call path samples. And so here this is showing a sequence of call path samples for an individual thread, and then for each thread in the application. And then what we can do is as we view it, we can view it with this visibility plane that we lift. And so up at the top level, everybody's in main. And then if we lower it, then we might see that over time, that in the early part of the application, you're in some initialization phase. And then in the middle, there's a solve phase. And at the end, there's some sort of post-processing phase. So here's the time view that we get out with our HPC trace viewer. And so what we can see here is we've got ranks and threads on the vertical axis, and we have time on the horizontal axis. And so we have a timeline for every thread and process here to the limits of the number of pixels we have in our display. And so here there's a cursor at a particular point at 77 seconds into the execution, and it is on rank 15, thread 30, and we get to see a complete call stack. Now, you might think that it's expensive to collect all this stuff. Actually, to collect call stacks at runtime, it costs us 12 bytes. We collect the calling context tree, and then for these traces, all we're recording is saying I was at node 56 in the context tree at time t. And then node 56 implies a complete calling context by the path to root in the calling context tree. And so we're able to overlay all that after the execution. So another view that we get with HPC Trace Viewer is there's a summary view in the bottom, where essentially we've taken like a histogram of the activity that is shown in the trace view. I forgot to mention that every color in here represents a different procedure that is active. And so what we're showing here is not a key. This is a call stack for the point that's marked by the cursor. And so I can stick the cursor at each of these things to identify what the different colors are that are active over time. And then in this histogram-like view at the bottom, this is like what projections gives you. It shows you the breakdown of how many threads or processes are executing any one of these activities at any point in time. And there's a statistics display that you can use to find out that information. So I can zoom in on a particular window over time and look at the breakdown of what costs are incurred within that time window. For instance, if there's time spent at OpenMP barriers or locks or whatever. Okay, so now on to, now that I've briefly described what HPC Toolkit does, let me briefly dive into some of the capabilities for monitoring the performance of GPU accelerated programs with HPC Toolkit. So HPC Toolkit supports monitoring GPU accelerated computations on NVIDIA, AMD, and Intel GPUs. On NVIDIA GPUs, we're using their CUDA monitoring library. We're also using NVIDIA's Sanitizer library. AMD provides this rock tracer infrastructure for monitoring activities on AMD GPUs. And then Intel has two substrates. They have an OpenCL substrate their programming model, the native programming model is data parallel C++, and you can compile that to use either the OpenCL substrate or their emerging level 0 substrate. The level 0 support is still a work in progress, and so OpenCL is the more stable opportunity, more stable runtime system at this time. And then we can also monitor OpenMP offloaded to devices. And so here it doesn't really matter what device it is, because we're using this OpenMP tools interface, which is designed to be as part of the OpenMP standard. So what's new in HPC Toolkit support for GPU accelerated codes? Well, one thing it does is it unwinds the CPU call stack to identify the CPU calling context where every GPU kernel is invoked. It also internally employs some wait-free data structures for inter-thread communication. So one of the concerns we had was that if we have multiple threads inside the application that are coordinating the monitoring of GPU activities, we didn't want threads to wait for one another. Otherwise, we would have we would introduce overhead in the execution. So I'll describe a little bit more about that in a minute. We also employ binary analysis of GPU code to be able to attribute fine-grained performance measurements to functions, inline functions, templates, loops, and statements that are running in code on the GPU. And we have binary analysis capabilities for NVIDIA binaries, Intel GPU binaries, and AMD GPU binaries. And this was built in conjunction with folks at the University of Wisconsin. We use a novel technique to reconstruct approximate GPU calling contexts on the GPU to be able to understand the computations in detail. So for the exascale computing project, there were some concerns that at places like Lawrence Livermore, they've built an application called Mercury that does quantum Monte Carlo simulations. And so inside the GPU kernel, the Mercury actually executes about 100,000 lines of code. And so if you tell them that the kernel is slow, that's really not good enough. You have to have sort of fine-grained understanding of what's going on in there. And so as I'll show you, these GPU calling contexts are actually pretty useful. So on NVIDIA GPUs, we're using PC sampling to collect measurements of the activity on the GPU. And that gives us information about instruction stalls. And so we can find that we're stalled waiting for data from memory. We're waiting for a result from a previous computation. We're overutilizing the memory pipeline. And so there's no more slots to issue memory operations and many, many more things. So there's about a dozen different stall conditions that we can monitor on NVIDIA GPUs using PC sampling. And then finally, our tools provide support for scalable analysis of sparse representations of performance measurements. And so one of the things that's of concern is if we're collecting a lot of performance data, we need to be able to aggregate it. And if we're going to do this at large scale for full machines, then we better be doing this in parallel. So our workflow for GPUs is quite similar. You can see this looks a lot like our CPU workflow. So we have our optimized binary and we run it using HPC run, and that reports profile files, and it also can collect trace files. In addition, as the GPU binary runs, or as the accelerated binary runs, we collect information about the GPU binaries that were employed by the CPUs. So every time a GPU binary gets launched, there are interfaces inside the NVIDIA, Intel, and AMD runtimes for figuring out what GPU binaries were launched. So we will record the GPU binaries, or we will record pointers to the GPU binaries as the application runs. And then instead of just analyzing the CPU binary with HPC struct, we'll also analyze the GPU binaries as well to recover information about loopness and inline code and whatnot for the code that's executing on the GPUs. And so we'll take the program structure information from the CPU binary and all the GPU binaries and combine it with the profiles and traces the same way that we did before with our HPC Prof and our scalable HPC Prof MPI tools. HPC Prof MPI is just an MPI program for digesting profile information faster. So at runtime, what we're doing is, I showed you the calling context trees that we had before. So we have the CPU calling context tree. And then at the point where kernels get launched, we associate the CPU calling context with the context of the kernel that gets launched. And then using NVIDIA's APIs, we can collect information about the kernels, such as how much time it ran for, the register usage, the shared memory usage, and things like that. We can also get information about the sampling frequency and the clock frequency that was used when the kernel was run. And then we can use PC sampling to collect information about individual instructions that are inside the kernel. And for each of these individual instructions, we can collect instruction counts and stalls, and like total stalls, or stalls for memory, or stalls for synchronization, or stalls for waiting for dependent instructions, things like that. So what we have is a calling context tree, and we have a sparse set of metrics. And so some of the nodes have CPU metrics associated with them, and other nodes have GPU metrics associated with them. But there's like about 100 GPU metrics that we collect. And we don't want to associate those 100 metrics with every node in the calling context tree on the CPU. And so we are able to represent these in a sparse form, so that our storage is only representing the GPU metrics associated with the GPU portions of the code. So as a preview of what we're able to do, this shows that we have this calling context. This is our HPC viewer user interface. We have the calling context on the CPU, and then we see that a GPU kernel gets launched, and we can see a mangled name for the GPU kernel. So this is from the AMRX AMR solver that's being developed at Lawrence Berkeley Labs. And then inside that, we can see loops and inline code and actually function calls. So we have some fine-grained metrics like GPU instructions. We have coarse-grained metrics like GPU kernel execution time that are reported back to the kernel level in the call stack. We also have derived metrics about GPU utilization for within this context. So let me tell you a little bit about how we go about collecting and assembling this. So when doing performance measurement on the GPUs, there's three categories of threads. There's the application threads, there's a monitoring thread, there's one per process. And so this is monitoring GPU events and collecting GPU measurements. And so for NVIDIA GPUs and AMD GPUs, these monitoring threads are provided by the CUDA and ROC tracer tools. And we also have some threads that we create inside our tool to support tracing for GPU execution streams. So whenever we turn on tracing, a CPU thread records its own traces, but we actually have to have some CPU threads that are acting as proxies for the GPUs and recording the GPU streams. So there's some interactions between the threads. We're correlating activities that are launched by the application threads with kernels that are observed by the monitoring thread. So we need to attribute measurements that are collected by the monitoring thread and send them back to the application thread to be logged in its calling context tree. And then finally, we need to record traces where the monitoring thread will gather information out of this stream of activities that's coming off the GPU measured by NVIDIA's CUDA or AMD's ROC tracer. And we want to put out a tracing timeline. And so the monitoring thread has to communicate with our tracing threads. So as I mentioned earlier, one of the concerns is that the threads might get stuck waiting for one another. And so what we did is we built some efficient communication mechanisms for that. So this is sort of an overall layout of our runtime monitoring infrastructure. And so this is specific for OpenCL. The details are a little bit different for working with AMD and NVIDIA infrastructures. In fact, they're simpler. So on what happens is the CPUs are going to launch work on the GPUs. And when they launch work, there's a GPU API callback that says that a kernel is being launched or a memory copy is being launched. Now, who receives these callbacks actually depends upon whether they're synchronous or asynchronous activities. So if I perform a synchronous memory copy, then the thread that launches it will probably get the callback. If I perform an asynchronous kernel operation, then in fact, someone else might get the callbacks for the launch and the completion. And so we have to deal with the fact that the thread that actually needs to log the performance information that says I launched this on a GPU is not necessarily the thread that gets the information about it in a callback that says that I launched a kernel that took so long. So what we do is we take all these measurements and we put them into these channels that are sending all of it to a monitoring thread of our design. And so these operation channels, the monitoring thread is going to multiplex and inspect all the operations that are being launched, and it processes them and then sends information back to the application threads for them to log in their calling context trees. And so we have stuff streaming into our monitoring thread and stuff streaming out back to the application threads in this way, and then stuff streaming out to these trace channels to be logged in trace files to record the activity. So a key component to make all this efficient are these channels. So what we developed is a set of weight-free data structures, or weight-free channels for inter-thread transfer of measurement data. And so the core component of this is a unidirectional weight-free channel between a pair of threads. So for those of you who are not familiar with this terminology, we can either coordinate using shared data structures with mutual exclusion. And so while I'm operating on the data, nobody else can. Or we can use so-called lock-free data structures where there are no locks involved, but there might be spin weighting while somebody else is working on the data structure. So I can try to do an operation on the data structure and then fail. Weight-free is actually a very strong performance condition. What it says is that any operation that I try on a data structure is guaranteed to complete in bounded time. And so what we built is a weight-free channel between a pair of threads that's implemented by a pair of stacks, one that's private and one that's shared. And so what we do is when we're trying to send information from one thread to another, whoever is providing the information is performing a push on one of these stacks. So it's pushing an item on a shared stack, and it does the push with a compare and swap. And then who's ever on the consumer side of the channel can steal the contents of this shared stack, and the shared stack may contain a whole bunch of items that have been pushed on it already. So it steals the whole contents and then pushes that contents onto a private stack. And then the consumer continues to pop elements from the private stack until the private stack is empty, and then it goes back and it steals the rest of the shared stack from the producer. So this is weight-free because the push can fail at most once when a concurrent steal is stealing the contents of the shared stack. Because a steal is going to perform a swap and say, I'm going to swap this topo stack pointer with a null. Once it's been set to null, then no other steal operations are going to change the state. And so a compare and swap that's trying to swap from null to push something on is going to succeed. So a compare and swap can only fail once. And a swap operation will in fact never fail. And so there's no spin weighting. There's in fact, you can end up having to retry a compare and swap exactly once. And so, so this forms a weight-free one-directional channel. And then we have a bidirectional channel that's a pair of these stacks. And so we're sending records down the channel, and then whoever consumes them and consumes the information sends the data objects back to us for them to be recycled and refilled. So in order to coordinate GPU, in order to correlate the GPU API invocations with the CPU calling context, we're going to unwind the call stack at every API invocation, which is like every kernel launch, memory copy, or synchronization. So our initial approach was to identify the function enclosing each call site in the call stack using a global shared map. The problem was that that applications have very deep call stacks and a large code base. So we worked with a couple of DOE codes, one called Nix that has 60 layers in the call stack. Another one, Lagos, has 40 layers in the call stack. And then there's lots and lots of calls. And so using this global shared map was actually costly. So it's a mutable shared map where we're keeping information about where functions are in the address space, the range of functions. So what we did is to facilitate unwinding, we would end up both memoizing call path prefixes so that we didn't have to unwind every step in the call stack. Whenever we got to a common prefix, we could identify that we knew where we were, and then we didn't have to unwind the rest of the stack because the rest of the unwind was known. We avoided access to this mutable concurrent data structure by caching unwind recipes in a thread private hash table. And then we avoided duplicate unwinds. So the CUDA driver APIs and the runtime APIs end up both getting invoked for the same kernel launches. And so we unwind out of only one of them. So what we found was that it was important to have GPU calling context to understand performance. And so GPU code that is derived from these template-based programming models is very complicated. And the NVIDIA GPUs can collect flat PC samples that can provide us some detailed information about what's going on inside the GPU kernels. But flat profiles for instantiations of complex C++ templates are inscrutable. So take a look at this. This is code from the Raja template-based programming model. And this is code that got generated for a dot product. And so the implementation of the dot product on the GPU, there's actually 25 routines that are components of the implementation. And if you see a flat profile, you're just left with this inscrutable set of instantiated templates without really any understanding of how they compose with one another. So what we do actually is we reconstruct approximate GPU calling contexts. We reconstruct the call graph from the machine code, and we infer from the call sites. We identify the call sites in the machine code, and we use PC sampling to recover call graphs. And so what we're able to do is to reconstruct something that looks like this. And so here, a dot product, well, we see that there's a for all, and then it's calling a dot routine, and then it's performing a sum reduction of a reduce operation, calling reduce data. And then we see some inline code and loops all the way down to the routines at the leaves. And so this is actually for the same data. And I would argue that this view is a lot more comprehensible than the previous view. It helps you understand what this complex template-based code is doing on the GPU. So how do we do these approximate reconstructions of the calling context trees on the GPU? Well, unwinding call stacks on the GPU is complicated, and CUPT doesn't provide an unwinding API. So the challenges are the GPU functions can be invoked from different call sites, and we need to understand how to attribute cost to each call site. So the solution is that we reconstruct a GPU calling context tree from flat instruction samples and a static GPU call graph. So initially what we do is we inspect the machine code. So for NVIDIA GPUs, we actually have to invoke the NV-disasm tool that NVIDIA provides to recover the machine code. And so we analyze the machine code and we identify the call instructions. And so from the call instructions, we can build a static call graph. And so that tells us what calls what. But we want to understand what function calls actually got invoked, like how many calls were invoked at every call site. And so we're using PC sampling to measure the execution on the GPUs. And so what we're doing is we use the samples of call instructions as a proxy for how many calls get done from each call site. And so what we do in our static call graph is we label the edges in the call graph with the call counts, the sample counts for each call instruction that were observed. And so here we have a pair of mutually recursive routines that are a cycle in the call graph. So we take our information from PC sampling, and then we do some propagation because it may be the case that we found ourselves in a routine or in something that routine called, and we don't know, we never sampled the call instruction for this. And so we know that we were in there, and there's only one way to get here. So we propagate we propagate a sample up to say we know that there was a call. And so what we do is we propagate activity up to a caller until at least one of the call edges has samples on it. And so, so we start with our initial call graph or our initial static call graph with weights on the edges, do a little bit of data flow analysis on it. And then we identify strongly connected components using Tarjan's algorithm. And then we remove the edges within the strongly connected component. And now instead of having calls to individual procedures, we just indicate that there are calls to the strongly connected component. And then we take the costs that are attributed to each of the procedures. So like costs that are attributed to the strongly connected component, we see that there were 2 calls from one location and 6 calls from the other. And so what we do is we make an assumption like gprof that every function call has equal cost, and we apportion the costs among each function among its call sites according to the ratio of the calls. And so this is the way that we reconstruct our approximation of call and context trees on the GPUs. And so we've done some comparisons of our reconstructions with some reconstructions that we've done using instrumentation with NVIDIA's NVBit. And we found that in fact that they're very accurate, and they also appear to be useful in practice. So here's an example. So this is the ECP Quicksilver application. So this is a proxy application for the Livermore's Mercury code with this quantum Monte Carlo code that I mentioned earlier. And so here's what we see inside the kernel. So we see this GPU kernel cycle tracking kernel was launched, and then it calls a function cycle tracking guts, which has a loop inside it, which calls collision event, which has a couple loop inside that, which calls macroscopic cross section. And then there's some inline code there for that calls nuclear get reaction cross section, and then it gets the cross section data out of a vector. And so we argue that this is like a very useful way to look at the GPU executions rather than just look at, say, flat profiles with costs next to every source line without any understanding of how you got to the individual source lines. So we also have support for OpenMP offloading. And so this is something from the QMC pack. Mini QMC is a code that was developed to test as a proxy application for QMC. And so we can see here is we've recovered information about offloaded OpenMP code. And so then it goes through a series of template instantiations, and then we get a kernel that's offloaded on the GPU, and we get to associate the cost back with the OpenMP outline function in the full program context. We can measure Raja and Coco's template-based programming models, and we can see the template instantiation and see the template-generated code and relate it all the way back to the context. So if the names of the functions are 2,000, 4,000 characters long, you really can't tell exactly what they are just by looking at them. What's important is you go back to the calling context where the code was instantiated, and then you know exactly what operation that you're trying to perform, and that's the routine that's doing it and the cost that was incurred. We're deriving GPU metrics. So I thought I'd mention that we measured GPU accelerated NAMD using Charm++. And so we can identify that there's a costly line in context. So this is assigning the electrical energy calculation. So we can see, I marked it with red dot where it is in both the navigation pane and in the source pane. And then we can see using the PC sampling, we can see that that there's a significant amount of stalls here, about like 1/3 of the time that's, or 1/3 of the instructions here stalled. And that the reason why we had stalls is because they were stalls on waiting for memory. And so in fact, this is accessing E of I. And so E of I is defined up here. And so this is stall waiting for the load from texture memory. We can see that there's full utilization of the GPU by the kernel, and we can also get information from NVIDIA's CUDA API showing us how many registers and how many threads per block and how many blocks and the GPU occupancy. So while NVIDIA's tools provide information like this and also the stall information, they don't provide everything in the calling context. And as it just showing you that I think the calling contexts are really important for understanding these big codes. We also can trace these large-scale GPU executions. And so this is a trace of this cosmological code called NIX that's using an AMR solver. And so we're seeing both CPU and GPU trace lines in this view. If we zoom in on a small part of the execution, in fact, the CPU trace lines sort of look like this, and then all of this is activity on the GPU. So it lets you see some of the structure of what's going on. The green here, I think, is actually synchronization operations that are happening on the GPU. And so by looking at these traces, you can uncover synchronization issues and imbalance issues and places where the GPU is idle where nothing is getting offloaded to it. So I'm running a little tight on time, so I'm just going to go through this very briefly. So one of the things that we are working on is support for scalable analysis of performance data. And so we collect these profiles for every thread and GPU stream in the execution, and then we need to unify them all together to get a unified set of call stacks across all of the threads. And then we produce the information in a sparse form where we have one set of metrics where we're indexing them by profile, like by per thread. And then for every calling context, we have a variable set of metrics. So we have a sparse set of metrics as indicated by this sort of sparse pane. So that's one form when we want to access things by thread. Also, sometimes it's useful to look and see if everybody is executing a balanced amount of work in a particular context. And so we want to access things by context. So we have another sparse form where it's indexed by context ID. And so both of these are four-dimensional representations where we're indexing by in a sparse form. And so they're generalizations of like a compressed sparse row format. So one of the things that we did is we looked at, we're using both MPI and OpenMP. And so the question was, well, what's better to use if we have the option? So within a node, should we use more MPI ranks or more OpenMP ranks? So this is comparing the scaling by adding more MPI ranks within a node and adding more threads in a node. So these were done on a Knights Landing processor. And so it supports up to 256 threads. And what we saw was that we were getting performance improvements out to 128 threads, whereas the performance started to tail off by adding additional MPI ranks over 1 per core. So this is 1 per core and 2 per core. So we're seeing some benefits in our threading model using the hyper-threading in the KNL processor. So here we're looking at 64 cores. Should we use them as threads or ranks? And so we find is where we're looking at one rank with, where we're using all ranks, and then out here we're using all threads, and we find that the all threads is much faster within a node than ranks, and so it's about twice as fast. So we prefer using threads rather than ranks to analyze the performance data. And then looking at the benefits of sparsity, so we found that I mentioned that for the GPU kernels, we can collect as many as 100 metrics. And so if we don't exploit the sparsity and only represent the GPU metrics for code that's running on the GPU, instead of representing GPU metrics everywhere, in fact, we can save a factor of 200 to 300 in the resulting outputs by exploiting sparsity. So this is showing that this is actually showing an execution using our trace view of our scalable analysis. So this is analyzing 64K profiles from a CPU base called AMG 2006. And so while the input data is small, this is only about 5 gigabytes of profiles, we're able to analyze 64K profiles and correlate them all with source code and whatnot in 184 seconds across 8 MPI ranks with 128 threads per rank. And so the blue here indicates some load imbalance, but all the rest of it is very highly threaded and very efficient. And we're not spending our time in locks. There's like almost no locking in this program at all. So, so what we found is that as we scale, we actually get very good scaling in the performance as we add, as we use additional profiles. Then we find that that our execution time is linear in the number of profiles, and that adding more threads reduces the execution time. So this is actually looking at analyzing, out here is looking at analyzing 200K profiles. And so so actually we're pretty confident that we could do with even just on 8 nodes of theta, we expect that we could do 1 million profiles in a half hour. Using larger resources, in fact, you can go faster than that. So finally, some status and some final remarks. So for the different GPUs, we're supporting NVIDIA, Intel, and AMD GPUs. The fine-grained measurement is supported by PC sampling on NVIDIA GPUs. We're using GT-Pin for instrumentation on Intel, and there's no fine-grained measurement capabilities for AMD yet. So some ongoing work, we're building a GPU performance advisor tool that attributes instruction stalls with backward slicing, analyzes code, and offers some advice about program improvements. We have a new user interface, and we're looking at performance analysis of machine learning networks. So a couple of final remarks. It's nice to work with the national labs that have early involvement in a big procurement. It amplifies our ability to affect the vendor software and hardware in the near term. And there's a lot of software development challenges. Trying to develop tools for 3 GPU software stacks at the same time is kind of ridiculous, but that's what the whole exascale program is about. So I'm sorry I'm running a little bit late, but I'd be happy to take any questions that you might have.
Certainly, thank you very much. We are going to be okay going a few minutes over. So so anyone has a question that's already, we just put the Google Doc out again, but since there's no question there, go ahead and ask question. It's okay. If 2 people speak over each other, that's not a problem. We'll resolve it. I had a question, but I kind of have to retrieve it. Can you go back to your slide 32? 31, sure. Maybe. I had a broad question and a narrow question. So, I see. Calling context, maybe I think I remember this now. So maybe it is the 30 or 31. The point is, I had forever, I haven't paid, I must admit, that much attention to it, but all methods that try to do sampling seem to be inaccurate when the grain size is small, when their durations are small. This is noticeable in gprof. You probably do better, I don't know. But the other side of that coin is that I feel like there is no need for those because the overhead for timer calls has gone so much lower, or at least it had. It's just a register lookup that every entry exit can be actually traced. So, and if you don't want to store it, you can increment some counters or whatever. What do you think? I mean, is there a need for sampling still?
So I think that if you're doing tracing with timer calls, are you talking about just tracing something like GPU API invocations, or are you talking about tracing every function entry and exit? Every function entry and exit, yeah. So actually, if there were some experiments that were done by the Tau team on tracing at that sort of granularity, and so I remember when they were doing this for this quantum chemistry framework called Madness that uses these template-based programming models. And so what they would do is they would process the source code, and then they would add like enter exit things to every template that you were instantiating along the way. And so what would happen then is that both, like adding these timer calls, both could disturb the template instantiation. And so what they ended up with was an overhead of a factor of 30 for this very complicated code. And so a lot of that overhead came from tracing very fine-grained things like lock acquisitions that were just minuscule, okay? And so what they said is, well, so we'll use this technique called throttling, where for very frequently called procedures, we just won't trace them. They're very frequently called and they're short. Yeah. Well, once you applied that throttling, then they completely missed the fact that there was actually lock contention and that was a problem, because the cost of tracing all of these very fine-grained routines for locking caused them to say, oh, we need to use throttling in order to bring our overhead down. But if you bring the overhead down, then you completely miss the performance bottleneck. So I would argue that with sampling that we can see those kinds of things and get all of this detail throughout templates without actually any cost by overlaying all the information after the fact. So we found that sampling is actually very useful, both at not just at the routine level, but attributing costs within individual routines and within particular contexts. And so I don't say this as someone who's just sort of like trying to sell an idea. We use this all the time, okay? So for instance, when we were developing our scalable performance analysis, we are using our tools to understand the inefficiencies in it and then correcting the algorithms where we're spending too much time in particular places. We're noticing lock overhead and refactoring data structures and things like that. And so the sampling is just incredibly helpful to get that very fine-grained detail. And on the GPUs, the sampling gives you instruction level detail. And you can't get that by just using timers.
Yeah, but I guess you're right. I have to look at it again to understand it. But you are saying somehow, even with sampling, I would have argued that sampling would miss those fine-grained details too, because it's just, you won't get into those situations often enough. But you somehow seem to think that's not the case.
If you collect enough samples, so you don't actually have to sample at a very high rate, but if you collect enough samples because the application runs for a period of time, then that gives you very fine-grained detail inside the application and allows you to make very, very detailed analysis decisions.
Yep. Okay, that makes sense. Yeah. Okay. Another question? There's a question from Nils. Nils, you go ahead, ask the question unless you want me to read.
Yeah, so this is really, really nice, and I really like the sort of the views that the view parts that you've adopted from projections. I always found them useful. So I sort of have two separate questions. A few years ago, we tried HPC Toolkit, and we ran into some issues with LD Open and loading Charm++ and OpenBLAS when OpenBLAS was built with threads, even if we disabled threading and this kind of thing. General question, has there been work done on sort of improving HPC Toolkit and Charm++ interoperability and this kind of thing since then? I think this was
there has been a lot. So you notice that there's this page of war stories. Okay?
Yeah.
And so OpenBLAS creates threads inside its init constructor. And then if we fork off a helper process, then it invokes @fork handlers that trigger thread destructors, and there's chaos. Okay.
Yeah. Okay.
And so we've addressed all of these things. So we don't fork, we use clones so the @fork things don't get invoked. We are very careful about now tracking dynamic library opens differently using this LD audit layer. And so that's something actually the best support for Charm++ is actually in our develop branch right now, which you can build out of spec. But what I would say is that all of this is a work in progress. As you can see, we're both hardening it for these complex applications and for 3 GPUs and scaling all at the same time. Okay. Right. So what I would say is that all of these improvements are coming to our master branch as soon as we can integrate them, which is going to be over the next month and a half. Okay.
Oh, that's awesome. That's a really good timescale for us, actually.
Yeah, that's great to hear. Projections that Nils mentioned we are very used to it. We really like it. I really like it, as my students know. But it's a tool we designed in 1994. And it's been continued to improve. It's based on basically a tracing framework, and the sampling and call stack issues have been ignored. And it will be great to be able to use those two in conjunction. But we find projections useful for scaling type of analysis. But these other issues will be very good to have that as a complementary, at least, or if not exclusive. So.
Right. So projections is operating at the level of individual chars, correct?
It knows about chars. I don't know what you mean by operating at. It knows about.
What I mean is the instrumentation is like not at like the loop level or whatever. It's at this higher level.
Method invocation.
So,
yeah.
And so what we get is all of the detail for all of the code that's executing inside.
Yep, right. That's correct. Yep.
So like at the high level, the projections level view can tell you about scaling, and it can tell you that you're not doing enough of this or you don't have enough of that parallelism, but it can't tell you internally why something is inefficient.
Right.
That's what we can do.
Yep.
Okay.
Excellent. Okay.
Right. That was basically, well, so first, thank you so much for dealing with all of this nightmare that is, like this open gloss thing. I'm so sorry and thank you. And yeah, my second question was
open gloss is only the half of it. Okay.
Yeah, I'm sure.
The ML frameworks like PyTorch, there's more war stories on there from PyTorch.
Yeah, I'm sure. So yeah, my second question was sort of, if I remember correctly, HPC Toolkit does sampling, right?
Yes.
Yeah. All right. Okay. And so that's exactly what you and Sanjay were just talking about. That's something that sort of was the thing that I've been missing with projections is I would like to be able to do sampling and so that but have sort of these nice views. So I guess this has turned into less of a question and more of a comment that I'm really looking forward to testing out this new HPC toolkit. That looks
okay.
Really nice.
Well, we would love to work with you. I didn't get a chance to try it out on like a larger NAMD thing on Summit last week when I was looking at NAMD. I could only figure out how to build GPU accelerated NAMD for a single node. And so that's all I looked at so far. But I saw that there was a paper that was looking at NAMD performance on Summit, and I was very interested in sort of trying it out to see how our GPU accelerated infrastructure would be able to monitor that.
I mean, just to correct an impression, Nils comes from a cosmology community, and his application is Spectre and Changa. There are these 3 or 4 other highly scaled applications that might be, of course, others too would be, there may be a dozen. So people might be very interested in exploring this, and you might be interested in some of them as at least research-wise or otherwise use cases.
Absolutely. So, absolutely. And so if you're interested in exploring something with HPC Toolkit with Charm++, if you try it out and have any questions or run into problems, please send a note to our mailing list. I suggest the mailing list rather than me, just because my mailbox is just way too full. And so at least with a mailing list, there are other people on my team who will look at it and make sure that it gets some attention. It'll probably end up on my lap, but someone will say, John, read this email, which is helpful.
Okay, yeah, no, that's perfect. Yeah, so basically we solve hyperbolic partial differential equations using, so it's a grid solver. And so basically we have some very floating point intensive loops and these kinds of things, but then we also have to worry about all of the inter-process communication. And so it seems like HPC Toolkit will be able to give us a view of what are we doing bad in terms of the floating point or memory allocations, bad memory accesses, and also be able to give us the view of how bad are we doing on the communication. So thank you.
That's the theory. And then if there are little interactions like with the software infrastructure, we promise to address them, because this is like on our hit list. If we're going to meet the challenges of the DOE ECP project, we have to be able to work with the most complex applications on the planet.
So we are running a little late. David Hardy has a question. I had a question. I probably could postpone my question, but let me ask you briefly, then you can tell me a forward pointer so we don't forget. Is that I was very interested in your stack, what do you call it, the CAS-based one process to process channel. Is that code somewhere I can see?
It is. That is in the HPC Toolkit master branch. In something called a bidirectional channel.
Yeah, because that steel process was not clear to me how the steel happens, but I will look at it later on.
Okay, there's also an ICS 20 paper that describes our tool and actually has the pseudocode for this and explains it. Okay, excellent. That's a good place to look for it.
Okay, will do. Thanks. David Hardy, your question briefly?
My question was already answered. It was just whether or not these tools worked on power, processors. And yeah, so for the purpose of, again, profiling NAMD on Summit. So I can certainly help you build a parallel version of NAMD for profiling on Summit too. So yeah.
Absolutely. So that would be a great thing for us to look into together, because I think that if we are not able to deliver insight into what you're doing, then we're doing something wrong. And if we're doing something wrong, then that's a research project for my students. So we'd be happy to work with you on it.
Okay, great. Thanks a lot. That sounds great.
Excellent. All right. Thank you very much. And it was an excellent talk. We went over a bit, but that's okay. Thanks a lot. Hopefully you can stay for a talk or two, but otherwise we'll stay in touch.
I'd be happy to answer any questions by email, but I actually have to run back to the Aurora workshop at the moment.
Yeah, you mentioned
they're talking about performance tools this afternoon.
Excellent. Okay. All right. So on to the next session, Chair.
Thank you. And I look forward to watching the videos of the talks that I missed.
Yeah, all right. Thanks.
Okay. Take care.
Yeah, bye.
Thanks for that. I'm Kavita Chandrasekhar. The next session is on load balancing and molecular dynamics. And our first talk is going to be from Phil Miller from Intense Computing on advances in VT's load balancing infrastructure and algorithms.
Actually, can you hold on just 1 second, Kavita? I forgot completely about the group picture. We wish we had done it with John, but even without, this is our chance to do it. So can everyone please turn on their cameras and let's do, I mean, it will just continue recording. We'll separately splice this out later on. Oh, John's here. Okay, excellent. And put the gallery view, whoever is in charge. Stop sharing. Okay, excellent. All right, so now, hey, hi, Filippo. All right, well, everyone there are two screens. I don't know how we're going to take, I don't know how exactly this will work, the recording of the two screens, but just wait for 15 seconds and then we'll record it and see what happens. Someone else take the screenshots or something like that. So please, okay, and go to screen 1 and screen 2. I think we don't have screen 3. So that's excellent. All right. Is that enough? Thank you. All right. Bye then. All right. Kavita, back to you.
Yeah, so like I mentioned, the next session is on load balancing and molecular dynamics. And the first talk is from Phil Miller from Intense Computing, and it's on advances in VT's load balancing infrastructure and algorithms.
Phil was waiting at the waiting room for some reason. Okay. I know, I just realized I was mute. Sorry, Phil, I don't know what happened, but I think you're back in.
Saskia, you still joining?
Is Phil back or not? Oh,
He's still in the waiting room saying he's joining, but
Okay, I think now he's
looks
back.
like, yeah. I think he went out. Oh, there he is now. Okay.
Phil? Okay, Phil is unmuted now. Sorry, Phil, I don't know what happened, but hopefully you're back in.
Hi, you hear me now?
Yep.
Okay, system, okay. Start video. Are we set up for my talk now? Sorry, I missed the photo prep.
Yeah.
Okay.
Ah, that's what happened, I see. Okay.
Looks like there are still issues with Phil's network.
Oh,
I'm seeing him as frozen.
ask Phil, should we switch to the next talk and do his talk later? Is the next talk ready?
Yeah, I'm next. I can fill in if Phil has issues.
Oh, there's Phil.
Hi, sorry about that. Apparently, the network is hiccuping for me. Am I back on?
Yes.
Okay, great. Get that. Share that. Okay. Am I audible? My screen's visible. Everything's good?
Yes. Yes.
Okay. I will get started. I'll shorten my introduction because we're running a bit late. So hi, I'm Phil, an alum from PPL and later CharmWorks. This afternoon, I'll be talking about some work we've done on load balancing under the Dharma project, both infrastructure inside VT and some of our related tools, and some algorithmic and theoretical work that we've done as a result of what we've seen in applications. Taking a slightly different view from earlier of the suite of modules in the Dharma toolkit, we have the VT runtime system that executes applications in a task-oriented manner and integrates nicely with overall MPI execution. So that provides instrumentation of application execution at the same kind of granularity as Charm++ of individual handlers being executed and the amount of time they take and the dependencies between them. Checkpoint provides serialization that supports migration of objects between different processes so that we can move them around for load balance. And then the load balancing analysis framework is our simulator that may be an answer to the request that Lercio made in his presentation earlier today for some amount of standardization of data formats and simulation platforms for load balancing work. In VT or in the Dharma realm, we're not just working on improving load balance for any one application or as just an abstraction independent of applications. Instead, we're kind of looking at improving the overall load balancing research and development lifecycle. So the applications written in VT and running on it run with designated phases and what we call subphases. So we could think of those phases as essentially time steps of an application. whatever broad outer loop that the application repeats. So VT is able to export its load balancing statistics database into files that contain the list of objects, their workloads, phase by phase, their communication graph, and the mapping of those objects to processes in the run that was recorded. The load balancing analysis framework then is a companion tool that can read in those statistics files, and it contains implementations of various load balancing strategies, including those implemented in VT itself, and it can simulate the application of any of those strategies to the data given to it. It can also be used to implement new strategies, or to tweak strategies, or to do parameter exploration of different settings and configurations for the strategies. So if you had something like an imbalance threshold that you're targeting, or that you use to decide what is overloaded or underloaded, you can try many different values of that in the analysis framework without having to actually use big parallel resources to get an approximate result of how well that'll work. So the LBAF can run those various strategies, produce new mappings, estimate what performance those mappings would provide, and it can then output those mappings to a corresponding set of files that actually are the same format as the statistics. And then the VT runtime has a special load balancing strategy that, instead of looking at the instrumented loads it stored, looks at a set of files that it can read back in from the analysis framework to apply the mapping that the analysis framework specified. And then you can run with that mapping to measure the actual performance. So this, in many ways, makes for a much more iterable process, shortening development of both new or modified load balancing strategies, and the process of tuning the load balancing applied for any given application. One place that we found it to be especially helpful is in developing new distributed load balancing strategies, because you can implement them not in terms of handlers and messages that are all going to run asynchronously, but rather as just a simple bit of serial code that simulates which processes are doing what and what they know, all in one straight line bit of code. So this kind of has echoes of BigSim, which was the full tracing execution simulator for Charm++. But we're working in a much more simplified environment where we're not capturing task dependencies. We're just kind of capturing what general synchronization interval various tasks ran in, and accounting load accordingly. So we found this to be a decent balance point or trade-off point for this kind of work. So as I mentioned in VT, our outermost level of, I guess, division of time is what we call a phase. So it's kind of a collective interval, meaning it should be about the same across every process. It should be synchronized. And in an application, that might be a time step. It might be one broad portion of execution if you have a non-iterative application. In VT's execution model, a phase will often align very closely with the execution of all the work in a single collective epoch. So that you start off some initial set of messages, and they spawn more work, and termination detection figures out when all of that work across all processes is complete. So load balancing treats the phase boundaries as the markers for when object loads should be roughly equal. So building on that, the infrastructure in VT is growing a general interface for phase management. And we're not here yet, but we expect to have this implemented in the next couple of weeks, actually, is that there are lots of things in parallel applications that naturally might change on phase boundaries. So load balancing, you might want to run a strategy and migrate objects. You might want to output statistic files separately from whether or not you ran a strategy at that step. Tracing can be enabled or disabled at particular steps on some ranks or all ranks. Similarly, trace files could be flushed at particular phase intervals. We can track memory usage. We've got a recently merged very broad diagnostic framework in VT for tracking system level performance counters of things like message counts, message sizes, handler durations, and a broad range of other activity metrics inside the runtime system that applications can add their own diagnostic values as well. You might want a checkpoint on phase boundaries, and termination detection. We can also apply certain debugging checks at those points that say there isn't a set of epochs that are sitting open and unfinished across phase boundaries. So this is kind of what we've thought of so far for things that one might want to do at phase boundaries. We expect that more will emerge over time, but these are all the kinds of things that applications often say, you know, if step mod 7 equals 0, then do something special. We want to provide a coherent, consistent abstraction in the runtime to support that. So as I alluded to earlier, in VT, with applications that we're working with right now, we find that phases sometimes have internal structure of synchronization that affects how the timing of work should be load balanced. And so we call those subphases. And if you consider the set of subphases in a phase, that ends up creating a vector representation of the workload for each object, rather than each object just having a scalar value of the total time it took during an entire phase. So we've also explored ideas of further structuring within the load instrumentation space to capture other things. If you have kind of a multi-physics or multi-component application, you kind of need to consider phases or subphases potentially separately per component. And you might have iterations within even a given subphase of, say, like a gradient descent algorithm or something like that. So just to give some illustration here, this is a projections trace from the Empire application, colored by entry method here. And this is a single phase of its execution. And so when I mentioned the iterations earlier, there's one part of its execution structure that actually is iterative, that it has to repeat one kind of computation multiple times until a convergence criterion is met. And so you can see the very first iteration in that runs the bulk of the work, but then there's several more iterations following with varying amounts of work. So to explore the subphases, what I have here is that same projections trace of Empire, but marked off with points where there is inherent synchronization across all the processes in the system because of dependencies on particular data generated over the course of the preceding subphase. So here I've marked off 5 subphases, and the T1 through T5 are the job level times for the taken for the subphase. So going with the principle that every math or CS talk should have some equations. Here are some equations that I'll go through to explore this and give kind of the derivation of the vector-based load balancing problem that considering subphases poses. And this, I guess, will be a prelude to Ronak's talk following this, who's taking, I guess, a somewhat broader perspective on load balancing more than just scalar timing values. So what we have is the total time for the execution of a phase is the sum over the subphases of the subphase times. And in each subphase, the time that's taken is the maximum work over any processor in that subphase. So W is the work, P is processors, S is the subphase. So for instance, in subphase 2, this process is probably the one that's taking the most time, though there are a few others that come close. And in phase 4, ignoring the iteration structure and only looking at the first iteration, this process has the longest time in that subphase. And to show kind of the reason that we're interested in balancing, considering particular subphases, notice that the loads between subphase 2 and subphase 4 are complementary to each other. Because this was balanced using only the sum over all of the subphases, the objects that were heavy in subphase 4 are counterbalanced by having been light in subphase 2 in their assignment. So it looks like that those PEs are at a reasonable average workload, even though they're actually overloaded during some intervals and underloaded during others. So in terms of representing this further and formalizing the problem that we're trying to solve, we have a work matrix W that's made up of the entries that we described here, which is the product of two other matrices, A and L. So this W matrix is shaped by number of processes times number of subphases. So we'll consider L first, just because it's a little bit easier to understand. So this is the per subphase object loads. So it's real numbers of just how much time was taken for every object, that's N, in every subphase, that's S. And then we'll consider what I'm calling the object assignment matrix, which is a Boolean matrix of processes cross objects. So basically, there's a 1 in this matrix where a particular object lives on a particular process, and a 0 everywhere else in the corresponding column. So that's what this, this constraint expression on the right-hand side shows, that the sum over processes for the assignments of any given object have to be 1 for all objects. So if we were to call this a discrete optimization problem, our objective function is minimize T, the total time for a phase, over possible values of A. So choose an assignment of the objects that minimizes the overall phase execution time. So as presented, this has some problems. So this assignment matrix is very large and very, very sparse. It's very not scalable. It's kind of the worst case. You get a lot of constraints here. So it's not really the way you'd like to represent or think about this problem. So instead, we can start shifting it towards a more familiar integer program optimization from a 0-1 optimization. So wherever we had a 1 in the object assignment matrix, we can consider a mapping vector that just has a number of entries equal to the number of objects. And that mapping vector just contains an integer of which process the object lives on. So these two representations are easily interconvertible, but that mapping vector is of course, much, much smaller than the assignment matrix. And to support representation as something more like a linear program, there's apparently a standard trick in the discrete optimization community of replacing maxes over a vector with inequality constraints that whatever value was equal to the max just has to be greater than any entry considered in the max. So that's potentially broadens the set of solvers that could be applied to consider this problem. So this is formulated to be able to plug it into standard solvers. We haven't done that yet, but we are planning to explore it. There are some MPI-based libraries for this that we think could actually be used directly in a VT load balancing strategy to do this online even. So we have a number of things to explore here. So for those looking for a little bit of literature reference here, this is in some sense the classic job shop scheduling problem that that the normal scalar load balancing would be, but it presents kind of a coupled set of multiple instances that all have to share a single set of assignments, and then you're optimizing the sum over all of them to, you know, where each subphase is a single job shop, but they have to have the same param or the same variable values for each of them. So reaching into PPL history, this kind of problem was actually considered in Gangbin Zheng's PhD thesis. He shows brief performance results, but doesn't describe what algorithm was used or show code. And I wasn't able to find code in the Charm repository history that, that reflected that load balancing strategy. So we're particularly interested if anyone recognizes this problem structure from the optimization literature. Pointers would be very much appreciated because particularly to like known good heuristics for this kind of coupled multi-job shop problem, because we want to see our applications based on facing this go faster. So shifting gears a little bit, another thing that we've implemented in VT that had a preliminary implementation in Charm++ that never really got adopted was a notion of load modeling. So in Charm++, there's the stated principle of persistence, but that's kind of taken to mean implicitly that the loads in a phase immediately preceding the invocation of load balancing should be used as the predictor for the loads in one or many upcoming phases. So by abstracting out load models in VT, we've made that implicit assumption an explicit embodiment of how we're going to predict load in future phases that we're attempting to balance. So it's essentially defining the interface going from instrumented data about object workloads from previous phases and subphases and producing predictions. So this offers the possibility of different configurations. You can do noise filtering at this level. You can track linear trends. And we have a composable function interface to define somewhat arbitrary models. So as this is being used right now, it's also mapping the vector of subphase load data down to scalars for current strategy. You know, just summing the loads across subphases, but it's very easy to pick different kind of norms or just choose a subset of subphases. So here is kind of the capsule summary of the load model interface. I've elided most of the members of that because I really only want to focus on the one interesting one. So we have the load model class that's just an abstract interface class with a get work method that's going to return a predicted or measured time. It takes an identifier of an object that's being queried, and it takes a phase offset argument saying when the query should apply to. So that phase offset is the structure shown here, which takes a signed integer of phases and an unsigned integer of subphases. So the phase argument can represent both past and future. So if a query is looking into the past data, then it would pass a negative number as the value of phases. If it's looking into the immediate future, it would pass next phase, which is 0. And if it wants a prediction further into the future, say for load balancing that's trying to account for known to be changing loads and optimizing several future steps altogether, then it can query multiple future steps. And if you have a prediction that is going to change over time, then that can give you more accurate results. So here's the enumeration of functions that we have available to compose right now. So there's the raw data that actually knows how to access the load balancing database, statistics database from VT. There's a norm function that runs over subphases, and you can specify what power you want it to use. You can select subsets of subphases. You could double up some of them to weight some of them more. You can do various things like that. Can add some imputed amount of work for every message that gets sent as an overhead. You can apply different models per collection, so per char array, essentially. And then we have our predictors, which can be composed on top of those. So naive persistence is a predictor that just says, take a look at the most recent past phase and return that as the prediction for all future phases. And that is used as part of our default model, which matches the implicit model in Charm++, that you take one norm over all of the subphases from the instrumented data and predict the future load as the load from the most recent past step. Other predictors that we have here are a persistence-based model of the median of the last n steps. So this is something that we hypothesize could be useful for filtering out noise. If you have objects with mostly stable loads, but a noisy system, this should tend to give you a more accurate predictor of what workload the object itself represents than the single most recent phase, which might have noise creating outlier values. We also have a linear model that creates a linear regression over the loads observed in the past k phases, and then can predict out into the future, more than one step based on that same linear trend. And finally, we have a multi-phases model that can sum the values across n future phases to account for the desire to load balance with a predicted changing load over, say, the next 10 phases rather than just one. So we've got a variety of load balancing strategies implemented in VT right now. We have a rotate LB that should be familiar to Charm++ users as well for debugging some kinds of serialization failure, just migrates everything. We also have for testing a random LB that creates a permutation of object assignments. This can be useful for code that interoperates or uses existing MPI SPMD code, because anything that has a dependence on having the same number of objects per process will tend to fail very quickly under the permutation produced here. We have a centralized greedy strategy. We have a gossip strategy, similar to the one in Charm++, but with some algorithmic refinements. We have a hierarchical strategy. We have a Zoltan Zoltan-based hypergraph partitioner that can optionally be communication sensitive, and that uses the MPI collective asynchronous embedding support that VT offers. And as mentioned earlier, we have the StatsMap LB that reads in a fresh mapping from the LB analysis framework and assigns mappings accordingly. So in conclusion, we're aiming to increase the expressiveness of instrumented load data that's coming out of the runtime system. We're trying to shorten the development and tuning cycles for load balancing. We're looking to improve the abstractions in real implementations and doing some formal theoretical work on these vector load representations to see if we can get better results when we take that more detailed data into account. So I will stop there and open up for any questions.
Kavita, can I ask a short question?
Yeah.
So not question, actually answer. Sorry. Gangbin was here yesterday. I don't know if he's here today. And Filippo, I just saw in the pictures when you went missing. So the two of them have, but the strategy, if I remember right, for Gangbin that you were asking, was a heuristic strategy, which used heaps for both. Well, anyway, for measuring both phases, trying to make sure they don't exceed either one in some average. But I think, I'm not sure, but it was a heuristic greedy-ish strategy. And the prediction for future is a feature that I think Filippo had done once. I mean, but it didn't come to that much, but it was an interpol, and then Harshita used it as a meta balancer for interpolating towards the future to decide when to do load balancing.
Yeah, so meta balancer did a future-oriented prediction at the process level. This is the object level predictions, and yeah, the object level load modeling that Filippo did, I found that in the Charm code before I started implementing this. I just didn't see anything that ever called it.
Right. I think this is excellent, and I think we should figure out a way in which both VT and Charm and other such systems benefit. So we have already talked about it before, but for everyone's information, we should.
So for everyone's awareness, the load model interface that I implemented in VT is actually structured in a way that it is completely independent of any of the rest of the VT code. So anyone can easily enough write classes that implement this interface or that consume this interface in Charm or in HPX or whatever other runtime system.
Can you unmute Gangbin? Someone?
Yes, I'm here.
Oh, hi, Gangbin.
Hi. Yeah. Yeah, I heard my name. So I believe the code is in a separate branch, but that was like 15 years ago.
Right, yeah.
The reason we didn't merge it was because the changes was a little bit intrusive because of the multiple phases, and then the database has to be heavily modified into, it's like a vector, like I said, it's like a vector database, and because it's like an array of phases.
Yeah, we found that the memory footprint, if we're not careful in Empire, does start to become problematic. So
right.
Yeah.
Yeah, so I guess that was the reason we didn't merge it. But it was tested with, I forgot the LeanMD or even I forgot the NAMD, but I think
it was LeanMD, if I'm remembering.
Right.
That section of the thesis.
Yeah, the thesis has some data, but the question was mainly the code. Okay, good enough. Thanks. Any other questions?
I've got a couple questions. One, and where you mentioned that you're able to run with the LBAF generated mapping and do this calculation offline and feed it back into the application.
Yeah.
How do you ensure that that mapping maps to whatever the new objects are? Does it have to be deterministic in terms of how the data is partitioned and how the objects are numbered and things?
I think it relies on a deterministic mapping between the objects and the identifiers in that statistics file. I'd have to check with Jonathan, or maybe he's online if he's feeling okay.
Yeah, it does depend on a deterministic initialization, essentially, construction order.
Okay, gotcha, it makes sense. Then my other question that I guess sort of ties into my talk too is you mentioned the stuff about subphase vector loads. Do you have specific strategies that take into account these vector loads? You talked about this ILP formulation. Or is that still something you're working on, or do you have results in that vein?
That's work planned. We don't have
Okay.
results. Other than we've played around a little bit with different models that produce scalar loads out of those vectors. So like different norms and like different degree norms, or selecting individual subphases, and nothing we've tried so far has really come out better than the naive one norm. But we're still poking at that.
Okay.
Or trying to figure out if there's some theory that would say that a particular function of the vector should give you a good representative scalar.
Okay. Something I know you mentioned about literature, there's a field, the optimization problem called just vector scheduling, that there are a few papers in, started by Chandra Chakuri, actually.
Oh, okay.
That you might want to look into. So it'll kind of tie into stuff I'm about to talk about now, but
Great.
that might be where you start looking.
Great. Any other questions? Okay, I guess I will turn it over then. Thank you.
Kavita.
Thanks for the talk, Phil. The next talk is from Ronak Butch on vector-based load balancing in Charm++.
Okay, can you all see my slides? Are my slides visible at all?
Yes, they are.
Okay, thank you. Okay, I'll get started. So as Kavita said, my name is Ronak Butch. I'm a PhD student in the Parallel Programming Laboratory here at the University of Illinois, and my talk will be on vector load balancing in Charm. A lot of this stuff ties into all the things that Phil just talked about and the questions I was asking to him. So in the interest of time, I'll go a little fast, but feel free to stop me if you have any questions, and obviously I'll take some more at the end. Okay, so before we get into the crux of vector load balancing, let's talk just about load balancing first of all. So load balancing is the hallmark of Charm++, as everyone here, of course, knows. One of the big things that load balancing does is minimize the maximum load on a PE. In lots of applications, performance is often limited by that. And when you do an iteration, you're constrained by these laggards until you go to the next one. So the way that this generally works in Charm is that the RTS will automatically measure load, store that in some database, feed that to strategies, and then the strategies will make some decisions and migrate objects based on that load that it saved in response to the decisions it's made. This has especially helped over the years for dynamic and irregular applications. We've demonstrated hundreds and thousands of cores of scaling for lots of these applications and can achieve really, really high performance and scalability that without some form of load balancing, they would not be able to achieve in the first place. But really, at the end of the day, we don't really care about load imbalance necessarily. What we really care about is performance. And in truth, in my perspective at least, load is really just a proxy value that we use to reason about performance. At the end of the day, we want to minimize execution time or time to solution. And realistically, I'd personally rather have an unbalanced fast program than a balanced slow program, where balanced is some function of utilization. The thing is that what we call load is often a very, very good indicator of this performance that we're talking about. And in lots and lots of cases, CPU time measured per object just by itself is often a sufficient metric for this value. But there are lots of cases that we've seen where, in the same way that when you look at profilers, that we can measure cache misses or pipeline stalls or things about the hardware, where that's shown big improvements over just merely running a CPU profiler. And in that same vein, collecting more than just the CPU load information can really be helpful for certain applications. So that's essentially what we're doing. That's what vector load balancing is for us. So rather than just being a single value, which traditionally has just been the CPU load, load is now a vector of multiple values. So how we've integrated this into Charm, we've had to make a few changes to the infrastructure. We've had to store vector loads in the LB database, pass these vector loads into strategies, use them in the strategies to make decisions. But we've done all that now, so now Charm is enabled to use these vector loads to make better decisions. And when we talk about vector loads, these vector loads can be filled with really any data. So we can use these sort of generically. We can use them for various hardware measurements, such as CPU time or GPU time, or memory capacity or network sends, things like that. We can use this to describe discrete parts of an iteration. So like the subphases that Phil, for example, was just talking about, or perhaps application-specific parameters that could correlate with the performance of what your application looks like that normally we as a runtime couldn't get access to. So there are some difficulties that come with this. One of the big things is that the extra dimensionality with vectors makes load balancing really, really hard computationally. It's already an NP-complete problem even in one dimension. So we're only interested in approximations, but especially as dimensions grow, a notion of what load should go to what location becomes very, very hard. One of the big reasons why this is that objects can no longer be totally ordered. And we still want to minimize the maximum in each dimension because we think that is going to improve performance, but figuring out where to place these things can be quite difficult. And we often can't use the same sort of data structures and techniques we've used in the past. So we need new strategies to address these problems. One really simple thing we can do is just sort of this version of the greedy LB that we have in Charm, where we find the object with the global maximum load dimension. So we look through all the dimensions of every object and see which one has the biggest value in one of its dimensions. Pick that object and then place it on the PE with the minimum load across all the PEs in that dimension. So this works well, but really only works well when the object has load in just one dimension, because we only consider one at a time when we're looking at balancing. So for more realistic cases, we have to consider the whole vector holistically. We have to look at both the object and the processors and how they mesh together and see how that increases the total load by some sense. So we have to kind of step back and look at everything at once. So there are a few ways of doing this as well. So we have a lot of different ideas about how to do this well, and it's still sort of a research problem on our end, but I'll describe to you two of the solutions we've come up with so far. One thing we can do is to find the object with the maximum P norm for some P, place on the PE with minimum P norm after placement. This works really well because we ensure that none of the dimensions of the vector grows too big, but it can be computationally quite expensive. We have to do a lot of math with powers. And the other big trouble is that the PE weight often varies with an object. For example, the 2 norm of a PE with load 2.0 is less than the 2 norm of a PE with load 0.3. But if we have the object 3.0, placing that is actually better on the one that has a larger weight than the smaller weight. So using the traditional greedy heuristics doesn't really work here in terms of cutting off where to look at. Usually we just use a heap. We can't necessarily do that anymore. Another technique is to calculate the average load vector across all of the objects and processors and put that as a point in D space, where D is the number of dimensions we're working with. Use that, create a normal hyperplane at that point, and then repeatedly, just iteratively allow the furthest PE below that hyperplane to choose an object to get closer to that average every time. So this also can be computationally difficult for largely the same reasons as I just described. But sort of this hill climbing approach to get to some sort of equilibrium. So we have some ideas on how to optimize these things. They work, but they're kind of slow right now. A lot of the other strategies we've come up with are sort of things in this vein. And it's quite difficult to do these things when you have to consider all these different aspects of a load vector. So more logistically speaking, in support of all these things, we have to add some new APIs to Charm to support vector loads. So one thing I'll mention, the terminology is slightly confusing with Phil's talk just now. What he calls subphases, we just call phases. And as you've seen in his example, and as you can, I'm sure, figure out from other applications, a lot of applications will have these orthogonal phases within an iteration, separated by barriers or sometimes some kind of weaker synchronization. So in order to support these in Charm++, we've added some new functions to track phase information. So we have a function called cklbsetPhase, which takes an integer phase. And basically what that does is until the next time you call this function, every time the runtime system measures load, that load is attributed to that phase of that object. So we can automatically do this. Basically, the user just has to make these one single calls. They can also query for the current phase using cklb get phase. So this should hopefully be an easy on-ramp for people who have applications that look like this. Separately, we have a way of doing this all manually. So we've also added an API for recording vector load data where that the user can fully specify. So that looks like this. We have the cklb set obj time, where you can submit a load that's of LB real type. It's basically a float or a double, and a dimension, specifying which dimension of the vector you want that load to go into. You can also, of course, query that. So this lets you add in application-specific parameters. If you have measurements of the number of particles on a GPU, for example, and you use that as a metric for your GPU load, you can put that in directly. So this lets you do whatever you want, essentially. So once we've tied all those things into the database, another thing we have to do is, of course, use that data to make informed decisions. So a couple notes with that. One is that currently only strategy is built on top of the new TreeLB support vector load balancing. The TreeLB is this new load balancing, new load balancer coming out in Charm 6.11. If you want more information about it, you can see our previous workshop talks, and the documentation right now has been updated to reflect what that is. But in summary, it's this new sort of flexible optimized replacement of central LB and hybrid LB. So it lets us make these hierarchical structured trees that let us run load balancing at various parts of the job topology with various frequencies and things like that. Eventually, we plan on migrating all of the non-distributed strategies into TreeLB. At some point in the future, of course, we'll get vector load balancing working with distributed strategies as well. But as of right now, you have to use TreeLB for the current Charm support. And the way that it's constructed right now, if the runtime system detects a vector load in the LB database at all, then it automatically uses a vector version of the chosen strategy. And this relies on templates, as we'll see in a few slides. So another thing is, of course, writing these vector strategies. So I've described to you some of the algorithms we've used, but let me talk to you about how we actually construct them. And if the user wants to, they can do this themselves as well, if you want custom load balancing strategies that use vectors. So the object and PE types that we use inside these strategies are templated on the dimension, and then that's externally accessible. There's a static const expr field inside that lets you extract that dimension. If you want to query the load of one of those objects, there's this get load function where you can pass a dimension, and you get the load back for that dimension. And as I said, the template specialization, you can use template specialization to allow the author of the LB to handle these different vector and non-vector cases or specific dimensions. So here's a quick example of that. So this is how strategies that use TreeLB look. Essentially, they inherit from this public strategy, which is templated on object, processor, and solution. And here we see that in this top version, we have a vector implementation that uses this generic template parameter O. Down below, we have a scalar implementation. This is a partially specialized version of this class. And you see that we're specializing on object 1, which means we're doing objects with just one dimension. We assume that the processor also has one dimension in this case, but we don't need to separately template on that. So this lets me, as a load balancing developer, write my scalar implementation separately from my vector implementation. If I wanted, I could have a specific 2-dimensional implementation or a 3-dimensional implementation or whatever I'd want. Okay, so now a few performance plots. These will mostly use basic benchmarks. So these are hypothetical applications that we've designed to test these vector load balancing features. So first off, an AMPI. This is a timeline view of an application with no load balancing. On the x-axis, we have time. On the y-axis, we have PE. So as you can see here, the red represents computation, and these blank white spots represent idle time. So you see we have a lot of idle time in this application, and we have these sort of distinct phases of different size and different PEs. When we use regular load balancing, we see that the load balancing period happens right around here. And we see that on the right side, we do have better utilization and better balance of the load on all the PEs. But we still have these gaps in these phases. If we use vector load balancing, which is cognizant of the particular separate phases on each PE, you see that the gaps have shrunk because we now at the load balancer level know that when we place an object somewhere that it contributes to these particular phases. So this is an overview of the previous 3 slides. As you can see, we have the LB off, the phase unaware, and the phase aware versions of load balancing. And we get 1.44x speed up from regular load balancing compared to using no load balancing at all. But using a phase aware load balancer, we get a 1.67 times speed up compared to no load balancing at all. So for this contrived application, granted, we do see this big boost in performance. Another view on the same thing. So we designed another char application that does effectively the same thing, where we have distinct phases of chars. And now for another view of it, we're using time profile here, which on the x-axis is time, on the y-axis is total processor utilization. So here again, when we don't use a load balancer at all, we see that we have a lot of idle time up top. When we do use load balancing, we do get spikes up to 100% utilization, but then we get a lot of gaps in between these phases because the phases themselves aren't well balanced. But when you use the vector version of this greedy load balancer, we get much, much closer to 100% utilization after the load balancing decisions have been made halfway through this execution. So again, it's clear that in these test applications that we do get a lot of benefit from using vector load balancing and these new strategies we've developed. So of course, those are all kind of simplified benchmarks. Really what we want to do is get these in working order with real applications. So I personally have started to do this for a couple of our larger applications. So I have a working version of all this vector LB stuff tied into Changa. I don't have performance results at scale yet, so I don't have plots for what that looks like, but all the load information is being recorded and the strategies are running in this vector mode. For Changa, there's a very good mapping between the structure of the application and vector load balancing. Changa uses something called multi-time stepping. And in multi-time stepping, we have different rungs of the application in which different parts of this domain are active. So we can very easily map the time spent in each rung of multi-stepping to a dimension in this load vector, and then use that to make informed decisions about where to place things. One of the problems right now is that it's also very important to minimize communication in these sorts of applications and make sure that objects are mapped to the same PE or nearby PEs. And right now, none of our vector load balancers take that into account. So that's something that we certainly have to add, but that's something I'm also actively working on. For another angle on vector load balancing, I'm also doing the same thing for NAMD. So NAMD is a different sort of application. Of course, it's a molecular dynamics simulation, but it uses CUDA very, very effectively. And one of the things we'd like to do for NAMD is to balance both CPU and GPU load to be able to make sure that it works well for applications regardless of what the hardware resource is. So that's something I'm actively in the process of doing and measuring right now. For anyone else out there, if you think that your application would benefit from vector load balancing or it has some characteristics that we can exploit with this, please contact me. I would love to hear from other Charm users that can use this. So to talk quickly about some future vector LB work, one of the issues that I mentioned before is that we have these strategies that seemingly work well, that do this holistic consideration of the problem domain, but performance is still a bit of an issue, so we need some optimizations. So we have a lot of ideas in this vein. things like discretization, doing some candidate style clustering, making space partitioning, using some space partitioning style data structures to figure out where to pick certain objects. And that should all go quite a long way. I think that'll decrease a lot of our complexity and help us with these selection processes a lot. Another thing that we're trying to do is exploit the distribution of load per dimension. What can often happen in applications like this is that certain dimensions are very, very sparse, where most of the objects have zero load in that dimension, but some have some high amount of load. So this can happen, for example, with Changa and its rungs. So we can reduce the dimensionality of the whole problem and ensure that we have a good balance for objects with that dimension when we try to exploit this distribution. Another thing, as I mentioned with NAMD to some degree, we have this accelerator API called Happy that Jamin kind of mentioned in his talk earlier today. One thing we'd like to do is integrate Happy into load measurement to automatically record accelerator load so that any Charm users who use Happy to use CUDA or other accelerators will automatically have the load information for their kernels attributed to their objects and put into the vector load balancer so that we can more effectively balance CPU and GPU work. Another thing is to add support for constraint-based objective functions. So far, we've just been talking about minimizing this load, but really we don't necessarily need to do that for applications that rely on cache locality or that have capacity constraints on memory. We really just need to keep this below some threshold to ensure we're able to fill the physical capacity of what the machine is and not go past that. So that can simplify some of these strategies in the future. So in conclusion, we've seen that applications have a lot of scope for improved load balance, especially looking forward as hardware gets more complex and programming techniques get more complex. Providing that more detailed load data that we've been able to do via vector LB has been shown to improve this decision quality over the more opaque traditional LB in testing. So looking forward, I think this is going to be a necessary part of complex applications to ensure that they maintain scalability and high performance. That's all I have, but I'll gladly take questions. Thanks.
I had a question about I guess the goals of load balancing. Like you mentioned at the beginning, the ultimate goal is to just get faster performance. You don't care, quote unquote, what the balance looks like. But does that simplify things? Like you talked about vector load balancing in general, where components of your load might be like CPU time and GPU time, where the load balancers have no inherent knowledge of how those times overlap or what the dependencies between those things are. Whereas when you're looking at phase-based in particular, like Phil kind of mentioned in his talk, the total application time is the sum of those, how long it takes each phase to execute. So since you have sort of a more concrete goal in the phase-based system, is there more you can do in load balancing strategies to specifically target that should simplify the problem, or is it still degenerate to like a pretty general case?
Yeah, it's a good question. I'm not sure exactly. I've done some thinking and some testing in that vein. What we're doing now, especially for the CPU GPU case where things can overlap, or other cases where we don't have these strict barriers between phases or between dimensions, we're probably solving a more difficult version of the problem than we have to, because we're considering that we want to minimize every single dimension when really we could just minimize the maximum potentially of each vector, which would reduce us down to sort of the scalar problem in some sense. I think the solution that we have is still, we'd still produce a good solution for it, though we might be doing extra work. So to get to the crux of your question, yeah, if we can figure out a way of exploiting exactly what our objective function is, given the data and given what our application looks like, we might be able to simplify some of the strategies. I'm not sure quite how to do that yet, but if we could find good ways, then that's something that I think we should certainly add.
And if I may add, in some cases, what we need to do is simpler. Some of the dimensions don't quite collapse. They are there, but they combine in a different way. And the best example I can think of is the memory constraint, right? Or same thing applies to communication volume constraint. But if you want to keep the memory occupancy of each node below some constraint, it doesn't really matter. It's a capacity constraint. You're not trying to balance it. You're not trying to equalize it. You're trying to fit within the memory of that node by not allocating it objects that don't do much computing but occupy a lot of memory. So one can do that by just simply keeping track of it up to some point in your whatever heuristic you're using. So there are algorithms get kind of modified, if not simpler. They are less complex than this multidimensional optimization, but they still require some modification. I don't know if that connected with the question properly, but yeah. But just consider those cases is what I'm saying. Memory, communication injection. Old problem in charm greedy strategies used to be that the greedy algorithm just goes, assigns the heaviest objects to the least loaded processor in a cycle, and towards the end it is dealing with a whole bunch of lightly loaded light objects, but all those light objects are not adding much work to the same least loaded processor, so the same one gets selected, and you add a whole bunch of tiny objects on it. And those tiny objects end up doing communication, and so that was creating problems. So it's these kinds of problems that a vector balancer needs to address as well.
Right.
Any other questions, I guess? Didn't Phil have questions? In the Google Doc, I see Phil has 2 questions there.
Yeah. I mean, I guess the big question I have that kind of spans all of these is you talked about writing kind of generic strategies, that are independent of the number or the dimensionality of the vector. But it seems that with different metrics, having different physical dimension, memory versus time versus communication, or time measured on 2 different, kinds of devices, heterogeneous time between CPU and GPU. It would seem that like a generic strategy that doesn't know what dimension, what physical unit a given dimension represents won't really be able to make sense of that, except in a very abstract, like hyperplane cut kind of sense that you described as one heuristic strategy.
Yeah, that's a good point. One thing that we basically do now is normalize everything, which makes it invariant in terms of units, but potentially gives more importance to things that don't deserve it. So yeah, it's very true. And part of the idea behind this is that we can create these generic strategies, but they may or may not be universally applicable. So the slide that you presented, in fact, where you're talking about these different forms of combination and filtering of what the load looks like before it reaches things, and the slide you had about models, something like that could be very useful here too, where you sort of have this pre-conditioning phase where we send the load through something to filter it down to the set of things that the user deems important.
Yeah, I've also looked at some notion of like whether it might be worthwhile to try normalizing loads in some fashion, scaling them by the max or the average or something, like basically to make the load representation scale invariant in some way, just to figure out whether that would help any aspect of the process. And never really got anywhere. So if you get traction on that, I look forward to hearing about it.
Yeah, I don't necessarily have a good reason to do it empirically. Some of the literature in this vein does that already, but it's much more concerned from a theoretical perspective than a practical one.
Yeah.
So yeah, I don't know if that's actually going to be beneficial or not in real life, but that's what we're doing right now. So once we get stuff working at scale with NAMD and Changa or other applications, then we'll certainly see if that has an impact.
Cool, thanks.
And treating different dimensions differently, ways of combining different dimensions differently is definitely part of my agenda. And
Looks
therefore
like
it will be Ronak's too.
it looks like there's another question or two in the Zoom chat from Niels and Francois Hibbert.
I thought those were older questions.
No.
Oh no, they're new
No,
questions.
I mean,
Okay.
my question is sort of fairly general and it's sort of would it be helpful, or is there a way we can supply the connectivity graph and weights for it to Charm++ for load balancing? It's somewhat tangential, but like in our case, we know exactly what the connectivity is between all of the chars and how much communication there will be, how often they communicate, and everything. We know that sort of a priori. I realize Charm++ measures all of this, but my thought process is sort of from a follow-up to Francois's talk is, could we give this information before we start the simulation to Charm++ and do a more expensive load balancing procedure that tries to minimize communication or something like this?
So somehow this issue has fallen. People are thinking of this. I want to understand why, Ronak, as something new. This is something that we have always had at, right? Parametis, Scotch. There is actually a whole bunch of stuff we did on Scotch exactly for this reason, doing a graph load balancer to begin with. And then after that, you can just do normal refinement, which will hopefully keep things carefully. But also you can do prefix-based balancer, which somehow again has fallen off our distribution, looks like. And or Kavita's, Kavita implemented it. It's some European paper idea, which is refinement of graph, which is not that different than something I heard today from, I mean, at least overlaps with something I heard from Lercio about, seems like graph refinement of some sort. So Ronak, can you say something about the state of software and why these questions are arising, and what's your opinion about that overall? And Kavita can chime in too if you want.
It's a good question for sure. We do support, like Sanjay was saying, these different graph refinement or graph partitioning style balancers, Zoltan, Scotch, Metis. And normally these I believe are all in the documentation and should be working, at least as some of them are tested. I don't think Scotch is because it's external, but I believe the other two are, and they should be working fine with Charm, last I know. But yeah, I think it's probably a question of what we're recommending. I think largely educationally, we certainly talk about these more basic load balancers like Greedy and things in that vein. And maybe there's just an awareness problem with the other ones.
Yeah, so I mean, for us, sort of, we couldn't get the Scotch one to work at all, and the Metis one keeps seg faulting on us, and this makes it very difficult to use, obviously.
Yeah,
and
of
the
course.
other thing we sort of have found to sort of, I think that answers Sanjay's question of why does this keep coming up? It's sort of documented, but not well. And I realize writing good documentation is super difficult. So this is, this is sort of asking, would it be possible to put some effort on that front? Because that's sort of what we have found the most difficult with load balancing is reading the documentation, figuring out what guarantees we have, and which load balancers to sort of use given what we want to do or what we know, or in different situations. And so I wouldn't be surprised
I got
if
an answer.
99% documentation.
Yeah, I think I understand the problem. We will take steps to fix it. I think part of the reason also is over time, the set of applications we use starts homing on to either their own or start finding some greedy or some simple thing good enough, and then they stop paying attention, and those strategies again start gathering dust. So we need to get back and do a good job of it.
Yeah, I think largely the problem is just that it was mostly older grad students who've since graduated who've worked on those things, and then since then, yeah. But I agree. Like we should get them working because all the machinery is in place, and if you can't use them, then it's clearly a failing on our part. So that's something we should fix.
Yeah, I mean, so my advisor has said it very well, that the problem with grad students is that they graduate. So,
yeah.
I sympathize with,
As a
maintaining these
professor, I'm
things
very
over the
well aware
long
of
term.
that problem. Yeah.
Yeah. So it's, yeah.
It's not well recognized by the student community. No. Okay, enough on that. Let's move on.
Thanks for the talk, Ronak. The next talk is on improving NAMD performance and scaling on heterogeneous architectures by David Hardy and Julio from UISC.
Hi, everyone. Can you see my slides?
Yep, but not slideshow yet.
Yes. Let me see how to. Oh, there's the play button. It was hiding.
Yep.
Okay, there we go. I seem to have lost my mouse now, too. There it is. So hi, thanks for giving us this opportunity to present our recent work on NAMD. So NAMD is a scalable molecular dynamics code. It is one of the earliest Charm++ applications, so the code is written in C++ and Charm++ and CUDA. And our performance scales to hundreds of thousands of CPU cores and tens of thousands of GPUs. And we can really scale NAMD simulations in a couple of different ways. One way is to take a large system and do like this single copy strong scaling of the system across multiple nodes. And then another way is to employ some sort of enhanced sampling technique with multiple copy scaling. And so in this case, you might have a much more modestly sized system. And then say you've got one copy of your system per, say, GPU on your parallel computer. And then you could do multiple copy scaling across all of the GPUs in the computer. And so anyway, and we're interested in supporting both of these approaches because both of these are important for scientific investigation. So NAMD runs on laptops up to supercomputers. We run on the AWS cloud and MS Azure. We also provide something that distinguishes NAMD from other MD codes. We actually provide a TCL scripting interface. And so this can actually provide a form of workflow control or even some sort of higher level method development. And we do structure preparation and analysis with VMD. And in particular, we have a plugin now to VMD called QuickMD that gives scientists a really accessible interface to NAMD for setting up their simulations and getting themselves going. So some of the highlights of NAMD are these advanced features that we provide. So we provide a collection of user-defined forces. We provide these accelerated sampling methods. So one in particular that I'll mention again is replica exchange, in which you're running a number of these small systems, and then
David, I think you're not progressing off the title slide for our view.
I'm not. Okay.
We need to break out of the play and restart it or something.
Stop sharing. Let's try it again. That'd be a shame because I have some really nice movies in there too. So. Can you see that?
Gray screen right now.
Sorry, what is it that you're seeing? Or not seeing?
Displaying gray screen.
Just a gray screen.
Yeah, I got the same thing, gray screen.
Huh. Do I need to maybe exit from Zoom and rejoin Zoom? Will that help? Or is it just an issue with playing a slideshow and for some reason it doesn't share the screen correctly?
Not sure.
Any suggestions?
So, Dave, which option did you choose when you try to screen share? Are you sharing the whole screen or just the application?
Just the application.
Okay. Could you try doing the whole screen instead? See if that works.
Yeah, okay. Let's try that instead. So let's share the desktop. How's that?
Okay, and move forward and back one slide just to make sure.
Okay.
Yep.
Yeah, it seems to work.
You're good.
Right. So this is one of the slides you missed. Sorry about that.
Beautiful pictures too. We don't want to miss them.
Right, exactly. So yeah. So the movies that hopefully you now are seeing are illustrations of some of these advanced features that I'm talking about. So the user-defined forces with this proteasome simulation, the use of grid forces to do this membrane vesicle fusion and formation. So another important method in NAMD is this collective variables module. And so this is actually a separately developed a library that we include in NAMD. And so we don't develop it ourselves, but we work closely with the developers of Colvars. But this allows a lot of flexibility in how you could define collective variables that you could use to bias your simulation and enhance your sampling. So for instance, this ABC transporter mechanism, the collective variable had to do with defining sort of an angle and then forcing that, transporter opened and closed. We have a rich collection of alchemical transformations. These allow us to do free energy perturbation and thermodynamic integration. And we also can attach NAMD to do hybrid QM-MM simulations to various QM packages as well. So when we're doing molecular dynamics simulation, at its most fundamental level, we're integrating Newton's equations of motion. And so this is just a system of ODEs that we're integrating in time, but up to billions of time steps. And most of the computational work is in calculating the forces between atoms. And in fact, the most expensive part of that are the non-bonded forces that are due to Lennard-Jones and electrostatics. And so the parallelism for MD simulation is limited then to each time step. And so if you just look at the computational workflow, you'll initialize, say, particle positions, and you will calculate forces on those particles, and then you'll use those forces to update the positions again. And you'll sit in this loop for millions or even billions of time steps. Occasionally, you will do some output to supply some reduced quantities to the user, like the energies or temperature or pressure, or even less frequently, you might do an entire snapshot of the positions to record what your trajectory has been for this simulation that you've done. And so the force calculation itself, that's, you know, somewhere in the neighborhood of 99% of the computational work. The updated positions is much smaller. So a lot of work has gone into NAMD to decompose these force terms into these fine-grained objects that then we can schedule and move around, load balance for scalability. And so when we've applied GPUs to do this calculation, we've offloaded forces to the GPU. Now, back when GPUs were less capable, we focused solely on the non-bonded forces. Today, we load almost all of the forces to GPU. And so this strategy has given us a lot of scalable parallelism. And so here I'm showing you some of the scalable results where we're measuring performance in terms of the nanoseconds of, or the computed nanoseconds of simulation per day, and then shown, on the number of nodes to achieve that performance. And so these are strong scaling plots here on two of the leading supercomputers right now. And this case is showing just our synthetic benchmarks that are created by replicating this STMV million atom virus and tiling space with it so that, we can create whatever sized benchmark seems appropriate. The two that we have generally been using are this 224 million atom matrix and this 21 million atom matrix. Well, recently we've had the opportunity to work with the Amaro lab at UCSD, where they've been simulating the SARS-CoV-2 on Summit, and so so these are some really nice results here, where they've done this scaling performance of this 305 million atom virion, and then we went ahead and scaled it across almost all of the nodes available on Summit, and what we saw is that we got reasonably good, strong scaling efficiency for this application, MD, so it continued to be about 50% efficient at, the ends of, what the resources that Summit provides. However, when we have done benchmarks on single nodes or newer GPUs, it's revealed problems. And so we can take a look at, say, the NAMD 213 performance going from Pascal to Volta, and we saw a 20% performance improvement just when we're running our standard 8.1 benchmark on just a single GPU. However, the hardware itself had a 70% performance improvement. So we haven't been taking full advantage of the GPU. And we can see that when we do some profiling on these modern GPUs. So this is something that was produced by Insight Systems, where you can see these gaps in the blue strips here on the plot. And so that's showing where the GPU is idle, where we're not keeping the GPU busy. And so the problem is that, NAMD 213 and now NAMD 214 have limited GPU performance. And the issue is that offloading force calculation is not enough. Our overall utilization of modern GPUs is limited now by the CPU work. And it's limited by that, 1%, amount of work that I showed that's just due to the time stepping that is still on the CPU. So we want better single GPU performance, also because the majority of MD users are running system sizes that are less than 1 million atoms, which works really well on a single GPU. So what this means for us is that we must transition from a GPU offload approach to a GPU resident one, in which we are maintaining data on the GPU across time steps. So we've been working now on developing this over the past couple of years on developing a GPU resident version of NAMD. So in this case, we are fetching the GPU force buffers directly from the force modules. We're bypassing any of the CPU GPU memory transfers so that we're only calling the GPU kernels. We've also converted the forces into a structure of arrays data structure. This way we can invoke the GPU integration tasks once and do that on the GPU and keep all of this data on the GPU. And so this development has led to better GPU utilization. And so now if we compare to the NAMD 214 profiling, where we see the gaps between the GPU tasks, NAMD 3, we don't see these gaps anymore. We don't have the same CPU bottlenecks that we used to have. And so if we look at what the overall performance is now on different systems, we see that we can get really good performance on small systems like the Jack benchmark from the Amber community that we used to not really perform well at all. And so all across here, we're seeing a better than 2x performance improvement now on when we more fully utilize the GPU. And furthermore, by pulling all of this work off of the CPU, it allows us to get really good aggregate throughput on hardware that is a GPU dense hardware, like a DGX2. And so if you're looking at the DGX2, you only have 48 CPU cores there, so you only have 3 CPU cores per GPU. For the older NAMD 214 or earlier, it really required a lot of CPU power to be able to do this calculation and for the CPU to try and keep up with the GPU and feed the GPU. Well, now we can run these benchmarks perfectly well just on 1 or 2 cores per GPU. And really what's getting all of the work now are the GPU. And it allows us to just fully saturate a dense GPU dense system like this with work. And so that's what we're seeing here when we're calculating now the aggregate throughput, where we've just summed all the nanoseconds per day that we get from the 16 different replicas. And so it's just a huge performance boost over what we had, what we have available in NAMD 214. And so all of that is right now available in an alpha version of NAMD 3. And now I'm showing you some very new work that is not yet available because it's not really production ready yet. But we've started to get some results now on multiple GPU performance. And so this is just showing our first attempt, that's starting to realize this, where we're trying to scale a system across multiple GPUs, in a single node, so that these are tightly connected GPUs. And so here we're seeing some really decent first results of doing that. What this approach is doing is really just employing the nickel library to first populate positions across each GPU so that that GPU can calculate its forces that it's responsible for, and then again another nickel reduction to sum the forces back. So there's a lot of overhead from this approach right now, and that's not why we're not really seeing linear scaling on this yet. But it's we feel good about the fact that this is giving us something right now. However, we haven't extended this to PME yet. PME is a little bit complicated to handle. So let's talk about that. The problem is that PME impedes scalability. So for multi-node scaling, the 3D FFT communication costs in PME grows faster than the computation cost. And so we're even seeing a problem right now for our single node multi-GPU scaling. The 3D FFTs that we wanted, that we need to do for PME for these problem sizes are too small to parallelize effectively with CUFT. Also, too much latency is introduced with an attempt to just do our own pencil decomposition and employ CUFT across 1D FFTs. So it looks like task-based parallelism here might be best as far as delegating one of the GPUs for the 3D FFTs and the reciprocal space calculation. However, doing that will require gathering all the grid data to that one GPU and then being careful not to overload that GPU with other work. So then, of course, the question is, why not use a better scaling algorithm such as MSM? So let's talk a little bit about multi-level summation method next. What this method is doing is, instead of doing the calculation that PME is doing, this is splitting the 1 over R potential into not just two pieces, but we're splitting into a short range cutoff part, plus these smooth parts that are successively more slowly varying, where all but the top level potential are cut off. And then these smooth potentials are interpolated from successively coarser grids. And so this the finest grid spacing H and the smallest cutoff distance A are then doubled at each successive level. So this actually gives us a linear time calculation for MSM. And so the computational steps involved calculating, again, this short range cutoff part that you can see along the bottom part of this, kind of inverted V cycle with bars across it. And then the interpolation and interpolation parts, these are really almost the same operations that you're doing when you're doing the PME charge spreading and the PME force interpolation. And then when you're at the grid levels, you have these familiar restriction and prolongation operations, just like you do with a multi-grid problem. But then the added work here is this grid cutoff calculation that you're performing. And this is simply a 3D convolution where you're convolving the charges, the grid charges with a fixed convolution kernel to get grid potentials at each of these levels. And so the reason why we haven't already been using periodic MSM is that the previous implementation was fine for non-periodic boundaries, but it was insufficient for periodic boundary conditions. It provided lower accuracy than PME, and it also required the system of atoms be neutrally charged, which is not always the case with what what the application, what people expect from the application. And so we have a very recent new development for MSM And so this involves interpolation now with periodic B-spline basis functions, which ends up giving us the same accuracy as PME. And then we can now handle this infinite 1/r tail as a reciprocal space calculation at the top level of the grid. And so what this allows us to do is terminate the number of grid levels long before reaching just a single point. But we can use that to bound the size of the FFT. In other words, we can make the FFT as small as what would be comfortable for just a single GPU or a single node to calculate. And otherwise, this is giving us this much better, much more scalable algorithm where the communication at each level is nearest neighbor going up the tree up to the top grid level. So this is something that we're in the process of developing right now. Now, in terms of extending NAMD3 to multiple nodes, we're interested in reintroducing Charm++ communication. And so I need to say that, you know, the way we got great performance on just a single GPU was to remove some of NAMD's infrastructure that involved the Charm++ handling of say, the force calculation out of the way. And so what we did here was we had these these GPU integration kernels called the force kernels directly. And we also had issues with just the user level threading that was going on in our sequencer objects. And so the unused sequencer user level threads are actually put to sleep, and you don't wake the threads up until you do an atom migration between patches or whenever you're doing the coordinate output. And so the question now that we're looking into is whether GPU direct messaging will be the best alternative. And we're aware that Charm++ support is now being developed to support that. So we have some additional challenges for NAMD as well. First is to have a feature complete GPU resident version. So NAMD3 for now only supports a subset of the features and not a lot of the advanced features. Another thing that poses issues for us is incorporating culvars in a way that is not going to just crush our performance. And so the way culvars is implemented and the way it talks to NAMD right now actually poses a significant performance penalty. And so we've actually considered, what if we re-implemented parts of culvars on the GPU? And finally, we are faced with the issue of introducing support for the other GPU vendors. And so we've actually been working with people from both AMD and Intel towards some initial porting of NAMD to AMD HIP and to Intel DPC++. And so that's an ongoing ongoing work for us as well. So finally, I'd like to especially acknowledge here Julio Maya, who has done the heavy lifting on the GPU developments that we have now for our single GPU and multi-GPU support in NAMD3. And of course, we get a lot of great advice from John Stone and Jim Phillips and the rest of the NAMD team. Thanks very much. Are there any questions for me?
Yes, when you're talking about GPU direct messaging, do you mean you're running a resident like GPU thread and then you call the messaging inside the GPU or actually doing it in the on the host?
The idea is that if we can keep data on the GPUs as much as possible without engaging the host. So whether that means things are set up by the host to go ahead and do communication of data directly between a GPU on one node to another node, say.
So this is still initiated by the host, not by the GPU kernel.
So it's initiated still by the host. That was my question.
Right. Yes.
Okay.
Is it possible to initiate it from the device?
There's some work going on that, but it's a little bit tricky because you don't have the whole, communication software stack running on the GPU.
Yeah, that's what I thought. Yeah, okay.
But
right now,
you can invent some standard. I mean, there was some effort in, for example, in MPI that they call it session. So basically, you can schedule a big message, and then every time when a piece is ready, so when the trunk is ready, and then you can say this is ready, and then MPI can send that portion of the message. So this works with GPU because then multiple threads can work on the same, different chunks, but same message, one message. So, and when each thread gets ready, it can call the function and then MPI can trigger the send. So if you leverage this kind of API, and basically you can set up, for example, the CPU can set up the communication schedule, and then the GPU can only tell that it's ready to send. And then it's give the illusion of that the GPU is triggering the send, but actually everything is set up in the CPU, but you kind of have a quicker way of starting the communication.
I think that's fine for what we're doing, since really it's the CPU that's driving the GPU kernels to begin with. So, that type of control makes sense to me.
Completion and initiation is at least currently managed on the host side. So might as well. Okay.
So there's no effort to basically offload everything on GPU in MD.
For the reasons that you just outlined, there seems to be, but every piece, I think, David, correct me, but sequencer, compute, so everything to do with the data will be moved eventually to the device. That's our plan.
That's actually the goal right now, yes.
The initiation of communication, initiation of kernels will be done by the host.
Right, okay.
Are there any other questions? I guess we'll move to the next talk otherwise. Thanks. Well, the next talk, not a talk, but a discussion. Is that Sam?
It's Eric Baum.
Right.
All right. Sharing my screen. Should be able to see the Charm release notes webpage if that's working correctly. All right. So just going to do a quick review of what's new in Charm 6.11, and then kick off a bit of a discussion regarding what people would like to see in future versions of Charm. So as a note, and a bit of a preview, we are transitioning our online discussion default form to be in the GitHub discussions. instead of the old mailing list. So I'm going to put a link for that in the Google Doc. All right. So this is a feature release, and the focus has been on overhauling the load balancing infrastructure. The goals here are essentially to make it much easier for people to develop new load balancers on the existing infrastructure, and make it so that you don't have to go through a whole lot of steps that used to be required, and that you now should not need to like make any alterations to the charm source tree itself to have a custom load balancer for your application. And so this included a number of changes to the architecture, where we've been replacing the old central LB and hybrid base LB designs. And these have been essentially incorporated, at least necessary features have been incorporated into tree LB. And so a much more in-depth discussion is available in the docs and from some of the earlier talks that we had in the workshop. One of the other focal points for the 6.11 release has been improving GPU performance with a special focus on minimizing redundant copies. And that has been by utilizing GPU direct and zero copy approaches, so that when we need to transition data intranode for GPUs, it can be sent directly without any kind of a copy having to go through host memory. So this allows for much better performance on machines with multiple GPUs. And there's related work going to improve the sort of GPU to GPU across nodes as well. But that's future as opposed to being immediately available in 6.11. Beyond that, in the build system, we have switched the default process from the sort of classic build system to using CMake. And the old build system is still available with build old. So if you run into issues where some scheme you used to use doesn't work, build old remains available. But in general, on newer systems or under most conditions, the CMake system should do the right thing and will interoperate better with a more modern ecology in the application space, where they are largely moving towards CMake infrastructure. As noted at the top, we have adopted GitHub discussions, and so that's available in a tab on GitHub, just right there under discussions. And the top level one is the one I just posted, where we are going to collect various ideas and requests people have for future versions. But we expect and hope to have more dynamic, interactive, engaging discussions in the GitHub discussions environment, as it will allow us to cross-link with the rest of the GitHub infrastructure more smoothly than prior venues. And as a matter of note, the BigSim emulator has been deprecated. It's no longer available in 6.11. People who need it can still access it in the older versions. Onward to other features and fixes. There's been a recent focus on improving support in TRAM. Specifically, variable size messages are now supported. And Jamin has been working on improving performance and a variety of other schemes, especially with using node level constructs to minimize redundant issues. And we've added a pup buffer API, so that uses zero copy to do in-place pupping to avoid having essentially both memory bubbles and copy overhead when pup is used under any conditions. And array broadcasts have now been made node aware, so that the redundant copies that were previously required are no longer necessary. and they can further leverage the zero-copy infrastructure. Similarly, expedited no-keep array broadcasts are also supported and should be relatively optimal. We've added CMI node reduce for converse node level reductions. This helps with some of our infrastructure and for any direct users of converse. And we have modified the infrastructure so that the CNP optimize one only does a seg fault instead to avoid some of the other crash behaviors, so that people can actually get the sort of debugging information that they need and not a crazy amount of useless information. And we have modified LiveViz so that it uses callbacks and now interoperates safely with ASLR. We have updated the implementation of various atomics, locks, and fences to use C++11 and C11 versions where the compiler has those, so that they should be both portable and more efficient. We fixed a number of bugs in Happy and updated the implementation to use new CUDA APIs. We added a new attribute to entry methods for speculative execution. This can be called for you when a PE becomes idle. And so this is one of those handy things for various uses, either functionally or to look for misbehaviors, depending on your use case. We've improved performance, support, and fixes for the UCX layer. And IBM Power is also now supported with UCX. So on machines where UCX is available, it should perform well. And in most cases, it is the best choice when it is available. CMI 6Send family now has been tuned up to avoid making excess copies for no-keep messages. We fixed a bug with element IDs and fixed a bug in block map array creation, so it doesn't misbehave terribly under some use cases. The aforementioned win idle is matched by lower level constructs for CCD processor long idle. We've added is checkpoint and is migration methods so that you can have that condition logic inside your pups to correctly change your conditional behavior when that is the case. We've added execution metadata to protections logs, added a number of new benchmarks and tests, and bounded the number of hops messages can take for chars that migrate frequently. Adaptive API has seen a suite of changes. Isomelec sync is now on by default. And so this allows the Isomelec to work safely and correctly and efficiently on essentially all architectures. But if there is some reason to not use it, you can disable it. The AMPI only build target has been added. And this doesn't remove any features of AMPI. It simply turns off features of char++ that AMPI does not use. So it basically removes a bunch of redundant code paths and some actual overhead, which is handy for tuning up AMPI applications. The TLS globals feature has it's fixed basically in terms of how it handles things on macOS. We fixed a number of bugs in activation and migration callbacks, fixed a bug in AMPI wait sum, and now support a number of AMPI build flags and environment variables to personalize or customize the behavior for AMPI CC. And we've improved the portability of both FS globals and pip globals. So that was the high level verbal burst of what we have done for 6.11. For the rest of the discussion, I welcome any questions people may have regarding those features and sort of open the floor for wish lists for the next dot release. Presumably 6.13 would be the one that would have features and 6.12 would have bug fixes. But and also for beyond, just general features in the larger scale the kinds of changes people might think of for Charm Next Generation or Charm 7. I've seeded it with a couple of ideas that we've tossed out, replacing Converse with Argobots, having PEs hosted directly on the accelerator, various ways to avoid having CI files and decals and defs, alternate binding choices for chars instead of being essentially core bound or PE bound. They might have larger scale bindings. There's an opening question right now. If we look at the actual implementation source for char arrays, it has explicit support for array dimensions up to 6. But if you needed higher dimensionality than 6 in your char array, you'd have to go to custom indexing at the moment. Is there a foreseeable need to go higher?
All right.
I guess my feature request would be further expansion on the load balancing documentation. And if I search for pup_buffer currently on Read the Docs, should I be finding it?
Search for what again?
Pup_buffer, the pup buffer thing. Or is that in a future documentation thing? I don't know how Read the Docs works in detail.
No, I think Read the Docs search. While we were talking earlier, I searched too, and I think there is something wrong with the way that I don't know. I couldn't find a few things that I expected to find there. So the fact that many documents are put together there might be part of the problem. But buffer should be documented.
That might be an oversight. It's a newer feature.
Yeah, I think that's yet to be added.
Yeah, and the load balancing, we need to document it, but we also need to get our suite together. So that's very much on our agenda. I would say we will do that. That's understood.
Yeah, and I guess one question I would have is, and we're more than happy to provide, like, this is what we found confusing, or this is what we didn't understand from the documentation. So the question, right, because that's sort of ultimately, like, that's the ultimate test, right? Is can people not working on the project use it? What timeline are you looking at for 6.11, just to make sure, because one of us is moving, and there's other workshops going on. We just want to make sure that we can get you feedback so that can go into main 6.11 early, so we can sort of prioritize that on our end.
Well, I think we wanted to release 6.11 soon, but I'm not sure the load balancing documentation should hold that up.
Right, but no, that's not. But I would like to be able to get you the documentation before you do that, right? So the question is, when do you want to release it so that we can get you, feedback before then?
So, I think the upper bound is we would like to have 6.11 released before Supercomputing 20, so before mid-November.
Okay, yeah, that's perfect. Yeah, that's all I really was asking for was, what, is it 3 days from now, or is it, 3 weeks from now? So.
3 days, it's more than 3 days, because there's a couple of things we really want in there that aren't quite through review yet. So, but it's definitely 1 month-ish, let's say, less than a month.
Okay, perfect. Yeah, just so that, we can run the beta on our end and see if there are any issues that we've encountered. Okay. Thank you.
Thank you. Any other questions or things to discuss? I understand it's the end of a long day, so people's brains may be experiencing fatigue of various sorts.
I wanted to say one other very quick thing. At some point, I think last year, this might have been discussed, greedy and all those other greedy related strategies, greedy calm, which is not really calm anyways, and refine, should all be replaced by this one thing called greedy refine that Juan wrote. And it's reasonably good, and it can actually stand in for both. There is no particular advantage greedy brings that you need to keep those far. Have they been cleaned out, Ronak?
But greedy and greedy refine both exist. The other greedies, I believe, have been removed.
Yeah. Okay. There may be situations where greedy does better, but I think
Yeah, I mean, our experience so far, as Francois showed, is that the rec by part seems to work the best, but it's sort of too early to, for us to be able to say, yes, this is definitely the best thing. And I think sort of long run, it would be like an exact space filling curve, but if you're able to get sort of within 10, 20% of that with something easier.
I think, long run, maybe the effort involved in doing a space filling curve based one is not huge, given that we had a prefix sum based strategy distributed. So I will see what's doable there, but yes, that's very much on the agenda. Yeah.
Go ahead. Yeah, so while we're talking about load balancers, something that I had wondered in doing these initial experiments we've been doing is there any interest or thoughts on supporting an extension of the current behavior where I can run one balancer the first time and then a different balancer every subsequent time, but where I would instead run the special balancer, for example, once out of 100 times, or once every sort of specifiable event, and then the other balancer the majority of the time. And the reason I'm thinking about this is if we have an application that does periodic big changes like AMR, where we might want not just a naive, or sorry, I shouldn't say naive, but maybe we want an expensive load balancer to be applied periodically after a big restructure like AMR.
But this should have been like supported even like 15 years ago. It's from the command line, you can specify multiple dash balancer or plus balancer, I forgot, but you can specify, and then each balancing cycle will use the subsequent load balancer in the command line. Is this feature removed?
I think he wants one that's tuned to an event.
No, for example, I want to run the first one with greedy, and then the subsequent load balancer as a refinement.
Yeah, but what if I want to run, and maybe this is a bad idea, okay, so feel free to tell me so, but what if one out of 20 times I want to run a recursive bipartition, and the other 19 out of 20 times I want to run a refine?
This was the point of what Ben was talking about, NAMD being somewhat easy because it didn't require that much of doing the whole thing very well again. It might have fallen out of use, but we definitely want that. What you're saying is definitely should be supported, whether to do it through a command line option or whether to do it through some kind of a configuration file. We will see, but it should be supported. Ronak,
is supported. Like what he said is supported if you do it once. I think what he was asking is, can you do like heavy duty like greedy, then like 19 refines, and then go back to greedy and do more refines? Right now, it's either you loop or you go to the end and then stay at the last.
Yes, I'm just saying that we should support what he's asking, and we will. It's just a question of how quickly. How it's not hard because it's the same mechanism. If we allow switching, then we can allow the pattern. It's just
yeah, but
do it.
I think there is a generalized feature request kind of in there, whereby the user could ask, can the next load balancer step use strategy X.
Yep.
Yeah,
So-
right. Not a good way to interface with the load balancing manager from within the application. It's like once you get past the command line, it does what it does. So I think that's something we also talked about in the refactoring of the load balancing framework, was a bit better way to interact with it during the application's run, which would be allow you to signify certain events like this.
Yeah, if I remember correctly, there is a function that you can call from the application that lets you set what load balancer to use. It's a little bit opaque in that I think you just have to give it an index. So you have to know what the numbering basically is. But I think you can do this programmatically internally. The other thing I'll say is that this also might be a good use case for meta balancer. Unless you really want to use the static structure of what load balancers you call, if you want to do one and then 19 other ones and then go back. Meta balancer does this in a more reactive way. The thing is that the control of when to call it is sort of out of your hands. You trust the runtime to make these decisions automatically for you. But if that's what you're going to do anyway, then that can be a good solution potentially.
Yeah, although it would still have to trip over the massive change and then realize that the choice that had been good for prior invocations was no longer ideal. So.
Right, like the sort of concrete example that happens is as the black holes get closer together, some parts of the grid become very distorted and not, the Jacobians sort of go bad and everything gets terrible. And at that point, basically what you have to do is scrap the whole grid and completely redraw a lot of the elements that make up the decomposition. And so it's sort of at that point, it would be like, okay, whatever distribution you thought you knew, it's basically completely toast.
So I think the point is that point, you might think it is the physics of it that's deciding it, but the computational behavior is also telling the runtime system the same thing. So it should be able to figure this out. That's Eric's point. But
ideally,
hold on. Even if that's the case, we still would need to provide a fallback anyways. So I think we're going to have to do both. Fully automatic is where we always, we need to have a default that observes everything and does the best job it can. And then the people are still going to think they can do better, and sometimes they can, and you have to always provide that option. So, yeah.
So this would be pretty easy for us to improve the current call structure, right? You just have to add an enum with the names of the strategies.
Ronak is saying it's already there. It's just you have to know the enum mapping. Right, Ronak?
If I believe so, I'm not 100% sure, but I think that function is exposed to the application where you can just say, call this load balancer next time, and you provide the index of the load balancer.
Yeah, so we can replace that call to an index with something. It's a tiny metasyntactic sugar to get it to have them give a name.
And the other improvement that we already have on the Anvil, or is it already there? I don't know. Is within node more frequently you can do within node for things that are kind of using a core as an anchor for a char rather than using OpenMP or something. For those, we can migrate within a node more frequently to postpone having to do across node load balancing, doing it less often instead. So that's another thing that TreeLB has, and I think there is no reason why distributed LPs should not have that feature as well. So all this phase structure, writing some kind of regular expression on command line, or having programmatic interface, so API, whereby you can specify, do this now, are all things that we need to consider. I'm not sure how quickly it will be done, but I think it is not a huge undertaking. We just have to systematically do it.
I guess
a simple suggestion is that if I remember from Francois' plot, basically they ran it once and then did dummy for a long time. One thing you can do is just not call @sync also. And that basically just, you can just avoid calling load balance if you don't want to call something. So it's different if you want to call a different strategy that's not a dummy strategy. But if your solution is just to not call it, you can just never invoke it until you need to invoke it again.
Yeah, granted. I guess the problem we're facing is not quite sure what the strategies will be interesting to us in the long term. We just have reason to believe from these initial experiments that we will want to call the recursive bipartition to clean up the distribution of chars onto the system, at least at the beginning, and probably every time there's a substantial change to the layout of the chars, for example, from AMR, or as Neil said, if we enter a different physics phase of the computation because the black holes are merging or something. So I'm sort of thinking ahead and thinking we're likely to want to do something like the recursive bipartition at some unknown interval, and then whatever else works, we will probably do in between.
Yeah.
So yeah, if the right answer is do nothing, then granted, the optimal thing is to just not load balance. But if we need to use some other sort of polishing load balancer at those intermediate times, then
Yeah, in a perfect world, Meta Balancer would figure this out for you, but we are never in a perfect world, so we want to come up with ways to allow you to get the performance that we can reach.
yeah, and I
or at least ways for us to waste time in coming to the conclusion that you did a good job. That's also good.
Yeah, I have not looked at the Meta Balancer very much, so I will go do my homework on that now.
I guess a quick comment would be, I think having a programming API for this would be somewhat nicer than fancy command line regular expressions. My worry is that, if you have a whole bunch of scripts and scripts and scripts, then you need to be very careful about how you forward arguments to different things. And my worry would be that, then we end up with like a 400 character command line argument or worse. So.
Yeah, that becomes its
One
own.
quick thing I'll mention with this too is that with the new TreeLB, there's command line arguments, but you can also specify a configuration file for your load balancer. So this lets you do it more reproducibly, and you can obviously save the state, not to type it all out on the command line every time.
Yeah, so I mean, does that currently have the way for the user to specify different strategies at different LB iteration counts?
Not at different iteration counts. You can specify, for example, if you have a root node and PE style thing, you can say that you want to run a certain strategy. You can specify 2 strategies, let's say, for the node level, and then there's a repeat strategies option where it'll either go through that and then repeat the last one, or go back to the beginning every time. So those are the options right now. But we can, of course, add some other mapping that says do this 20 times and then do this and then go back. So we can add something similar to what you're suggesting.
I think that's not hard to do, but for the situation that they're describing, it's not likely that they'll always know that it's going to be iteration X. It's a conditional behavior law.
Yeah,
that's right. And so
sorry, go ahead, Francois.
Yeah, I was agreeing that if this can be programmatically specified, that might actually be more useful.
Yeah, I think that's definitely a useful thing to add. It would be good if we could write some of this down concretely in a GitHub issue or in a discussion, so we don't lose track of this too.
Yeah, it's in the Google Doc now, but not as not a GitHub issue yet.
I mean, we're happy to. We can write up a little blurb of like, this is what we want to do, and this is sort of what it dictates the intervals, which in general is some physics thing happens that we don't know ahead of time when it's going to happen, and so we have to sort of be reactive to it. But yeah, we can.
Okay, yeah, that'd be great.
Okay, so that was a fruitful discussion. Any other topics?
In Slack. But it would be really nice. So there's currently, there's like the CK out or like the print, the CK printing, printf, or I forget what it's called. It would be really cool if we could have this sort of functionality, but right into a log file where we specify at the print call where to log it. This is sort of one of the big things that we will ultimately need to do, because if we have different code features or different physics features, or for example, we want a lot of AMR diagnostics. We don't want that all being blasted into C out or into standard out, or being all blasted into the same text file that something else is being blasted into. Having some option of specifying maybe even some writer at the end that you have something that has some static member function or some object or something like that, that then receives the string and writes it to disk in the appropriate manner would be really nice to have.
Do you want it centralized, or do you care about the ordering?
No. I guess, yeah, no. The only thing that exactly what CK out does, just that I can specify a file or a thing that does the write after. So what I'm thinking about, for example, if we have 100 things doing logging, it'd be nice not to have 100 different files, but say have an HDF5 file that has 100 different sub sort of groups in it that contain the data or something like this.
Right. So it might be non-deterministic, but at least it's all in one containable place.
Right, exactly. And it's basically the big thing is having that sort of guarantee that we don't have, if we did just C out or something basic like std C out, where we would then get intermingled garbage to the terminal. So just having that, you charm take care of that guarantee, and then we can say, okay, we have received this thing. We will write it to the file, and we know that the file writing is only going to happen serially.
But you care about the performance. I mean, if we give you another stream or ability to create any arbitrary stream, just like CK out, with a file at the other end, is that good enough for that?
I think so. Yeah.
But that would not mean a database like it has fields and different things going exactly the same place. It is just a grab bag of whatever is you want to spew out to this file.
I would like to be able to specify different files in different parts of the code.
Yeah.
So if I can so basically if I can write to n files for different parts of the program, but those just sort of things just get dumped into there in whatever order they show up, that's perfectly fine.
Yeah. Oh, that's easy. I think we simply make a variable for CK out like object as a stream that you can generate. Okay, we'll discuss it internally, and come up with a solution. But I think I have an idea for what's needed. So. Good.
Yeah, I would guess you have pretty much all of the infrastructure there because you have CK out. So.
Yeah, the way CK out does it is all that we want to do. We just reuse it and have a file connected to it.
Yes, that is exactly what we're looking for.
Yeah, right. In fact, I don't know if Justin discussed this today. The Go. He's trying to implement the Go-like functionality in Charm as example, and in that there are streams, and so maybe that. But anyway, I think I'm jumping. I understand the problem. We don't need to spend time discussing the solution here. So good. Okay.
Right.
I guess that's sort of relate. Oh, sorry.
Go ahead.
A related thing. I think Charm has some like CKIO thing support, right? At least when I looked at this maybe a year and a half ago, I found that there was a lack of documentation on this and how to use it. So I guess another feature request would be if there could be some documentation on this, or at least things that point to example code, because as was mentioned, I think yesterday or something, how to get efficient I/O from these things is non-trivial, and so being able to explore CKIO as an option would be very nice.
Yeah, that's something on my to-do list for the 6.11 release, so that'll definitely be done before that comes out.
Okay, cool. Thank you.
Mm-hmm.
And it is already mostly CKO.
I guess, yeah, for our usage, all we care about is the O part. We try to read in as little as possible, really.
Any other discussion topics? Going once. Going twice. All right. Well, thank you all. That will wrap up our discussion segment for the 6.11 release and future requests. We have any closing workshop announcements that you want to make, Sanjay?
No announcements, but I think we as a group have a issue in front of us, which is for the workshop, which is what to do next year. Current thought is October, still September, October. Is that first of all, we will poll the bigger group, but for people here, do you see an issue with that? We did see some issues with DOE meetings this time, but at least there was one meeting I was aware of, but that would have that had no significant impact. This Argonne meeting, I didn't realize was happening now. So, but there could be overlapping meetings of this sort that we could try to avoid. But overall, late September, October, mid-October, does that sound like an okay time? Yeah. So okay, that's good news. So that's what I think will. In any case, there's probably no appetite to do it in April of next year. So let's assume this for now. We have actually quite a bit of. You saw Larcio from France, who's originally from Brazil. There is Esteban from Venezuela, and then academics-wise, we have Abhinav now at Maryland. So we might also think about some other ways of broadening the conference. So again, your thoughts are welcome by email on that. Other than that, I guess we'll be in touch through other mechanisms. So I think Eric didn't mention, but we are moving from. We created GitHub discussions and trying to use that as the forum for discussion rather than our even eventually mailing list and whatever else mechanisms we were trying before. So let's see if that works well. Anything you want to say about that, Matthias? Or anyone else? Okay. So other than that, thank you very much. This was a challenging workshop to put together with virtualization squared. But I think with all your cooperation and everyone submitting their papers, etc., well, it worked out well. Thank you very much, and we'll keep in touch. Bye then.
Thank you all.
Thank you so much.
Thanks, everybody.
Thank you. Bye-bye.
Bye.
Thank you.
Jonathan,
Good night.
we feel better.
Thank you. Bye.
I see you all. Bye.